A tire built to hold a vehicle steady at 125 miles an hour is not poured, not stamped, not cast from a single block. It is assembled by hand, layer over layer, in roughly 15 minutes. And rubber accounts for only a quarter of what goes into it. The rest is petroleum, steel, carbon, and some 30 separate chemical compounds, bound into a formula Michelin has guarded for 130 years and never disclosed to anyone. A winter tire and a summer tire do not differ in tread pattern alone. They are two fundamentally different chemistries. A single tire for a mining haul truck stands taller than a grown man and costs 40,000 euros. The one riding on a Mars rover carries no air at all. And the deepest secret of all waits at the very end. Michelin was founded by two brothers, Edouard and André Michelin, in 1889 in the small French city of Clermont-Ferrand. In its earliest years, the company turned out ordinary rubber goods, gaskets, hoses, balls for hand pumps. Then, in 1891, everything changed. A cyclist named Charles Tarrant arrived asking for a repair on a tire glued solid to its rim. The job took 8 hours. Edouard Michelin decided it should never take that long again, and he invented the removable bicycle tire, the kind that could be swapped out in minutes, by hand, without tools. It was a breakthrough that reshaped an entire industry. The company never slowed after that. Today, Michelin stands as the largest tire manufacturer on Earth by revenue, having overtaken both Bridgestone and Goodyear. Its tires carry passenger cars, aircraft, mining haul trucks, tractors, and even the rovers of NASA. More than 130 years of unbroken work, and every single year the company produces something it did not know how to make the year before. It does not begin in France. It begins in Thailand, Malaysia, and Indonesia, the countries where the Para rubber tree grows, the tree from which natural rubber is drawn. Every morning before first light, workers move through the plantations and cut a thin spiral groove into the bark, deep enough to reach the vessels beneath, shallow enough to leave the wood unharmed. The tree responds. It begins to weep a white, milky sap called latex. Over the course of a night, a single tree releases about 1 fluid ounce. Not much. But one plantation holds thousands of trees, and each can be cut again the very next day. The latex is gathered in cups, poured into vats, treated with acid, pressed into dense blocks weighing 77 pounds apiece, and shipped across the ocean to Europe. The journey from tree to factory takes several weeks. And here lies the paradox. All of it serves only a quarter of the finished tire. The other 3/4 comes from an entirely different raw material, made by an entirely different method. Synthetic rubber is made from petroleum, from the byproducts of its refining. Under the action of catalysts, chemical compounds line up into long molecular chains and become an elastic material, much like natural rubber. Much like it, but not identical. Natural rubber grips better under heavy load and sheds heat more efficiently at extreme temperatures. Synthetic rubber holds firm in the cold and resists aging under the assault of oxygen and ultraviolet light. Winter tires carry more synthetic. Without it, at 20 below zero, the rubber would stiffen like hard plastic. Summer tires carry more natural rubber. In every tire, the two are blended in precisely calculated proportions, set by climate, by load, by the range of speeds the tire must endure. A winter tire and a summer tire are not merely a different tread design. They are a fundamentally different chemistry within. And that formula is the central secret Michelin will not reveal to anyone, ever. At the factory, the rubber is loaded into an industrial mixer known as a Banbury. It is an enormous machine, tall as a 2-story house, in which 2 massive rotors knead the mixture under high pressure. Into it goes carbon black, the technical carbon that gives tires their black color and increases the strength of the rubber 4-fold over the untreated material. Without it, a tire would fall apart within a few thousand miles. Into it goes silica, for grip on wet roads and for lower rolling resistance, which feeds directly into fuel economy. Sulfur and chemical accelerators, which set off the process of vulcanization. Antioxidants that shield the rubber from breaking down. Processing oils. As many as 30 separate compounds in a single batch, each in a precisely measured quantity. The temperature inside climbs to 320 degrees Fahrenheit. What emerges is a hot, sticky, sharply pungent mass. It is not yet a tire, but it is already the material from which a tire must inevitably take shape. The rubber compound is rolled into sheets of the required thickness, cut into blanks, and fed to the building drum. Here comes the most unexpected truth of all. A tire is not cast whole and not stamped from a single piece. It is assembled by hand, layer over layer, like a precise, many-layered cake. The first layer is the airtight inner liner, which holds the air sealed within. Over it come the layers of cord, fabric of steel or aramid threads, soaked through with rubber compound. The threads are laid at a strictly determined angle to the axis of rotation. It is the cord that holds the tire's shape under pressure. Without it, a tire would swell like a balloon at the very first inflation. The next layer is the belt. Steel threads crossed at roughly 20 degrees. The belt keeps the tire from expanding at speed and guards against punctures. And only after all of this comes the tread, the very pattern seen from the outside. Building a single tire by hand takes between 7 and 15 minutes. The assembled blank is sent into the mold, a massive steel structure weighing several tons, on whose inner surface the tread pattern, the size markings, and the direction of rotation are engraved to within hundredths of a millimeter. The mold closes. Through a membrane, hot steam is forced inside at a pressure of 220 pounds per square inch. The temperature reaches 340 degrees Fahrenheit. Vulcanization begins. The reaction discovered by accident by the American Charles Goodyear in 1839, when he dropped a mixture of rubber and sulfur onto a hot stove. The molecules of rubber stitch together through sulfur bridges, forming a single three-dimensional molecular network. The rubber turns from soft and tacky into something springy, tough, resistant to heat, to wear, and to ceaseless mechanical strain. The process takes between 10 and 15 minutes. After it, the tire can no longer be reworked or corrected. It is what it is, forever. After vulcanization, every tire, without exception, passes through a multi-stage quality control. First, a visual inspection under bright lamps. An operator hunts for surface flaws, blisters, cracks. Then an X-ray. The tire is scanned straight through. Inside, there must not be a single pocket of air, not a single shifted layer of cord, not a single fold in the liner. Then a test of uniformity. The tire is pressed with a force that imitates the real weight of a car and spun, while deviations in its shape are measured around the full circumference. The permitted deviation is fractions of a millimeter. And finally, balancing. The tire is spun up to the equivalent of 125 miles an hour, and any imbalance is measured to within grams. If even one parameter falls outside tolerance, the tire is scrapped. Not marked down, not sent for rework, scrapped. Because a tire that fails at 125 miles an hour is no longer a manufacturing defect. It is a catastrophe. Michelin builds tires for everything that moves, for bicycles and for the Airbus A380, for hatchbacks and for the Caterpillar 797 mining haul truck, which weighs 600 tons, a machine whose single tire stands taller than a grown man and costs 40,000 euros. For the cars of Formula One, where a tire lives 9 miles and costs as much as a used automobile. And for the rovers of NASA, where in place of a rubber air chamber, there is a metal mesh, because on Mars there is nothing to pump in. Michelin has developed the Uptis, a fully airless tire of reinforced polymers that cannot be punctured at all, in principle. It is already being tested on public roads in several countries. A company that began with a bicycle rim in 1891 is now seriously engineering tires for the transport of the next century, and it is doing so right now.
Every year in Dubai alone, over 1 million tons of asphalt are produced, and that number is constantly rising. Imagine it, tankers carrying millions of barrels of crude oil dock at Jebel Ali port. The oil is distilled in reactors at over 350 degrees Celsius, and a black, heavy residue is transformed into an advanced, elastic bitumen. Then come minerals from the mountains of Fujairah, processed at hundreds of tons per hour, blended in automated mixers, and transported in insulated trucks. This is the engineering magic that gives Dubai roads that neither melt in the sun nor crack in the night. Watch until the end, and you will discover the secret that makes this asphalt tougher than the desert itself. It all begins on the waters of the Persian Gulf, where giant tankers slowly cut through the surface, carrying millions of barrels of black gold, crude oil. They journey from Iraq, Saudi Arabia, and Kuwait. When a tanker docks at a port in the UAE, such as Jebel Ali, a process begins where men and machines work as a single organism. The oil is pumped into vast storage tanks, hidden within the industrial landscape, marking the start of its transformation. From there, it travels underground through a network of pipelines, like arteries leading to the heart of the refineries. In Jebel Ali or Abu Dhabi, it is met by a city of steel, reactors, distillation towers, and chrome columns. Here, the crude oil is heated to over 350 degrees Celsius to separate it into fractions. Lighter components, petrol, diesel, kerosene, vaporize first. The heaviest residues, the ones that refuse to vaporize even at these temperatures, are exactly what we need. This residue is fed into a vacuum distillation column, where the pressure is dropped to a minimum. What remains is bitumen, a black, viscous substance, the soul of asphalt. On its own, however, this bitumen is too thick and brittle for road construction, especially in a desert where the surface temperature can reach almost 50 degrees. So it must be modified. In special reactors, the bitumen is blended with polymer additives, plasticizers, stabilizers, and sometimes even crumb rubber. This is the bitumen modification process. The result is a material with high elasticity and resistance to UV radiation, one that won't soften under the sun or crack when the temperature plummets at night. In Dubai, a polymer-modified bitumen that meets the strict standards of the RTA, the Emirates Roads Agency, is used almost exclusively. Once the bitumen has completed its transformation, it begins the next stage of its journey, delivery to the asphalt mixing plants. The modified bitumen is transferred from the reactor into insulated storage tanks, which maintain its temperature at around 175 degrees. In this liquid state, it remains perfectly uniform. It is then pumped through high-pressure sealed pipelines to the nearby plant or loaded into road tankers with special thermal containers. These tankers are built with a double-skinned steel body and a thick insulating layer. The drivers undergo special training. They must maintain a steady speed and monitor temperature sensors in real time. If the temperature begins to drop, an onboard heating system activates. At the plant, for example, the DXB asphalt factory in Dubai Industrial City, the tanker connects to the intake system. At this moment, the bitumen is hot, thick, and has a distinctive smell. It is pumped into the plant's holding tanks, where it waits to be precisely dosed. From this point on, it is no longer just a material. It is a component in a formula, where the weight, viscosity, and temperature of every ingredient will determine the lifespan of the road it is destined to become. One of the largest plants is the DXB asphalt factory. Here, the bitumen is heated to 160 degrees and mixed with mineral aggregates, gabbro, basalt, and quartz sand. Gabbro is a dark volcanic rock quarried in the mountains of Fujairah. The rock is crushed into fractions smaller than 25 millimeters, screened through vibrating sieves, dried in huge rotating drums, and then fed into the mixer. Inside, the bitumen and aggregates are combined into a hot, uniform mass known as hot mix asphalt. The temperature of the mix is 160 degrees. It must be perfectly homogeneous, with a precise ratio of components. After mixing, the asphalt is transferred to insulated silos where it can be stored for no more than 6 hours. From there, it is loaded into insulated trucks for the final journey. On site, the asphalt is laid by paving machines and then compacted by rollers, first vibratory, then static. In the desert, achieving maximum density is critical to prevent the ingress of sand and water. Compaction is done in multiple passes, and the temperature of the asphalt must not drop below 120 degrees Celsius during the process. If it does, the mix loses its workability and the road's integrity is compromised. A key feature of Dubai's highways is their multi-layered structure. The base course is made of a coarse-grain asphalt. The middle, or binder course, uses the modified bitumen and acts as a shock absorber. The top, or wearing course, is a thin layer with a high polymer content to provide grip and durability. In some cases, reflective minerals are added to reduce heat absorption. In the desert, it's not just the heat. Dust, wind, and humidity changes all have an impact. Asphalt plants in Dubai are equipped with advanced air filtration systems, and the mixes themselves are tested for resistance to abrasive wear and thermal expansion. In the RTA's laboratories, every batch of asphalt is checked for viscosity, density, and thermal stability. If it fails to meet the standards, the entire batch is rejected. This journey, from oil tanker to finished highway, takes several days, but involves dozens of quality control stages. And it is because of this meticulous process that Dubai's roads can withstand the daily punishment from thousands of vehicles without melting under the desert sun. Over 1 million tons of asphalt are produced in Dubai annually, and this figure is growing with the city's infrastructure. The DXB asphalt factory alone has a capacity of 240 tons per hour, allowing it to supply major projects without interruption. For comparison, an average plant in Europe produces around 150 tons per hour. Interestingly, asphalt is the most recycled material in the USA, with over 99% of old pavement being reused. Dubai is also actively adopting recycling, especially during the reconstruction of older highways.
Every minute, thousands of kilometers of old cable vanish from our world. They're torn from the walls of houses, factories, and machines. And all of this scrap is reborn as pure copper, a hidden treasure more vital than gold for our modern world. Imagine it. Coils of wire that yesterday lay forgotten in a scrapyard are today melting in a furnace at over 1100 degrees Celsius, hotter than a volcano. But the most remarkable part? Copper can be reborn infinitely. So the wire that lit your room 20 years ago might be powering an electric car tomorrow. And stay with me, because at the end, I'll reveal a secret this metal's been hiding, and it will change the way you see copper forever.
Every wire you see around you, from old charging cables to industrial coils, has a story. It was part of something, conducting power, carrying signals, bringing things to life. But time moves on, technology is upgraded, machinery replaced, and these cables become waste. But this is where their second life begins. The scrap is gathered from everywhere: homes, offices, demolition sites, even old vehicles. A vast, unseen logistics network of lorries, containers, and depots comes to life. It's a treasure hunt, but the prize is metal and plastic, twisted together in a tangled mess. The first stop, the factory floor. Here, the cables pass through the hands of experienced operators who aren't just sorting, they're industrial archaeologists.
This is a critical stage. The quality of the final product depends entirely on the accuracy of this sort. Mix the wrong types of metal, and you compromise the purity of the copper, complicating every process that follows. The team here uses a variety of tools: shears, pliers, and specialized stripping machines. The work is fast, but precise. Every coil is unwound and separated into fractions: bare bright wire, plastic-sheathed cables, thick industrial lines, copper, and aluminum. The integrity of the copper must be preserved. It's the heart of the operation. Even the smell on the workshop floor, a mix of old plastic, metal, and dust, tells you that this is where the transformation begins.
The coils are separated, the wires untangled, but the real alchemy is yet to come. What were once kilometers of cable are now fed into the heart of the plant. Some call it a shredder, others a dragon with steel teeth. The principle is the same. This beast devours everything. Cable fragments are loaded into a vast hopper. Inside, shafts armed with razor-sharp blades don't cut, they chew. Copper, aluminum, plastic, it's all torn, crushed, and ripped into small pieces. From there, the shredded mix enters a machine where physics takes over. A symphony of centrifugal forces, vibrations, air currents, and magnets goes to work. The light plastic is blown away into one stream. The heavy copper falls into another.
The air is thick with dust. The hum of machinery is constant. Operators watch the metrics on their screens intently. This isn't just noise, it's the sound of rebirth. Just like the alchemists of old who sought to turn lead into gold, there are formulas at work here too. But instead of elixirs, there are weighing systems, calibration tools, and purification technologies. Because in the modern world, magic is just well-engineered technology.
Inside the furnace, fluxes are gradually added, special agents that bind to impurities like oxides, dirt, and residual insulation. They float to the surface, forming a dark crust of slag. This is skimmed off by hand with long ladles, in a heat you can feel through a protective suit. It is one of the most dangerous jobs in the plant, but also one of the most majestic. Here, people witness the purification of old metal with their own eyes. They watch rusty scrap transform into a molten lake that glows like the sun. Even the sound is different here, a deep, guttural, threatening hum. It's the sound of copper saying, "I am returning."
Once the molten copper is cast into solid ingots, it still doesn't know what it will become. Its future lies in the hands of engineers and the rolling mill. The ingots are transported to the mill, reheated, and then forced through a series of giant rollers, like flattening a piece of red-hot dough. With each pass, it gets thinner. With each pass, smoother. This is how copper sheet is formed, or the feedstock for wire. Next comes drawing. This is where the copper is pulled through a series of progressively smaller holes, or dies. It stretches, thins out, but never breaks. Each die brings new precision, measured in microns. All of this to create a thin, flexible, gleaming copper wire.
Sometimes, this wire will be insulated and buried in the walls of a new house. The average home requires around 200 kilograms of it. Sometimes, it will be wound into the motor of an electric vehicle. And sometimes, it becomes the delicate coil in a pair of headphones, carrying music from one heart to another. Every minute, over 17 tons of copper scrap are recycled globally. It's a metal that can be repurposed almost infinitely with no loss of quality. It lives, works, melts, and begins again.
This ship doesn't go around the ice, it goes straight through it. 10 feet of frozen ocean, and it doesn't care. I'm standing in a shipyard where they're assembling the hull of a nuclear-powered icebreaker, and in front of me is a giant steel skeleton that will soon be working where temperatures drop below -50, and ice pressure can crush any ordinary structure like a tin can. You know, I usually go look at things you can touch without risking your cheek freezing to them. But today, I slightly overestimated my ambitions. And right now, I'm going to show you how a machine is born that makes even the Arctic itself back down. The first thing that hits you at the shipyard isn't the size, though the future vessel stretches over 500 feet long, and individual hull plates run several inches thick. What stuns you is the steel itself. They don't use ordinary rolled stock here. An icebreaker hull demands special steel grades that stay flexible even in brutal cold. Regular steel turns brittle in the freeze. Strike it, and it'll crack like glass. This stuff, though, has to take impacts from ice fields and not fail. The engineers explain it simply. The hull needs to give a little, flex slightly under pressure. Otherwise, the Arctic will just snap it. Massive steel plates arrive at the yard already rough processed from the rolling mill. Each plate weighs dozens of tons, and when the crane lifts one into the air, It looks like a chunk of an apartment building somebody randomly decided to relocate. But the icebreaker's shape doesn't appear all at once. First, these plates pass through giant rollers that slowly, with enormous force, bend them to the required angle, giving the metal that crucial curve without which the hull can't push ice aside. In front of me, steel rollers, each as thick as a decent tree trunk, stacked one above the other. Between them, they slowly feed a flat steel sheet, heavy, rigid, seemingly completely inflexible at first glance. The operator gives the command, and the mechanism starts moving. The rollers rotate at low speed, but with massive force. The sheet gradually gets pulled inside, and at some point, you can see it start to change shape. First, it's a barely noticeable bend. Then the radius increases, and the metal's no longer flat. It curves smoothly, as if obeying someone's will. The sound here is unique, a muffled pressure, grinding, and a slight crackling, like the metal reluctantly gives in. I'm standing nearby, and I hear how the steel literally groans under the load, a sound like you're pressing on something really stubborn, and it's grudgingly surrendering. They might roll the sheet several times, adjusting the roller positions each time, until they get the exact angle or curvature. And there in front of you is no longer just a piece of steel, but part of a future hull that perfectly matches its contours. By the way, if you're into stories about how seriously complex and powerful machines are built, hit subscribe so you don't miss the next episode. Now, let's keep going. Next comes the assembly of sections, and this looks like a giant construction set, except each block weighs as much as a small locomotive. Individual hull blocks are assembled in the shop. These can be sections 60 or even 100 feet long. Inside each block, there are already bulkheads, cable routes, and even foundations for future decks. In other words, the hull isn't built from scratch in one spot. It's assembled in pieces, like a puzzle, just really heavy and really hot to produce. I walk into the shop and there are finished sections already standing there. These aren't just sheets of metal, they're entire fragments of the future ship. Inside each one, you can see passageways, openings for cables, spots where pipes, wires, and entire life support systems will run later. Then these blocks are transported to the slipway and joined together. The cranes move in. They lift the section into the air slowly, smoothly, no sudden movements, and transport it to the slipway. There, they carefully lower it and fit it against the already installed parts of the hull. At this moment, you literally see separate pieces starting to come together as one. The future icebreaker takes shape right before your eyes. Welding is a whole different story. You can't just run a bead and go grab coffee. Every joint goes through multiple levels of inspection. First, the welder lays the main seam. Then they check it with ultrasound to make sure there are no voids or cracks inside. If something's off, they cut it out and do it over. I watched them redo one seam 3 times, and nobody even got stressed. That's standard practice here, because the price of a mistake in the Arctic isn't just a breakdown, it's a potential catastrophe. And that's how it goes. Every seam, every joint, along the entire length of the hull. We should talk about the hull shape. An icebreaker doesn't just have a strong bow, it's specifically designed to climb up onto the ice and break it with its own weight. That's why the bow section has that distinctive slope, and they reinforce it with extra layers of steel. In some spots, the thickness multiplies several times over, and inside they add ribs that distribute the load along the entire length of the ship. While I'm walking around here, there's constant movement everywhere. Cranes, platforms, people in hard hats, for whom all this is just another workday. Though honestly, when they're moving a whole section weighing dozens of tons right over your head, you kind of rethink the word ordinary. One of the engineers jokes that the scariest thing here isn't the cold or the metal, it's when someone forgets their lunch in the shop, because finding it among all this scale is practically impossible. When all the sections are connected, the hull starts taking its final shape. Its length becomes physically tangible. You walk alongside and catch yourself thinking it's like strolling past an apartment building, only horizontal. The height of the hull is impressive too, several levels that will eventually become decks, engine rooms, and crew quarters. After that comes surface treatment. The metal gets cleaned, anti-corrosion coatings applied, painted with special compounds that reduce water friction and protect the hull from salt and ice. It looks like cosmetics for a giant, but in reality, this coating determines how many years the ship can operate without major repairs. And that's not an exaggeration. Arctic saltwater and constant ice friction can destroy unprotected metal in just a few seasons. Modern nuclear icebreakers can ram through ice up to 9 feet thick while underway, and the newest designs are rated for ice up to nearly 15 feet thick. Power, that's a whole other story. Heavy icebreakers can pump out over 75,000 horsepower, and without that, they simply wouldn't budge the ice. I'm standing here staring at this hull, and it hits me. This isn't a finished vessel yet. There's no reactor in here, no propellers, no control systems. But even now, the main thing is crystal clear. This is a structure built to battle the elements, where every millimeter of steel serves a purpose. And when she heads out to sea, she won't just sail. She'll carve a path where other ships wouldn't even dare to go. I'm gonna stick around here a bit longer. Listen to that metal grinding. Watch these machines come to life. Then head out to prep your next adventure. Because after something like this, you want to find something just as massive, just as complex, just as beautifully insane. When you stand next to a structure like this, you start seeing what humans can actually build differently. Not on a computer, not in theory, but right here, with hands, steel, and fire. And I think I've already got a couple ideas where to head next. So stick around, it's gonna be good. Hey folks, on this channel, we go where cameras usually aren't allowed. If you dig these behind-the-scenes deep dives, hit subscribe and smash that bell so you don't miss new episodes. Today, I'm showing you how they make those manhole covers we walk over every day without even thinking about it. Turns out, it's way more interesting than you'd expect. I'm standing in the middle of a foundry floor, and it's about 110 degrees Fahrenheit in here. Sweat's pouring down like crazy, my glasses are fogged up, and the air's thick with the smell of molten metal and coal. Black coke dust crunches under my feet, and in the distance, a furnace pulses with a crimson glow. Come with me. I'll show you everything from the first ladle of molten metal to the finished cover. I'm met by the foundry master, a man in his 60s, with hands scarred by thousands of sparks. He's worked here for 38 years and says he's seen manhole covers cast for every major city. His creations lie everywhere beneath our feet. It all starts with scrap metal, massive piles of old cast iron, engine fragments, pipes, radiators, even old manhole covers that have served their time. Cast iron can be remelted an infinite number of times without losing its properties. It's one of the few things humanity gets right. Metal recycling here is 100%. The scrap is sorted by composition, weighed, and crane-loaded into a cupola furnace, a massive furnace about 30 feet tall, resembling a medieval tower. Inside, layers of coke and cast iron scrap alternate. The coke burns at around 2,700 degrees Fahrenheit, and at that temperature, the cast iron melts, transforming into a glowing orange liquid that flows to the bottom of the furnace. I stepped closer, as close as safety regulations would allow, and felt the skin on my face instantly tighten from the heat. At 15 feet, the temperature is so intense you want to back away. But the workers stand right by the furnace in special reflective suits, looking like astronauts. When the iron's melted, they release it into a ladle, a massive metal scoop that holds about 2,000 pounds. The ladle hangs from a crane and glides smoothly over rows of sand molds laid out across the factory floor. Each mold is the negative of a future manhole cover, an imprint of every detail, every letter, every ridge. The molds are made from special sand mixed with clay and water. A master craftsman showed me how it works. They take a wooden or metal model of the cover, press it into the sand, then carefully lift it out. What's left is a perfect impression. Every line, every curve, copied with accuracy down to a few thousandths of an inch. They place the second half of the mold on top, and you've got a cavity ready for the metal. A single model can produce thousands of impressions before it needs replacing. The coolest part? The text on the manhole covers. Each one shows the name of the city or water department. The letters are made separately. Small wooden or plastic type pieces get pressed into the sand in just the right spots. When the iron hardens, the text pops out. That's why all the words on manhole covers are mirror images of what was in the mold. Now comes the most spectacular part, the pour. Two workers in silver suits tilt the ladle, and out flows a stream of molten iron. It glows so bright you can't look at it without protective glasses. Your eyes start watering after a couple seconds. The metal hits 2,600 degrees Fahrenheit. The iron fills the mold in 5 seconds flat. But you've got to pour carefully. Too fast and the metal traps air, creating pockets inside the manhole. That cover will be weak and could crack under the weight of a truck. Too slow and the metal starts hardening on the way down, filling the mold unevenly. An experienced foundry worker feels the right speed instinctively. It's a skill that takes years to develop. The sand mold starts smoking after the pour, moisture from the sand and clay evaporating. The smoke is thick, gray, smells like scorched earth. Ventilation runs full blast, but visibility in the shop still drops to about 50 feet. Then comes the waiting. The iron needs to cool, but not too fast. Slow cooling is what gives the metal its proper structure and strength. Open the mold too early and the manhole cover warps from the sudden temperature shift. Scrap. The sweet spot is 18 hours. During that time, temperature gradually drops from about 2,550 degrees Fahrenheit down to around 210. The molds sit in rows on the shop floor, radiating steady, dry heat, like a radiator. Next day, workers smash the sand molds with hammers, and out come the manholes, still hot, dark gray, coated in sand residue. They look rough, messy, nothing like those smooth covers lying in the streets. Each manhole cover weighs between 66 and 132 pounds, depending on the size. A standard cover for city sewers runs about 24 inches in diameter and weighs roughly 95 pounds. I tried lifting one, barely got it off the ground. The foreman laughed. He's been lifting 10 of these a day for nearly 40 years. Next, the covers go to processing. A special machine with rotating steel cable brushes cleans off any remaining sand. Sparks fly in every direction. The metal gradually takes on a clean gray color. Pneumatic hammers knock off the flash, leftover metal that solidified in the wrong places. The most critical step is machining the seating surface. The cover's edge has to fit the frame perfectly or it'll rattle under traffic. Tolerance, about 1/10 of an inch. A lathe turns the edge to perfect roundness, and every cover has small holes, 2 or 4. They're for the special hook utility workers use to pull covers out. Without them, lifting a 95-pound cast iron lid off a flat surface is basically impossible. The quality control here is amazing. An inspector just taps each manhole cover with a small hammer and listens to the sound. If the sound is clean and ringing, the cover's good. If it's dull or has an off tone, there's a crack or void inside somewhere, and that cover gets scrapped. He checks 200 covers a day and says he's never wrong. I ask why manhole covers are round. Seems like square ones would be simpler to make. The foreman explained something brilliantly simple. A round cover can never fall through its own hole. A square one can be turned diagonally and drop right down. A circle is always bigger than its opening, no matter how you turn it. That's why manhole covers are round all over the world. It's not tradition, it's math. Another detail, the pattern on the surface. Those grooved lines, stars, or grid patterns aren't there for looks. It's an anti-slip coating. Smooth cast iron in the rain is slippery as ice. With the ridges, traction is way better. I stood on one cover right there in the shop, held firm even in work boots with smooth soles. Finished manhole covers get stacked 10 to a pile and shipped out to cities. Each stack weighs around 900 to 1,100 pounds, so they only load them with a crane. One factory produces 50,000 covers a year. Sounds like a lot, but a major city alone might have over 300,000 manholes. That means every few years, every single cover needs replacing. Why so often? The covers break down. Sand and salt in winter, vibrations from trucks, temperature swings from -22 to 130 Fahrenheit on the asphalt in summer. Cast iron is tough, but it's not forever. Average lifespan is 30 years, and in high traffic areas, just 5. There are covers for steam tunnels, telephone, electrical, water mains. Each type differs slightly in size and thickness. The thickest ones are for highways, where they get run over by trucks weighing 36 tons. There, the wall thickness hits 2 inches. The factory museum holds old manhole covers, the oldest one from 1892. Over 130 years old, and it's still intact. The cast iron's dark, smooth from time, but not a single crack. There are covers from different countries: France, Japan, England. The Japanese ones are the most beautiful, engraved with cherry blossoms or mountains. Over there, manhole covers are art. When I left the factory, there was an ordinary manhole cover lying in the street. I stopped, crouched down, ran my hand across its surface. Now, I see it differently. This isn't just a lid. This is 2,700 degrees of heat, 18 hours of waiting, precision down to 1/10 of an inch, workers' hands in silver suits, and the ring of an inspector's hammer. Every manhole cover beneath our feet has been through this journey and will last another 30 years, bearing thousands of tons, millions of footsteps, rain, snow, and heat.
Every second, the world produces 28 million tons of stainless steel. And behind the shine of every spoon, every faucet, every surgical instrument stands one metal: chromium. But here's what's mind-blowing. Chromium melts at 3,375 degrees Fahrenheit, and in the electric arc furnaces that produce it, temperatures hit 5,000 degrees, hotter than the surface of the sun. A single furnace consumes 4,000 kilowatt hours of electricity per ton of alloy. That's as much as the average apartment uses in 4 months. 80% of all chromium in the world goes into making stainless steel. But where does this metal come from? Why are 99% of the world's chromite reserves concentrated in just a handful of countries? And what happens in that hellish zone beneath the electrodes, where ore transforms into molten ferrochrome? Stick around. You'll discover how black rock gives birth to the metal that makes steel immortal. Picture a massive electric arc furnace as tall as a 3-story building. 3 carbon electrodes up to 6 feet across plunge into a churning mass of glowing ore, coke, and fluxes. Between the electrode tips and the furnace floor, electric arcs crack and snap. Temperatures in this zone hit 5,000 degrees Fahrenheit. That's hotter than the surface of the sun. The air above the furnace shimmers with heat. Clouds of smoke and gas blast out from beneath the half-closed roof. Inside, real alchemy unfolds. Chromium ore mixed with coke melts down, oxygen escapes as carbon monoxide, and molten ferrochrome, an alloy of chromium and iron, flows to the bottom. This is a submerged arc furnace, and this is where most of the world's ferrochrome is born. The process runs non-stop. Fresh batches of ore and coke pour in from the top, molten metal and slag tap out from the bottom. A single furnace like this can pack 25 to 45 megavolt amperes of power. This is a monstrous amount of energy. An entire power plant runs just to melt the ore. When enough molten ferrochrome accumulates in the furnace, workers punch open the tap hole, a special opening in the furnace's side. And then the mesmerizing spectacle begins. A stream of white-hot metal and slag bursts out, flowing down a channel into an enormous ladle. The stream's temperature around 3,000 degrees Fahrenheit. The metal glows bright orange, almost white. The heat radiating from it is so intense that workers stand dozens of yards away, protected by special screens and fireproof clothing. Slag floats to the top and is drained off separately. The ferrochrome cools in massive molds, transforming into solid ingots weighing hundreds of pounds. These ingots are later crushed into pieces of the right size for sale to steel mills. But the process of obtaining ferrochrome, that's only the middle of the journey. It all begins with ore, mined deep in the earth. Chromite, the only industrial ore of chromium. It's a dark brown, almost black mineral with a metallic luster. The chemical formula? Iron and chromium oxide. Pure chromite contains 68% chromium oxide and 32% iron oxide. But in nature, perfect ores like that barely exist. Real deposits contain anywhere from 40 to 50% chromium oxide. Chromite forms in igneous rocks, in massive molten masses rising up from the Earth's mantle. The largest deposits are found in South Africa, Kazakhstan, India, and Turkey. These four countries account for roughly 80% of global production. South Africa is the absolute leader. Its deposits in the Bushveld complex contain 200 million tons of chromite. We're talking ore seams stretching for hundreds of miles and plunging thousands of feet deep. Kazakhstan holds reserves of 230 million tons. India? 54 million tons. Now, the story. French chemist Louis-Nicolas Vauquelin discovered chromium in 1797. He isolated it from croquat, a bright red lead chromate mineral. The mineral's vivid color inspired Vauquelin to name the metal after the Greek word chromos, color. Because chromium compounds produce stunning colors, greens, yellows, oranges, reds. A year later, in 1798, Vauquelin isolated pure chromium by reducing the oxide with carbon. Iron with added chromium was first produced in the mid-1800s, and the first use of chromium as an alloying element in steel production happened in France in the 1860s. The revolution came in 1893 when Henri Moissan smelted chromium ore with carbon in an electric furnace and produced ferrochrome. This became the foundation of the modern industrial method, which has evolved but at its core remained the same. Chromite gets mined both through open-pit operations and underground mines. Open-pit mining gets used when the ore sits close to the surface. Giant excavators strip away the soil and overburden, exposing the chromite layers. Then they blast the ore, load it into haul trucks with capacities up to 300 tons, and transport it to the processing plant. Underground mining gets deployed for deep deposits. Tunnels get driven hundreds of feet down, sometimes miles. They blast the ore, load it into mine cars, and haul it to the surface. The extracted ore? It's not pure chromite yet. It comes mixed with waste rock and other minerals. That's why the ore needs processing. First, they crush it in massive jaw crushers. Chunks the size of a car get reduced to fist-sized pieces. Then they grind it in ball mills down to the size of sand or even dust. After that comes separation, isolating the chromite from the waste rock. The main method for enriching chromite is gravity separation. Chromite is heavier than waste rock. Its density is 4.5 to 4.8 grams per cubic centimeter, while the rock is 2 to 3 grams. The crushed ore is mixed with water, creating a slurry. The slurry passes through jig machines, concentrating tables, spiral classifiers, centrifugal separators. Under the force of gravity, the heavier chromite grains settle faster, while the lighter waste rock is carried away by the water flow. Magnetic separation is also used. Chromite is weakly magnetic, but modern high-intensity magnetic separators can attract it and separate it from non-magnetic impurities. After enrichment, they obtain chromite concentrate containing 46% or more chromium oxide. This is ready-made raw material for metallurgy. The concentrate is dewatered, dried, and sent to ferroalloy plants. Lump ore is needed for ferrochrome production. Fine powder doesn't melt well in the furnace. So the fine particles get agglomerated, sintered into large chunks. They mix the concentrate with fluxes and coke breeze, moisten it, and form pellets. Then they heat it to about 2,200 degrees Fahrenheit. The pellets sinter into solid lumps a couple inches across. Now the ore is ready for smelting. At the ferroalloy plant, chromite concentrate gets mixed with coke and fluxes in specific proportions. Coke is the carbon source that'll reduce the oxides down to metal. Fluxes, quartzite, dolomite, limestone, are needed to form slag with the right composition and melting point. The charge, the mix of ore, coke, and fluxes, gets loaded into the electric arc furnace from the top through special hoppers. Loading happens continuously or in batches, depending on the furnace type. The electrodes, massive carbon cylinders, are submerged in the charge layer. When they switch on the current, an electric arc forms between the electrodes and the material beneath them. Temperature in the arc zone? 5,000 degrees Fahrenheit and higher. That's enough to melt any ore. Inside the furnace, complex chemical reactions take place. Carbon from the coke combines with oxygen from chromium and iron oxides, forming carbon monoxide that rises upward. Chromium and iron are reduced to their metallic state and fuse together, forming ferrochrome. Some of the carbon dissolves into the metal, producing high carbon ferrochrome with a carbon content of 4 to 8%. Typical South African ferrochrome contains 52 to 54% chromium, 6 to 7% carbon, and 2 to 4% silicon. Ores from Zimbabwe with a higher chromium to iron ratio yield a product with 63 to 67% chromium. The molten ferrochrome and slag accumulate in the lower part of the furnace, the hearth. When enough metal has built up, they open the tap hole. Metal and slag flow into a ladle. The slag floats to the top and is poured off or skimmed away. The metal is poured into molds or cooled in special forms. Once solidified, the massive ingots are broken down by hydraulic presses or hammers into pieces of the required size. Ferrochrome production is incredibly energy intensive. A single ton of high-carbon ferrochrome burns through 2,000 to 4,000 kilowatt-hours of electricity. That's why ferrochrome plants get built in countries with cheap power, often right next to hydroelectric dams. Chromium recovery from ore hits about 90% under good conditions. The remaining 10%, it goes into slag. Slag isn't just waste. Metal particles get extracted from it using mineral processing methods, and what's left goes into construction. Ferrochrome isn't the end product. It gets shipped to steel mills where it's added to molten steel for alloying. Chromium gives steel corrosion resistance, hardness, heat resistance. Stainless steel contains 10 to 20% chromium. Average, 18%. It's chromium that forms a thin, invisible oxide film on the steel's surface, protecting the metal from rust. And so, having traveled from black rock in the Earth's depths, through quarry explosions, crushing and processing, through the inferno of an electric arc furnace at 5,000 degrees Fahrenheit, ferrochrome is born. An alloy that gives steel eternal life and shine, resistant to time and corrosion.
The metal hiding in every muffler. Every minute, 130 cars roll off production lines around the world, and each one hides between 2 and 7 grams of palladium, a metal more expensive than gold and platinum, so rare that all the world's reserves could fit in a single room. But without it, every modern city would choke. Palladium scrubs poisonous substances from exhaust gases. 85% of all palladium mined goes into automotive catalysts. Platinum's little brother has become the critically important metal of the 21st century. How do you extract a silvery metal worth $40,000 per kilogram from ore mined a kilometer underground in Siberia? You'll learn why palladium was named after an asteroid, how it transforms poison into harmless gas, and why its reserves could run out in 20 years. Watch until the end. The finale reveals what stands behind the clean air in our cities. This is the story of the metal the future of the automotive industry depends on. The story of palladium began in 1803 in London. British chemist William Wollaston was studying platinum ore from South America. He dissolved the ore in aqua regia, a mix of hydrochloric and nitric acids, the only solvent capable of dissolving platinum. From the solution, he extracted platinum, but noticed some impurities remained in the solution. Wollaston performed a series of chemical operations and isolated a new metal, silvery white, similar to platinum, but lighter. He named it palladium after the asteroid Pallas discovered a year earlier. Coincidence or not, Pallas in Greek mythology is the goddess of wisdom. Palladium turned out to be an amazing metal. It could absorb hydrogen in volumes 900 times its own. Picture this. A cube of palladium 1 centimeter by 1 centimeter can soak up nearly a liter of hydrogen. The metal swells up like a sponge. But the key property was discovered later: catalytic activity. Palladium speeds up chemical reactions without taking part in them. For a long time, palladium remained a laboratory curiosity. It was used in jewelry. White gold often contains palladium. In dentistry, for dental crowns. In electronics, palladium contacts don't oxidize, but consumption was minimal, just a few tons a year for the entire world. Everything changed in the 1970s, when environmental regulations suddenly got much stricter. Car exhaust contains carbon monoxide, nitrogen oxides, and unburned hydrocarbons, all of them toxins. Cities were choking in smog. A solution was needed, and one was found: the catalytic converter, a device that transforms poisonous gases into harmless ones. Inside a stainless steel casing, a ceramic honeycomb structure coated with an ultra-thin layer of platinum, palladium, and rhodium. Hot exhaust gases pass through the honeycomb. On the surface of the platinum group metals, reactions occur. Carbon monoxide converts to carbon dioxide, nitrogen oxides to harmless nitrogen, hydrocarbons burn off. The converter cuts emissions by 95%. But there's a price. Each converter contains precious metals. Palladium turned out to be perfect for the job. It's cheaper than platinum, but better at oxidizing hydrocarbons. With environmental regulations rolling out in Europe and the US, demand for palladium exploded. Production jumped from just a few tons a year to 300 tons. The price rocketed from $500 per troy ounce in the 90s to $3,000 in 2020. Palladium became more expensive than gold and platinum. Catalytic converter thefts started spreading. Thieves cut the converter out from under a car in 5 minutes and sell it for $200 to $500. The palladium inside is worth even more. The problem is, palladium is one of the rarest elements out there. In the Earth's crust, it makes up 6 parts per 10 billion. That's 30 times rarer than gold. Worldwide, only about 200 tons of palladium get mined each year. For comparison, 3,000 tons of gold, 20 million tons of copper. Palladium doesn't form its own deposits. It shows up as an impurity in nickel and platinum ores. Main sources: Russia and South Africa. 70% of the world's palladium comes from Russia, mostly from the Norilsk mining complex in Siberia. Norilsk is a city above the Arctic Circle, one of the most northern cities on the planet. Winter temperatures drop to -50. But underground lies a unique deposit of copper-nickel ores containing platinum group metals. The ore is mined in shafts up to nearly a mile deep. They blast the rock, load it onto dump trucks, bring it to the surface. The ore contains about 1% nickel, fractions of a percent copper, and just a few grams per ton of platinum group metals: platinum, palladium, rhodium, iridium. But the volumes are massive. 20 million tons of ore per year. The ore is crushed, ground into fine powder, enriched by flotation. The process is similar to lead ore enrichment. They get a concentrate containing 10 to 15% nickel and copper and elevated levels of precious metals. The concentrate is smelted in massive furnaces. This produces matte, an alloy of nickel, copper, and iron sulfides. All the platinum group metals are concentrated in the matte. Feinstein gets shipped to a metallurgical plant. There, it's converted, blasted with oxygen at temperatures hitting 1200 degrees. Iron and sulfur oxidize and get stripped away. What you're left with is crude nickel-copper alloy containing the platinum group metals. This alloy gets dissolved in sulfuric acid. Nickel and copper go into solution. Precious metals stay behind in the residue, what they call slimes. These slimes contain up to several percent platinum group metals. It's not polyeum yet, but it's highly concentrated feedstock. The slimes get dissolved in aqua regia, that same acid mixture Wollaston used. All the platinum group metals go into solution. Now the ultra-precise separation chemistry begins. From the solution, they sequentially precipitate platinum, palladium, rhodium, iridium, ruthenium, osmium. Each metal precipitates at a specific pH with specific reagents. The process takes weeks. The result, precipitates of various palladium salts. These salts get calcined at high temperature. You get sponge palladium, a gray porous powder. It's almost pure metal, but not yet a marketable product. Spongy palladium gets melted down in an induction furnace under argon or vacuum. Palladium can't oxidize. The molten metal pours into ingots. You end up with small bars weighing anywhere from a few ounces to 2 pounds. Silvery white with a slight steel tint. Palladium's softer than platinum, so you can roll it, forge it, draw it into wire. Palladium's melting point? 2,828 degrees Fahrenheit, lower than platinum. Density? About 0.43 pounds per cubic inch, lighter than platinum, but still a seriously heavy metal. Palladium doesn't tarnish in air, doesn't react with most acids, only dissolves in aqua regia and hot concentrated nitric acid, corrosion resistant. But here's the key property, catalytic activity. Palladium speeds up oxidation and reduction reactions. On its surface, gas molecules get adsorbed, activated, react with each other. That's exactly what makes palladium irreplaceable in automotive catalytic converters. The entire journey from ore to metal takes months and involves dozens of processing steps. How does a palladium car catalytic converter work? The device looks like a metal canister installed in the exhaust system right after the engine. Inside is a ceramic honeycomb structure, like an actual beehive. Thousands of channels in this structure. Total surface area, several square feet. The surface is coated with aluminum oxide, a thin porous layer that multiplies the area hundreds of times over. On top of that layer, palladium, platinum, and rhodium, total weight between 2 and 7 grams. Palladium and platinum oxidize carbon monoxide and hydrocarbons into carbon dioxide and water. Rhodium reduces nitrogen oxides back to nitrogen. Exhaust gases at temperatures between 750 and 1470 degrees Fahrenheit flow through the honeycomb. Reactions happen on the metal surfaces. What comes out? Almost pure nitrogen, carbon dioxide, and water vapor. Efficiency? Up to 98%. Without a catalytic converter, a car dumps dozens of grams of toxins into the atmosphere every mile. With one, fractions of a gram. A modern passenger car contains 3 to 5 grams of palladium. A truck or SUV, up to 7 grams. Here's the problem. Palladium reserves are limited and running out. There aren't many accessible deposits left. At current extraction rates, proven reserves will last 20 to 30 years. Prices are climbing. The shortage is getting worse. Automakers are hunting for alternatives to palladium. They're partially switching to platinum. It's also a catalyst, but more expensive and less effective for gasoline engines. For diesels, platinum works better. Recycling palladium from spent catalytic converters is ramping up. Old converters get collected, crushed, and the platinum group metals extracted. Recycling provides up to 30% of palladium supply. It helps, but it doesn't fully solve the problem. Demand keeps growing. Around 90 million cars roll off production lines worldwide every year. Electric vehicles don't use catalytic converters, but their share of the market is still small. Hybrids still need palladium. The palladium market's unstable. Prices swing from $2,000 to $3,000 per troy ounce. Palladium has become a strategic metal. The entire automotive industry and urban air quality depend on it. And just like that, journeying from ore a mile deep beneath the Siberian permafrost, through months of chemical operations and ultra-precise separation, palladium emerges into the world, platinum's younger brother, now the champion of clean air. A few grams of silvery metal hidden inside every muffler, saving millions of lives annually. The rarest of elements, 30 times scarcer on Earth than gold, has become critically vital to modern civilization. It's the paradox of technological progress. The more we care about ecology, the more we depend on rare metals. Every time you start your car, remember, beneath the chassis works a palladium catalyst, transforming poisons into harmless gases. A metal worth $40,000 per kilogram makes city air breathable. From the asteroid palace to automotive catalysts, 220 years of history for a metal that found its calling in the fight for ecology. But reserves are dwindling, prices are climbing, and palladium's future looks uncertain. Perhaps in 20 years, humanity will discover a replacement, or learn to recycle more efficiently, or switch to electric vehicles. But for now, palladium remains the thin silvery thread connecting a billion automobiles to clean air, the metal without which megacities would suffocate, the hidden hero of the environmental revolution, tucked away in every muffler.
Every hour, somewhere in the world, a metal component weighing over 50 tons is manufactured, and a single microscopic error in its machining can trigger a multi-million-dollar catastrophe. Picture a crankshaft as long as a bus that must survive a billion cycles of explosive force, or a cylinder block where a deviation the thickness of a human hair means scrapping a multi-ton giant entirely. But here's the mystery. How do engineers achieve micron-level precision when machining parts heavier than a tank? What happens in that secret quality control room where a computer measures thousands of points and can shut down the entire process? And most importantly, stick around until the end, because I'm going to show you the final operation where one tiny slip turns months of work into scrap metal. This is manufacturing where every thousandth of an inch is a matter of engine life and death. Ready to look inside? The first thing that hits you at this facility? The sheer scale. Forget your average car engine. Take this cylinder block, for example. It can weigh dozens of tons. This isn't just a casting, it's a complex, multi-layered masterpiece of foundry art, requiring special grades of steel or cast iron that can withstand unbelievable loads, temperatures, and pressures. And here's the crankshaft. In big engines, this thing can be as long as a small bus and weigh just as much. This component is probably the most critical. It has to endure the explosive force of fuel combustion, converting it into rotational motion. The blanks often arrive as massive forgings where every pound of metal already has its own story. The process starts with incoming inspection. Specialists check the chemical composition, scan for internal defects using ultrasound and X-ray equipment. Because even the tiniest hidden flaw in a part this massive could lead to catastrophe during operation. It's like a health checkup for a steel giant. Only after a thorough inspection does the blank get clearance to enter the machine shop. Moving these blanks takes serious muscle. That's why the shop is equipped with powerful overhead cranes capable of lifting loads that outweigh most ordinary machine tools. Mounting the part onto the machining center is a precision operation requiring coordination and experience. This is the first step in turning metal into might. Now we move to the heart of the shop, the cylinder block machining zone. This is where multi-axis machining reigns supreme. Before you stands a gantry-type milling machining center. It looks more like a small house than a machine tool. Its spindles, fitted with ultra-hard cutting inserts, can remove up to several hundred pounds of metal per hour. The first operation is roughing. The goal, remove excess stock, eliminate surface casting defects, and give the part its basic geometry. The speed and sheer aggression of this cutting process? Absolutely mind-blowing. Those streams of hot chips tell you everything you need to know about the energy being dumped into this transformation. But the real magic happens later, during finishing operations. Remember when we talked about precision? For diesel engines, perfect cylinder geometry isn't just important, it's critical. That's where boring and honing come in. Boring creates the cylinder holes with micron-level accuracy. The slightest geometric error means uneven wear, compression loss, and ultimately engine failure. And honing, that's the final touch. A specialized tool with abrasive stones creates a micro-texture on the cylinder's inner surface, what we call crosshatch. This crosshatch is essential for holding oil and ensuring perfect lubrication of the piston rings. We're talking about polishing at nearly molecular level, guaranteeing engine life measured in decades. These machines operate under strict temperature control. Any temperature fluctuation can cause thermal deformation in a part weighing several tons, which means losing precision. That's why the shop floor maintains a constant microclimate, and the machining itself can run for days. Up next, meet our next hero, the crankshaft. This component works under the most demanding conditions. It needs not only colossal strength, but perfect balance. Manufacturing it, an engineering masterpiece. First up, preliminary journal machining. On specialized CNC turning milling machines, the connecting rod journals and main journals take shape. Given the weight and length of the shaft, unique support systems are used here to prevent sagging and vibration during machining. The critical stage, grinding. The shaft journals must have minimal surface roughness because that's exactly where friction with the bearings occurs. The smoother the surface, the less friction, and the longer the engine lasts. Special cylindrical grinding machines with highly sensitive sensors handle this job. Now, for the critical part, heat treatment and surface hardening. After grinding, the crankshaft journals undergo induction hardening or nitriting. What does this do? It creates a super hard, wear-resistant layer on the journal surface while maintaining the core's toughness and strength. This is essential so the shaft can withstand billions of load cycles. Think of it as armor for the engine's most vital component. Final stage, balancing. Given the massive weight, even a tiny imbalance can destroy the engine. That's why every crankshaft goes through dynamic balancing. If the machine detects a deviation, counterweights are added, or material is removed from the flywheel sections until the shaft achieves perfect balance. It's like tuning a violin, except instead of music, we get harmony of rotation and power. How do you achieve that kind of precision when working with such giants? The answer lies in the tooling and quality control. The tool itself is a high-tech product. Every cutter, every mill is equipped with carbide inserts or even synthetic diamonds. They have to withstand enormous temperatures and cutting pressures. Special coatings extend the life of these tools while keeping machining quality consistently high. In a dedicated tool room, there's constant monitoring of their condition, resharpening, and replacement. But the most important thing is quality control. After every key operation, the part undergoes rigorous measurement. Coordinate measuring machines help us with this. These machines, equipped with high-precision probes and laser scanners, can measure up to 1,000 points on a part's surface with accuracy down to a few micrometers. They create a three-dimensional map of the part and compare it to the perfect computer model. If the error exceeds the tolerance, the process stops, and the part gets sent back for rework or, worst case, scrapped. No part leaves the shop floor until the computer gives the green light on its perfect accuracy. And then, when all the components, the block, crankshaft, cylinder heads, connecting rods, have passed strict inspection and achieved perfect precision, they're ready for the final stage, assembly. This is a different shop, where sterile cleanliness reigns. Assembling an engine like this is no less precise a process than machining. All parts are thoroughly washed, removing even microscopic traces of metal chips and dirt. Specialists use torque wrenches to tighten thousands of bolts to a precisely defined spec. A mistake in torquing the cylinder head, for example, can lead to a blown gasket and engine failure. Every stage of assembly is tracked and controlled by electronic systems. Not a single bolt gets tightened without computer confirmation. After assembly, the engine heads to the test stand. Here it's fired up and gradually brought to operating conditions. Sensors measure temperature, oil pressure, vibration, power output. Any deviation from the norm, and the engine goes back for rework. Only after successfully passing all tests does the engine receive its quality certificate. These giants get installed on ocean vessels, locomotives, mining dump trucks, power plants. One of these engines can run for decades, churning out thousands of horsepower. And behind every hour of its flawless operation stand months of work by engineers, machine operators, quality inspectors. Manufacturing these engines is the pinnacle of mechanical engineering, where metallurgy, precision mechanics, and computer technology converge. And just like that, starting from a multi-ton forging, through rough and finish machining, through honing with precision down to microns, through heat treatment and balancing, through sterile assembly and rigorous testing, an engine is born, capable of running billions of cycles without a single failure. This is the story of how humanity learned to create steel hearts for the most powerful machines on the planet. Every crankshaft, every cylinder block, it's a symphony of engineering thought where an error of 1 micron means failure, and success means decades of flawless operation. When you see a massive ship crossing the ocean, or a locomotive pulling thousands of tons of cargo, remember, at its heart beats an engine, every part of which has passed through the hands of master craftsmen and the scrutiny of computers. This isn't just metal, it's the embodiment of humanity's drive for perfection, where precision is measured in microns and reliability in decades of impeccable service. Ever wonder how you make a material just 6 microns thick? That's 15 times thinner than a human hair. So thin that if you hold it up to the light, you can read a newspaper through it. So fragile that one wrong move and it tears, yet so strong it can withstand temperatures of 570 degrees Fahrenheit and protect your food from light, oxygen, and bacteria better than any plastic. I'm standing at the gates of the Eurofoil plant in Dudelange, Luxembourg, one of the largest aluminum foil manufacturers in Europe. Here, across 50 acres, 100 tons of foil are born every single day. That's over 600 million feet, a ribbon you could wrap around the Earth 5 times at the equator. The air is thick with the smell of hot metal and machine oil. The roar of the rolling mills is so powerful the ground vibrates beneath your feet. Welcome to the place where aluminum makes the journey from crude ingot to an almost invisible film. This isn't just a factory, this is a laboratory of precision at the edge of what's physically possible. The process begins in the foundry where real metallic hell reigns. 4 continuous casting machines run non-stop 24 hours a day, 365 days a year. I put on protective goggles with dark filters. Without them, looking at molten aluminum is just dangerous. The temperature here stays at 1330 degrees Fahrenheit. This is the melting furnace where they load aluminum ingots, massive bars weighing 55 pounds each. But Eurofoil prides itself on being eco-friendly. 70% of the raw material here is recycled aluminum. Foil scraps, production waste, even old soda cans, everything gets used. Aluminum can be melted down infinitely and it doesn't lose its properties. Jean-Pierre, the plant's head metallurgist, shouts in my ear. We're standing on a platform above the furnace, and the heat is so intense that the skin on my face starts tingling. In the enormous crucible, a silvery liquid churns, molten aluminum. But this isn't just pure metal, it's an alloy. Depending on the intended purpose of the future foil, they add magnesium, manganese, silicon. For food-grade foil, alloy 8011. For technical foil, alloy 8079. Each percentage of additive changes the properties: strength, plasticity, corrosion resistance. From the furnace, molten metal flows into the casting machine, a 100-foot-long monster. Here's where the magic happens. Liquid metal at 1300 degrees turns solid in seconds. This is continuous casting. Molten aluminum pours between two rotating water-cooled rolls, 6 feet across. Inside those rolls, water circulates at 150 pounds per square inch. When scorching aluminum hits cold steel, instant crystallization. The sound? Like dumping a bucket of water on a blazing stovetop. Hissing, crackling, clouds of steam. Out from under the rolls comes an aluminum ribbon, 1/3 of an inch thick, 5 feet wide. It's still glowing dull red, around 750 degrees. The ribbon crawls forward at 10 feet per minute, slowly cooling in the open air. I step closer and watch as a distinctive pattern emerges across the metal surface. That's the crystalline structure of aluminum. Metallurgists call this grain. Everything depends on the size and shape of those grains, how well the foil will stretch, whether it'll tear during winding, how it'll behave under heat. The perfect grain is a labyrinth, Jean-Pierre explains. The crystals need to interlock with each other, creating a strong network. If the grain's too coarse, the metal becomes brittle. Too fine, it loses flexibility. The cooled strip winds into giant coils weighing 12 tons each. These are blanks for the next stage, hot rolling. We move to the adjacent shop, where rolling mills stand as tall as a 2-story building. Here they start rolling the aluminum strip like dough, except instead of a rolling pin, 50-ton steel rollers, and instead of a table, an alloyed steel frame 3 feet thick. They feed the coil into the mill. The rollers spin, grip the strip, and pull it through with monstrous force. Pressure hits 1,200 tons per square meter. The metal resists, springs back, but gradually gives in. After the first pass, thickness drops from 8 millimeters to 4. After the second, down to 2. Speed builds. If at first the strip crawled at 5 meters per minute, after the third pass it's flying at 300 meters per minute. Air whistles. The strip hums like a taut string. Each pass generates massive heat. Metal grinding against steel heats the strip to 250 degrees. So the rollers get continuous cooling emulsion, a water oil mix. It sprays at 30 atmospheres of pressure, forming a white cloud of mist through which the strip shoots like silver lightning. After hot rolling, the strip, now 0.12 inches thick, heads to annealing. This step is critical. Here's why. During rolling, aluminum work hardens. It gets tough and brittle. The metal's crystal lattice deforms. Internal stresses build up. Keep rolling without annealing. The strip just tears. The annealing furnace is a tunnel 260 feet long. The strip travels through at 33 feet per minute. Inside, the temperature hits 930 degrees Fahrenheit in a nitrogen atmosphere. Oxygen is completely excluded. Otherwise, the aluminum oxidizes and gets covered in loose black scale. At that temperature, recrystallization happens. The metal's deformed grains heal. Internal stresses release. The aluminum goes soft and ductile again. This process takes 2 hours. Coming out of the furnace, the strip cools in a water bath, then gets dried with hot air. Now it's ready for the most demanding stage, cold rolling to final thickness. The cold rolling mill, that's the heart of the factory. 3 state-of-the-art rolling stands here, capable of rolling aluminum down to 6 microns thick. That's the limit. Any thinner? Physically impossible without tearing. The process takes 20 passes. Each pass reduces thickness by roughly 30%. 0.12 inches becomes 0.08, then 0.06, then 0.04, and so on, until you hit 0.0024 inches, 6 microns. Rolling speed on the final passes? 67 miles per hour. The foil ribbon flies faster than a car on the highway. The slightest vibration, the tiniest roller deviation, and it tears. A tear at that speed means shutting down the entire line, losing several tons of material and hours of rethreading. That's why laser thickness gauges are installed here, measuring the strip 200 times per second, accurate to 0.4 microns. The computer instantly corrects roller pressure, rolling speed, coolant flow. A human couldn't react fast enough. I'm watching the monitor in the control room. The thickness graph runs flat, 6.0 microns, 6.1, 6.0. Deviation within plus or minus 0.8 microns. That's perfection. But there's a problem. You can't roll foil 6 microns thick in a single pass. It sticks to itself, tears, crumples. So they use a clever trick, doubling. 2 layers of foil, each 12 microns thick, are stacked together and rolled as one. The rollers press down, and both layers simultaneously thin to 6 microns. But between them remains the thinnest air gap. After rolling, the layers are separated. And here's where an interesting effect shows up. One side of the foil, the one that contacted the roller, comes out, shiny, mirror-like. The other side, which contacted the neighboring foil layer, stays matte. You've probably noticed this on kitchen foil. Well, it's not a defect and not a special coating. It's the trace of the doubling process. The matte side is the imprint of the micro-texture from the adjacent sheet. At the molecular level, it's covered with microscopic irregularities that scatter light. The finished foil gets wound onto huge jumbo rolls, 6.5 feet across and weighing 3 tons. These are the mother rolls. From them, they'll later cut foil to the needed width. For chocolate wrapping, 12 inches; for yogurt lids, 2 inches; for industrial uses, 4 feet. Quality control at Eurofoil borders on paranoia. And that's a good thing. Every jumbo roll goes through a dozen tests. First up, backlighting. The foil passes in front of a powerful lamp. Any microcrack, any pore, and light will shine through. A computer flags the defect, and that section gets marked as scrap. Second, leak testing. A foil sample gets clamped between 2 chambers. Helium under pressure is fed into one. A highly sensitive detector sits in the other. If even a single helium molecule seeps through the foil, test failed. Third, mechanical testing. The foil is stretched on a specialized machine, measuring tensile strength. Quality foil must withstand a load of at least 15 megapascals. That's roughly 330 pounds per square inch. For a material 6 microns thick, that's a phenomenal number. Fourth, chemical analysis. Every 2 hours, they take a sample and run it through a spectrometer. It shows the exact alloy composition down to hundredths of a percent. Any deviation, and the batch goes back to the smelter. Fifth, corrosion testing. A sample is held in salt fog at 95 degrees Fahrenheit for 72 hours, simulating 3 years of use. If corrosion shows up, it's scrap. The final stage, slitting and packaging. Jumbo rolls feed into slitter rewinders. Disc blades made from hardened steel, sharpened to razor-edge sharpness, cut the 10-foot wide web into narrow strips of the required width. Slitting speed, 1,600 feet per minute. Blades spin at 3,000 revolutions per minute. The slightest wobble, and the foil edge comes out ragged, jagged. That's why blades get swapped every 8 hours. Slit rolls move to winding. Here the foil winds onto cardboard cores 3 inches in diameter. For household foil, the standard, 33 feet per roll. For the food industry, rolls of 1,000 feet, 1,600 feet, 3,000 feet. An automatic system measures the required length, cuts, seals the edge, marks the roll with a barcode. Output, 200 rolls per minute. Finished rolls get packed into cardboard boxes, boxes loaded onto pallets, pallets hauled to the warehouse. From here, Eurofoil foil ships to 70 countries worldwide. To Germany for chocolate wrapping, to France for cheese factories, to Italy for coffee capsules, to Switzerland for pharmaceutical blister packs, to Japan for electrolytic capacitors. I'm standing in a finished goods warehouse. Around me, stacks of pallets tower 13 feet high. Each pallet holds 2,000 rolls of household foil or 50 jumbo rolls of industrial grade. The product stored here is worth around 5 million euros. The plant runs at full capacity, 100 tons of foil per day, 3,000 tons per month, 36,000 tons per year. That's enough material to wrap the entire United Kingdom in a continuous sheet, or package 15 billion chocolate bars, or make 300 billion yogurt lids. This entire foil empire was born from a simple piece of aluminum that passed through the inferno of casting furnaces, the monstrous pressure of rolling mills, the precision of laser measurements, and rigorous quality control. From 8 millimeters down to 6 microns, a journey 1,300 times over. If you found it interesting to learn how a material thinner than a human hair but stronger than many plastics is created, hit the like button on this video. Write in the comments whether you knew that aluminum foil can be recycled infinitely. And subscribe to the channel to keep discovering the technologies that surround us every day but remain invisible.
Every year, the world produces over 4 million tons of hollow structural sections, and that's just in the US. Picture this, that's enough to build 400 Eiffel Towers annually. But behind these massive numbers lies the silence of steel giants we never see, because they're hidden inside buildings, bridges, and machines. How does rusty scrap metal transform into tubes capable of supporting the weight of entire bridges and weathering the storms of time? And what secret makes them both lightweight and incredibly strong? Stick around till the end, and you'll discover a secret you never knew existed. The market for hollow structural sections, where our heavy wall tubing reigns supreme, is a massive chunk of America's steel industry. Every year, the country cranks out over 4 million tons of these tubes. That number is mind-blowing. To put it in perspective, the entire Eiffel Tower weighs about 10,000 tons of steel. That means in a single year, American mills produce enough square and rectangular tubing to build 400 Eiffel Towers. It's an entire forest of steel giants sprouting up annually. We just don't see it because it's hidden inside structures. Mountains of scrap metal, remnants of cars, construction frames, old machinery sit waiting for their fiery rebirth. A giant crane with an electromagnet scoops up this metallic chunk and feeds it into an electric arc furnace.
Down there, in that roaring inferno where temperatures hit nearly 3,000 degrees Fahrenheit, this scrap metal transforms into a boiling, blinding lake of molten steel. Into this melt, like a chef adding spices, they introduce alloying elements, So the future pipe isn't just strong, it can withstand extreme loads and won't crack in freezing cold. Then this river of fire flows into a continuous casting machine where it cools and solidifies, becoming long, massive steel billets. For our future pipe, these are typically thick, round slugs called blooms. Automatic cutters slice off pieces to the required length, and these hot but now solid cylinders are ready for the really interesting part. This is our blank, our solid chunk of metallic dough. But how do you make a hole in it when it's hard as rock?
To do this, it's sent to a heating furnace where its temperature is brought back up to that perfect plastic state, 2300 degrees Fahrenheit. And from there, glowing white hot with a blinding yellow radiance, it moves to the piercing mill. This is the heart of the entire process, and it's real industrial magic. Picture two massive barrel-like rolls spinning in the same direction. They're set at an angle to each other. The hot steel cylinder enters between them, and here's where something incredible happens. As they spin, the rolls don't just forcefully push the cylinder forward, they also make it rotate at a crazy speed. Because of this rotation and compression, enormous stresses build up right at the center of the metal cylinder, and the metal there literally loosens up, preparing to split. And at that exact moment, from the other side, a special piercing rod, or mandrel, is fed in to meet it.
It plunges into that loosened center like a knife through butter, literally punching straight through the solid billet, transforming it into a thick-walled tube. It's an incredible sight. A solid chunk of metal becomes hollow in mere seconds, all happening with a roar and grinding that shakes the ground. The piercing process was invented in the late 19th century by the Mannesmann brothers in Germany and remains the primary method for producing seamless tubes to this day. But now we've got a round tube, and we need a square one. Our hot, freshly pierced tube immediately moves to the next stage, the forming mill. This is a series of roller pairs, but these ones aren't round. They have special grooves whose shape gradually transitions from round to square. The tube flies into the first pair of rollers, which squeeze it slightly from the sides.
Then it rotates 90 degrees and enters the next pair, which squeezes it from different sides. And so, step by step, passing through several of these gates, our round tube transforms right before your eyes into a perfectly square one. It's like a skilled sculptor, gradually, blow by blow, giving stone its desired shape. The final finishing rolls calibrate the tube with incredible precision, guaranteeing that all its walls have uniform thickness and all corners are perfectly square. The standard sizes are impressive. There are tubes with cross-sections of 500 by 500 millimeters. That's about 20 inches wide, and the wall thickness on these monsters can easily exceed 25 millimeters. Picture a steel wall as thick as a big encyclopedia. The weight of such a tube is simply colossal.
A single yard of this pipe can weigh over 800 pounds. That's like having 4 grown men standing on every yard of its length. And a standard 40-foot section? That'll clock in at over 10,000 pounds, the weight of 2 full-size SUVs, like a Range Rover. And that's just one piece. But here's the thing. Their real genius isn't the weight itself, but how intelligently it's distributed. That's their superpower. Picture a solid steel bar and a hollow pipe of the same weight. The pipe will be way more resistant to bending and twisting. Why? Because all the material sits on the outside, as far from the center as possible, and that's exactly where the greatest stresses hit under load. The hollow core? It just saves weight. Same principle as bird bones, hollow but incredibly strong.
That's why hollow profiles have the highest strength-to-weight ratio of any structural steel shape. This makes them the perfect choice when you need maximum rigidity without extra tons, in crane booms, heavy equipment frames, bridge trusses, and even roller coaster structures. It's because of these tubes that modern skyscrapers can withstand hurricane-force winds, and bridge structures last for decades, carrying millions of tons of cargo. From the final roller, a long, red-hot, now square tube emerges. It travels along a roller conveyor to a cooling table, where it slowly cools down, gaining its final, rock-solid strength. During cooling, the metal can warp slightly, so each tube is run through a straightening machine, a system of rollers that straightens it to perfectly linear precision.
Now we've got a perfect, strong, but really long pipe. Time for the final operations. A massive saw roars to life and cuts it into standard lengths, say 20 or 40 feet. Each section goes through strict quality control. Specialists check its geometry, wall thickness, angle precision. Then they X-ray it with ultrasound to make sure there aren't any hidden internal defects. Modern flaw detectors can spot micro cracks smaller than a millimeter, invisible to the naked eye. Only then does the pipe get marked with all its info: steel grade, dimensions, batch number, production date. The finished, inspected pipes get bundled by robotic cranes, strapped down with heavy steel bands, and shipped off to the warehouse. And just like that, traveling from rusty scrap metal through the fiery heart of the furnace, surviving brutal piercing and precise forming, this humble yet incredibly strong steel rectangle emerges, ready to become the silent but reliable backbone for humanity's most ambitious creations. From the skyscrapers of Dubai to the bridges of San Francisco, from oil rigs in the North Sea to the frameworks of space launch pads, everywhere these unsung heroes of modern civilization are hard at work. They don't demand applause, they don't seek recognition, but it's on their steel shoulders that our world stands. And now you know their story, from fire to structure, from the chaos of scrap metal to the mathematical precision of engineering calculations. This is the real magic of industry.
Every year, dozens of nuclear submarines get retired around the world. Steel giants weighing over 10,000 tons. Inside each one sits a reactor pumping out hundreds of megawatts. But what happens when their service ends? How do you cut out the heart of a nuclear monster and survive a battle with invisible radiation that lasts for months? Temperatures here hit 14,000 degrees Fahrenheit. A mistake isn't measured in seconds, it's measured in centuries. In this video, you'll see the decommissioning process from the first cut to the last ton of melted metal, and find out what becomes of a submarine giant's armor. The process begins with the most dangerous stage, removing the spent nuclear fuel. The submarine is moved into a special enclosed dock. Around it, a real scientific laboratory unfolds. This is a battle against invisible radiation. It doesn't last days, it lasts months. Inside the reactor core are fuel assemblies. They've kept this monster alive for decades. Each assembly is a bundle of thin zirconium tubes about ½ an inch in diameter. Inside, uranium dioxide pellets. One assembly is 13 feet long. Weight, 660 pounds. The reactor holds 100 to 120 of them. They're removed using remote manipulators. Each assembly emits a lethal dose of radiation, 500 roentgens per hour at 3 feet. That'll kill a person in an hour. The assembly is lifted by a crane rated for 20 tons and lowered into a lead container. Container wall thickness, 10 inches of pure lead. Container weight, 17,000 pounds. Only lead stops gamma radiation. The containers are loaded into special rail cars with water cooling and shipped to temporary storage. This stage takes 3 to 4 months of continuous work. If you're interested in seeing how things built for war get taken apart, subscribe to the channel. Here we show you production processes hidden from view. Once the fuel's extracted, it's time for the reactor compartment. This is a massive section of the sub. Weight, 1,500 tons. Length, 33 feet. Diameter, 30 feet. Engineers don't dismantle the reactor piece by piece. Too dangerous. The metal itself is radioactive. Neutron flux from the operating reactor bombarded the steel for years. Iron atoms transformed into radioactive isotopes, so they cut out the entire compartment whole. They use oxyacetylene torches. Flame temperature 5,800 degrees Fahrenheit. Mix of acetylene and oxygen. Feed pressure 217 pounds per square inch. The torch burns through 3-inch thick steel in 10 minutes. They cut in a ring around the compartment. 2 cuts, forward and aft. You get a cylinder. All technological openings are welded shut with ½ inch steel plates. Welding, electric arc, quarter-inch diameter electrodes. Current, 350 amps. You get a sealed capsule. It's lifted by a 200-ton crane and loaded onto a barge. The barge is towed to a burial site. In Russia, that's Novaya Zemlya. In the US, Hanford site. There, the capsules are placed in concrete trenches 65 feet deep, covered with earth on top. They'll sit there 300 years until radiation levels drop to background. Decontamination is the longest phase. The reactor compartment's cut out and shipped off, but the work's just beginning. Decades of coolant circulation left their mark. Thousands of feet of primary loop piping, pumps, heat exchangers, steam generators, all of it contaminated. Radioactive isotopes soaked into the metal. That's induced radiation. Teams in protective suits scan every foot, hunting for hotspots, areas with elevated readings. They use DP5B dosimeters. Sensitivity, 0.01 milliroentgen per hour. Every pipe gets checked, every pump, every valve. Then chemical flushing begins. They run acid solutions through the primary loop piping. Sulfuric acid at 10% concentration. Temperature 140 degrees Fahrenheit. Pressure 115 psi. The acid dissolves the oxide film off pipe walls. Radioactive isotopes go with it. Solution gets collected in 13,000-gallon tanks, filtered through ion exchange resins. Radionuclides precipitate onto the resin. Resin gets incinerated at 2200 degrees Fahrenheit. You get ash. Mix the ash with cement and pour it into concrete containers. That's Class II radioactive waste. Chemistry doesn't work everywhere. Valves, gate valves, filters, they dismantle those by hand. Teams of 3. Shifts last 30 minutes. Can't go longer, the dose accumulates. Every part gets packed in a lead box. Box weighs 265 pounds. Walls, 4 inches of lead. If contamination levels run too high, they encase the part in concrete right inside the hull. Special attention goes to the reactor's biological shield. Massive plates of lead and polyethylene. Lead layer, 6 inches thick. Polyethylene, 12 inches. Lead stops gamma rays. Polyethylene slows neutrons. Weight per plate, 4 tons. 8 plates total. They pull each one with a crane. Decontaminate with ultrasound. Frequency, 40 kilohertz. Power, 3 kilowatts. Ultrasound breaks down the oxide film. Then they rinse the plate with alkaline solution and dry it with hot air at 250 degrees. Only after thousands of air samples and surface swabs, when everything reads 0, they open the dock to regular workers. Now it's not a nuclear facility, it's just a complex steel structure. Cutting the hull. After decontamination, the submarine is ready for final dismantling. The submarine's hull isn't ordinary metal, it's an alloy built for war. It withstands water pressure at depths of 1,000 to 1,300 feet. That's 30 to 40 atmospheres. Hull thickness, 3 to 4 inches. A K29 grade steel. Tensile strength, 100,000 pounds per square inch. Regular cutters won't touch it. They use plasma torches. Plasma is ionized gas. An electric arc creates the temperature. Voltage, 300 volts. Current, 400 amps. Power, 120 kilowatts. Argon gets blown through a nozzle 1/8 inch across. Pressure, 90 pounds per square inch. Flow rate, 1 cubic foot per minute. The arc heats the argon to 15,000 degrees Fahrenheit. That's 1.5 times hotter than the surface of the sun. The plasma jet shoots from the nozzle at 670 miles per hour. That's the speed of sound. Under that stream, 4-inch thick steel melts in 5 seconds. The torch follows the marked line. Cutting speed, 8 inches per minute. Sparks and smoke fly from the torch. Flame height, 10 feet. Spark temperature, 1,800 degrees. The second tool, oxygen lances, a 10-foot steel pipe, 1-inch diameter. Inside, a bundle of steel rods, each about 1/6 of an inch thick. Pure oxygen flows through the pipe at 150 psi. Flow rate 50 cubic feet per minute. The rods are ignited with an acetylene torch. They start burning in the oxygen. Steel burns. Massive amounts of heat pour out. Temperature in the burn zone, 6,900 degrees Fahrenheit. The lance burns clean through the steel, leaves a molten seam 2 inches wide, burn through speed, 20 inches per minute, faster than plasma. But it takes serious skill. You guide the lance dead perpendicular. Deviate more than 10 degrees and the burn's incomplete. Crews of 4. Protective suits made of Kevlar. Masks with number 13 filters. They block infrared and ultraviolet radiation. Without the mask, your retina burns in 1 second. They cut from bow and stern, working gradually toward the center. The hull gets cut into cylindrical sections, each section 20 feet long, 30 feet in diameter. Weight, 400 tons. Cranes rated for 800 tons lift the sections and stack them in the sorting zone. Metal sorting. Every hull fragment gets checked again with dosimeters. They're hunting for isotope traces in microcracks and weld seams. If the device clicks, the fragment gets isolated, sent for re-cleaning or special disposal. Only clean metal receives a safety certificate. It can leave the shipyard territory, then sorting by chemical composition. Steel grades HY80 and HY100. These are high-strength steels. Nickel content, 8%. Chromium, 2%. Molybdenum, 1%. These alloying elements are treasure for metallurgists. Nickel provides toughness. Chromium, corrosion resistance. Molybdenum, strength at high temperatures. Regular hull steel. AK-29 gets sent for remelting separately. Titanium parts, the sail, fairings, also separate. Titanium doesn't melt with steel. Different melting points. Titanium, 3,034 degrees Fahrenheit. Steel, 2,795. Copper alloys, wiring, heat exchangers, to non-ferrous metal. Aluminum alloys, bulkheads, ladders, to aluminum scrap. Reborn in fire. High-strength steel heads to the metallurgical plant. Loaded into an electric arc furnace. Capacity, 100 tons. 3 graphite electrodes, 24 inches in diameter. 600 volts, 60,000 amps. 36 megawatts of raw power. An arc ignites between the electrodes and metal. The arc zone hits 6,300 degrees Fahrenheit. Metal melts, becomes a liquid lake. The melt reaches 3,000 degrees. Melting time, 3 hours. Lab techs pull samples every 30 minutes. Analyze composition on a spectrometer. Adjust with ferroalloy additives. Precision matters. Carbon tolerance, plus or minus 0.05%. Nickel, plus or minus 0.1%. Finished melt pours into a ladle. The ladle weighs 200 tons. From the ladle, it flows into molds. Create slabs, steel plates. 6.5 feet by 20 feet. 10 inches thick. 23 tons each. Slabs get rolled into sheets or cut into rebar stock. Yesterday's warship armor plating becomes a river bridge support or a skyscraper skeleton. Steel that once withstood depth charges now holds up bridges. Metal doesn't die. It lives again. If you found this fascinating, hit that like button. Drop a comment. Did you know submarines get recycled for 300 years? Subscribe. We show you how the old dies and the new is born.
Are you ready to peer into a world where millimeters determine life and gleaming metal journeys from raw material to lethal precision? Picture this. Over 12 billion cartridges are manufactured worldwide every year for military, police, hunters, and sportsmen. And each one is the result of jewelers' precision engineering, where temperature, pressure, and form matter down to the last decimal place. In this video, we'll show you everything from selecting gunpowder and brass alloys to quality tests where muzzle velocity reaches nearly 900 meters per second. Brace yourself. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the very edge of what's possible. Hundreds of millions of cartridges roll off factory production lines worldwide every year, and each one passes through quality control with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive coils roughly 1.5 millimeters thick, weighing up to 2,700 kilograms. These coils are supplied by metallurgical plants. Upon arrival at the factory, the brass is unwound on a special platform and fed into a rolling mill. The metal's temperature at this stage reaches 315 degrees Celsius to make it more malleable. Next, the brass sheet is fed into a press line, a high-speed stamping machine that cuts out discs with lightning precision, so-called blanks. Their diameter is roughly 19 millimeters. The press operates at up to 250 strikes per minute. The resulting discs are heated to 430 degrees, essential for the next deep drawing process. They're immersed in lubricant and fed into a hydraulic press, where under pressure of up to 100 tons, the disc is formed into a primary case. This process repeats several times, each time drawing the case slightly longer and thinner. Each case after drawing is annealed, heated to 540 degrees to relieve internal stress in the metal. Otherwise, the case could crack during firing. It's then cooled in water and cleaned in an acid solution. Next comes calibration and weighing. Cases pass through a high-precision laser control system. Weight discrepancy means automatic rejection. Length, wall thickness, and even acoustic response are checked. Special sensors detect whether there are microcracks in the case. Finally, the case is trimmed to precise length, a groove is cut for the primer, and the neck is expanded. The next critical stage is primer installation. It's a small but absolutely vital component that initiates firing. The primer is miniature explosive. Inside a metal cup sits the primary detonator, typically based on lead styphnate. Before installation, primers are tested for sensitivity. On an automated line, each case passes through a priming station, where a mechanism inserts the primer into the rear of the case with incredible precision. Next comes gunpowder. The type depends on the cartridge's purpose. On average, one 223 Remington cartridge contains roughly 1.5 grams of powder. For comparison, a .45 caliber cartridge uses just 0.4 of a gram. Powder is measured automatically to 1/1000th of a gram. Excess or shortage means danger for the shooter and weapon. 1/10 of a gram discrepancy is unacceptable. Once the powder's in, it's time to install the bullet. Its material, shape, and mass depend on the task: hunting, military, sport. But installation happens with the same precision. The bullet is pressed under pressure into the case. Then the neck is crimped so it won't cop out during chambering. After this comes final calibration and visual inspection. Rejection rate at major facilities is under 0.3%. And only after all stages of inspection, calibration, and final weighing does the cartridge reach its ultimate phase, packaging. Packaging isn't just aesthetics, it's a matter of protection, identification, and logistics. Cartridges are automatically sorted into trays or fed to weighing lines, where batches are formed in 20s, 50s, or 100s. The cheapest option is plastic trays with heat shrink film. Military supplies are packaged differently, in zinc or steel containers with hermetic lids. Inside are inserts with anti-corrosion treatment, marking with caliber, batch number, and manufacturing date. On industrial lines, one shift packages between 100,000 and 300,000 cartridges. Individual factories operate 3 shifts 24/7, especially during periods of high demand. One packaging machine's output reaches 12,000 units per hour. In workshops with powder, primers, and explosives, there's anti-static flooring. This is special surfacing that channels electrostatic charge from human bodies or equipment into the ground to prevent sparks. Workshop humidity is also maintained at 40 to 60%, which reduces ignition risk. Workers wear special suits made from natural fabrics or anti-static materials. Wearing metal objects, watches, or jewelry is forbidden. Only certified specialists are permitted near powder or primer zones. Access is, naturally, biometric. People don't touch powder manually. Everything happens through sealed automated systems. Primer formation, explosive mixture dosing, case sealing, everything's maximally automated. Every 45 meters, there are powder extinguishers and sprinkler systems positioned. Personnel undergo mandatory drills every 3 to 6 months. All cases, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they're disposed of or recycled. The factory is guarded like a classified facility. CCTV, armed security, inventory of every single unit. In 1998, in the United States, a powder manufacturing plant for sporting ammunition exploded due to storage regulation violations. The blast force was equivalent to several tons of TNT. 4 workers were killed. Investigation revealed dozens of systemic violations. That's why safety at such factories matters more than the products they manufacture.
Every year, the world produces over 1 billion new tires, and just as many worn-out ones end up in landfills. Just imagine, in the United States alone, over 250 million tires are recycled annually, saving the planet from mountains of rubbish. But where do these black rings go after they've served their thousands of miles? They don't simply vanish. They pass through fire, steel, and grinding machines to be born a second time. And what's most captivating, we don't even realize that every day we walk on their second life. Stay till the end, because there I'll reveal a secret that will forever change your perception of an ordinary tire. So today, we're heading to a cemetery of automobile tires. Hectares of land buried under mountains of black rubber rings. These are the silent veterans of the roads, which have rolled their thousands of miles and now lie here, seemingly useless to anyone. But this isn't the end of their story. It's merely the beginning of their remarkable reincarnation. We'll trace how these worn, dirty chunks of rubber pass through a series of brutal yet high-tech trials to be reborn as the soft, springy heart of a modern sports stadium.
Americans have learned to give a second life to the overwhelming majority of tires. The recycling rate for old tires in the U.S. currently exceeds 85%. This means that over 250 million tires annually avoid landfill and are sent for rebirth. Part of them are burnt as highly efficient fuel. Part are used in civil engineering, but a significant and ever-growing quantity is transformed into rubber crumb. At this tire graveyard operates a machine resembling a steel tyrannosaurus. It's an industrial shredder. An enormous loader grabs an entire handful of old tires and tosses them into the steel jaws of this machine. Inside it, with a deafening screech, two massive shafts with thick, sharp hooks rotate. They seize the tires with relentless force and tear them to pieces with an incredible crash. Inside every tire is a steel belt, a robust framework of steel wire. During tearing, this belt is released, transforming into a glittering web of steel threads mixed with rubber chunks. This chaotic mixture of rubber and steel moves further along the conveyor. And here, an industrial, powerful, enormous magnet enters the game, rotating above the stream of shredded material. Like a fridge magnet, but a million times stronger. It extracts all the steel threads from the rubber mass. With grinding and clanging, the steel belt sticks to the magnet and is dumped into a separate container. This steel will then be sent for remelting, whilst our purified rubber continues its journey. But it's still too large. Next stop, the granulator. During this process, another tire component is released, textile cord. These are nylon or polyester fibers that gave the tire additional strength. These light, fluffy fibers need removing. For this, rubber granules pass through a system of vibrating sieves and air separators. Powerful air streams literally blow away the light textile fluff, leaving only clean, heavy rubber granules. Now we have clean but still rather large material. To become stadium surfacing, it needs transforming into crumb. For this, granules are sent for final grinding, often in so-called cracker mills. As a result of this process, we finally obtained what everything started for, rubber crumb. This is a uniform, free-flowing mass resembling black caviar or coarse sand, where each particle size is just a few millimeters. This crumb is carefully sieved to guarantee perfect size uniformity and packed into enormous bags weighing a ton each. Its journey from dirty tire to clean, high-tech raw material is complete. And now, let's transport ourselves to where this black crumb will find its true calling, construction of a new stadium. Workers roll out huge rolls of artificial turf over a perfectly leveled gravel base. But for now, they look dreary and lifeless, pressed against the base. For them to stand up and resemble real grass, they need support. And here, a special machine enters the pitch, resembling a large fertilizer spreader. A process called infill begins. First, the machine spreads an even layer of fine, rounded quartz sand across the entire pitch. It's heavy and settles at the very base of the carpet, acting as ballast so the turf doesn't shift. And following the sand, our main hero is poured onto the pitch, black rubber crumb. The machine distributes it just as evenly across the entire surface. And here, the main transformation occurs. It's like running on a billion tiny trampolines. This dramatically reduces the load on athletes' joints and makes falls far safer. The final touch is combing the pitch. A special machine with an enormous brush drives across the turf, carefully mixing sand and rubber crumb and combing them deep down to the very base, forcing every blade of grass to stand perfectly upright. And now, when the work's complete, before us appears a perfectly green, springy, and safe pitch. And none of the players running on it might guess that beneath their feet lie millions of particles from old automobile tires. To create one standard pitch for American football or soccer requires on average between 20,000 and 40,000 old car tires. Just think about it. A single pitch completely devours an entire mountain of rubber waste. And how many such pitches are there in the country? Currently in the U.S., there are over 13,000 artificial turf pitches in schools, colleges, parks, and professional arenas. And now simple maths. If we take even the minimum figure of 20,000 tires per pitch, it turns out that in sports pitch surfacing across the country alone, over 260 million old tires have found their new home. Natural turf is a very finicky thing. It needs constant mowing, watering, fertilizing, and giving it rest. On average, a natural pitch can withstand no more than 20 hours of play per week. And a pitch with artificial turf? It can operate 24 hours a day, 7 days a week in rain and heat. And now about water. One artificial turf pitch can save between 500,000 and 1 million gallons of water annually. That's the amount of water an average family uses over several years. Add to this savings on fertilizers and lawnmower work, and the benefit becomes obvious.
The fastener industry is a true empire worth over $90 billion annually. And its flagship products? Massive bolts and nuts that hold our entire industrial infrastructure together. They're not just chunks of steel with machined threads. They're the result of a complete process involving metallurgy, high-pressure forging, heat treatment, and incredibly rigorous mechanical testing. One tiny deviation in material quality, shape, or tightening force can render an entire joint unsafe. In this video, we're going inside the production line that creates giant hex bolts and nuts to show how raw steel transforms into the mechanical foundation of the modern world. The production process for heavy-duty bolts and nuts begins with one fundamental stage: cutting raw blanks. Large diameter steel bars rolled from high-strength alloy steel are fed into industrial cutting machines and divided into segments with precisely controlled length and weight. Modern cutting systems use hydraulic shears or powerful industrial saws, producing clean square cuts that don't distort the metal's internal structure. Throughout the cutting operation, coolant is sprayed directly onto the contact zone to reduce temperature, minimize friction, and wash away metal chips. This maintains cutting tool stability and ensures the blank surfaces remain clean and free from thermal damage. Typically, bolt blanks are roughly twice as long as nut blanks, because bolts require additional material to forge the load-bearing shaft and head in a single production run. During one shift, each cutting machine can process thousands of bolt and nut blanks. Each cut takes just a few seconds, yet the allowable tolerance is extremely tight, because the final shape and mechanical strength of the product depend entirely on the initial dimensions of these blanks. After the blanks are cut, the bolts and nuts move to the heating stage, but the way heat is applied to each component isn't quite the same. For nuts, the entire steel blank feeds into a continuous furnace and is uniformly heated to a temperature range of 1900 to 2100 degrees Fahrenheit. Heating the entire body allows the blank to reach a fully plastic and uniform state. So during forging, the metal can flow evenly inside the die and form a solid hexagonal body before the internal hole is drilled and threads are cut. Temperature is tightly controlled to prevent surface burning while ensuring the core remains soft enough for proper forming. Bolts, however, are heated differently. Instead of heating the entire blank, only the head portion of the steel rod passes through an induction heating system. In a matter of seconds, the front end reaches forging temperature and glows bright orange-red, while the shaft behind it stays significantly cooler. This localized heating method concentrates energy exactly where the hex head needs to form, reduces overall energy consumption, and preserves the mechanical structure of the bolt shaft, which is the primary load-bearing section of the fastener. Right after reaching forging temperature, the blanks are transferred directly into the hot forging zone for shaping. For nuts, the entire evenly heated blank is placed inside a closed forging die, where a high-powered hydraulic press forces the metal to flow according to the die's shape, forming a solid hexagonal body. Under this intense compression, the metal densifies, and its crystalline grains reorganize into a tighter structure, making the steel denser and more uniform. Between each press cycle, the forging die is sprayed with a layer of high-temperature coolant and lubricant. This helps control heat, reduce friction, and protect the die surface during continuous operation. For bolts, the forging process focuses on the head section that was induction heated. The blank is positioned so the hot end sits precisely inside the die, and the press applies force, causing the metal to flow outward, forming the hexagonal head. At the same time, the die is also sprayed with the same type of high-temperature lubricant used in nut forging. When the fluid contacts the hot die, it instantly vaporizes and creates a temporary protective film. This prevents metal adhesion and ensures the bolt head forms cleanly, with sharp, clearly defined edges. Right after forging, both the bolts and nuts are dumped straight into large steel containers for natural cooling in the open air. For big components, this cooling stage typically runs anywhere from 30 to 60 minutes, and can take even longer if the steel mass is particularly heavy. This slow cooling method prevents thermal shock, minimizes the risk of microscopic cracking, and keeps both the shape and the internal structure of the metal stable before the parts move on to the next production stages. Once fully cooled, the bolts and nuts are transferred to the surface cleaning stage. At this point, they're typically loaded in bulk into rotating drum cleaners or vibratory tumbling machines. The rotating drum moves slowly and steadily, creating mechanical friction across the entire surface of the bolts and nuts. This process sharpens the hex edges and leaves the metal surface clean, dry, and uniform. In large-scale production lines, each batch can handle anywhere from a few hundred to several thousand parts at once. Tumbling time usually ranges from a few minutes to several dozen minutes, depending on the size of the parts and the level of oxide scale stuck to their surfaces. Once the surface is cleaned, the bolts and nuts move to the identification marking stage. For nuts, markings are stamped directly onto the hexagonal body, while for bolts, markings are placed on the top face of the head. These symbols indicate the strength grade, technical standards, and manufacturer of each part. They function as an official ID card, mandatory for bolts and nuts to be approved for use in industrial structures, heavy machinery, and large-scale construction projects. Once they've achieved their final shape and received their identification markings, bolts and nuts enter one of the most critical stages of the entire process: thread machining. The threading process for bolts typically begins with a light finishing turn on the shank to achieve a precise diameter and a sufficiently smooth surface. On the lathe, the bolt is firmly clamped and rotated at a steady speed, while the cutting tool simply glides over the surface to correct dimensions before threading. After this, the workpiece is transferred to a thread rolling machine, where 2 or 3 thread rolling dies, engraved with the precise thread profile, press against the shank under high pressure. Thread rolling is a cold forming process that doesn't remove material but rather deforms the surface of the shank, creating threads through plastic flow of the metal. This produces stronger threads with improved fatigue resistance compared to threads cut by a cutting tool. For nuts, threads are created through the tapping method. First, a specialized drill bores a vertical hole through the center of the hexagonal body. Then a tap, a rotating cutting tool with external threads, is inserted into the hole. As it advances, the cutting edges of the tap shave material from the hole wall, forming a precise internal thread profile. During the tapping operation, cutting fluid is continuously supplied to cool the cutting edges, lubricate contact surfaces, and flush away metal chips. Once threading is complete, both bolts and nuts move on to final quality control. First up are geometric checks: diameter, thread pitch, thread depth, concentricity, and sharpness of the thread profile. Threads must match standard thread gauges perfectly. Even the tiniest deviation means rejection. Next come mechanical tests, including surface hardness, tensile strength, and torque resistance. Only after passing all these tests do bolts and nuts move to packaging. At this stage, the products are no longer semi-finished parts. They're full-fledged structural components, ready to ship to construction sites, power plants, steel bridges, or drilling rigs, where every bolt and nut will be responsible for holding together massive industrial systems. From raw steel rods through cutting blanks, heating, forging, thread cutting, inspection, and packaging, giant bolts and nuts complete a manufacturing journey that's precise down to the tiniest details. If you find this journey fascinating, hit that like button to support the video, drop a comment to share your thoughts, and subscribe to the channel to keep exploring the production lines that quietly keep our modern world running.
And now imagine what holds enormous suspension bridges in the air, which daily withstand the weight of thousands of cars and hurricane-force wind gusts. Not concrete and not steel in the columns, but an invisible hero, steel cable. From thin, almost fragile wires, they create structures capable of bearing hundreds of tons. The secret lies in technology that transforms a simple metal rod into a sinew that never gives in. American factories have already woven over 800,000 kilometers of cables, and each meter is like a separate artery of civilization. But there's a detail that's not written about in textbooks, and you'll discover it only at the end of this video. Everything begins with selecting raw materials, high-quality steel wire that must possess exceptional strength and flexibility. These wires pass through a cold drawing process where thick steel rods are pulled through special holes, gradually reducing their diameter to thin but extraordinarily strong threads. This process doesn't simply make the wire thinner, it enhances its mechanical properties, making it resistant to breaking. Imagine that each meter of this wire can withstand enormous loads whilst remaining flexible and elastic. After the wire is ready, the most interesting part begins, forming the steel cable. Dozens and sometimes hundreds of such threads are twisted into strands, then woven into complex structures. Each wire layer has its purpose. Internal threads bear the main load, whilst external ones protect against wear and corrosion. The entire process resembles creating living tissue, where each thread is a separate vein that together forms a strong and reliable whole. Particularly impressive is the precision and control with which these cables are manufactured. Each stage is accompanied by strict testing. They check tensile strength, resistance to bending, and impact of weather conditions. Testing is conducted using special equipment that simulates the loads the cable will experience during bridge operation. This is extremely important, as bridges often stand in human environments or in locations with aggressive climates. Thanks to these coatings, cables not only maintain their strength, but also extend the bridge's service life, ensuring safety and reliability. Imagine the production scale. Factories that can manufacture thousands of tons of steel cables annually, unwinding and weaving hundreds of kilometers of wire. American manufacturers, for example, have many years' experience and employ the most modern technologies, allowing them to create cables for the world's most famous bridges. It's known that American Bridge Company has laid over 800,000 kilometers of steel cables for suspension bridges. Another aspect that impressed me is the role of engineers and technologists who constantly improve production processes. They work to make cables even stronger, lighter, and more resistant to extreme loads. Using new alloys, improving twisting and coating methods, all this makes modern steel cables genuine masterpieces of engineering thought. During the tour, I saw how enormous spools of steel wire move smoothly along conveyors, how wire passes through cold drawing, and how craftsmen control every centimeter of this process. American manufacturers, such as American Bridge Company, have enormous experience in manufacturing steel cables for the country's largest and most famous bridges. They produce thousands of tons of cables annually using modern technologies and strict quality control. It's known that for suspension bridges, they use cables with multi-layered structure that can withstand loads of hundreds of tons per square centimeter. During Brooklyn Bridge construction, for example, each of the main cables consisted of 19 separate strands, and each strand of 278 wires. This provided an enormous strength reserve. Steel cable production in the U.S. is a combination of tradition and innovation, where the craftsmanship of engineers and technologists is complemented by automated lines and modern equipment. Each stage, from raw material selection to protective coating application, is controlled with maximum attention, as thousands of people's safety who daily use bridges depends on this. European enterprises, particularly in countries like Germany, France, Italy, as well as Ukraine, Romania, and Poland, play an important role in supplying steel cables for bridge construction of various scales. Modern bridges are the result of millennia of engineering thought development, where traditions, innovations, and the most modern materials combine. They not only perform the function of connecting shores, but also become city symbols, cultural monuments, and technical masterpieces. Modern engineering marvels include the Falkirk Wheel in Scotland, a unique rotating boat lift that connects two canals and allows lifting boats through 180 degrees. This structure is not only functional, but also impresses with its futuristic design. Cable-stayed bridges, such as the Golden Gate in San Francisco, demonstrate the application of steel cables that withstand enormous loads and ensure structure longevity.
On a shipyard floor that stretches farther than the eye can follow, a machine nearly a third of a mile long takes shape. Tall as a skyscraper, built to carry an entire small city sealed inside metal boxes. The modern container ship is one of the most complex and staggering objects heavy industry has ever produced. It does not merely move cargo between continents, it carries the weight of global trade itself. Electronics, clothing, spare parts, appliances, the machinery of everyday life, all of it can at some point cross the deck of a giant like this. Yet the most extraordinary part of the story begins long before the hull ever touches water. Building a container ship is not simply the welding of steel. It is a project measured in years, where shipbuilding, heavy metallurgy, digital modeling, immense logistics, power plants of colossal output, and a precision without which no floating city of thousands of separate parts could ever be assembled, all converge into a single effort. What follows is how these giants are built, why their assembly ranks among the hardest industrial tasks on Earth, and how flat sheets of steel are transformed into a true ocean titan. It all begins long before the first piece of steel is ever cut. The creation of a container ship starts with design, and it is here that the fate of the future vessel is sealed. Engineers and naval architects calculate cargo capacity, stability, speed, fuel consumption, the behavior of the hull in a heavy sea, the arrangement of the containers, the operation of the engine, the trade routes, and compliance with international rules of safety. A modern container ship is not simply a large vessel. It is a balanced system in which a single change ripples through dozens of other parameters. Even at the stage of digital design, the loads on the hull are modeled, along with the methods of lifting the blocks, the order of assembly, the distortions that welding will introduce, and the way the ship will one day operate at sea. This work can stretch across many months. In a very real sense, the ship is first built in its entirety inside a computer, and only then begun in steel. The approach reduces the risk of errors that, on a real shipyard, would cost millions of dollars. That is why modern shipbuilding begins not at the dock, but inside engineering software, where the future giant is assembled before it is ever physically born. After the design comes what can only be called the birth of the ship out of metal. Enormous sheets of shipbuilding steel arrive at the cutting bay, where automatic plasma and gas cutting systems turn them into the future elements of the hull, the decks, the bulkheads, and the structural members that bind it all together. A single sheet can run longer than a city bus, and any error in its geometry will echo through the entire project that follows. But the modern shipyard abandoned hull-by-hull construction long ago. Today, the giants are built on the block principle. From the cut pieces, workers first assemble panels, then sections, and finally large blocks that already represent substantial fragments of the future ship. Such blocks can weigh tens of tons, and at times, a great deal more. At this stage, much of the piping, the cabling, the internal passageways, and the equipment is often installed in advance. This is known as pre-outfitting, and it saves enormous time, because fitting out a single block on the ground is far simpler than carrying out the same work later, deep inside an already assembled hull. It was block assembly that made it possible to build today's ocean giants within any reasonable span of time. Rather than raising a ship piece by piece directly in the dock, the yard builds it like a colossal industrial construction set. Individual blocks are joined into even larger mega sections, which are then moved to the place of final assembly. But the larger the block, the harder the task of lifting and setting it in place. Here, the heavy infrastructure of the shipyard comes into play. the colossal cranes, among them the famous Goliaths, capable of raising hundreds of tons in a single lift. With their help, megasections the size of an apartment building are moved with a precision that seems almost impossible to believe. The slightest tilt, an error in the points of grip, or a single distortion can turn an expensive operation into catastrophe. For that reason, long before the lift, engineers calculate how the structure will behave while in motion, and the assembly itself proceeds in a strictly defined sequence. Here the ship at last begins to take on its true scale, as separate parts gradually become a hull that surpasses in size most of the objects a person ever encounters on land. When the megasections arrive in the dry dock, the moment begins that can rightly be called the true birth of the container ship. It is here that the blocks are welded into a single, monolithic hull. A dry dock is an immense protected basin that can be flooded and drained, allowing these giants to be built almost as though on solid ground. Inside the dock, the keel line is laid, the supports are set in place, and then, step by step, the hull takes form. The vast sections are fitted to one another, aligned, locked, and welded. At this stage, precision and the control of distortion become critical, because welding on such a scale always drives stress into the metal. In parallel, the ship continues to fill with its systems, as additional mains, engineering runs, the structures of the superstructure, and the internal compartments are installed. The container ship is, in effect, assembled like a steel organism, where every section has its appointed place and every error accumulates along the entire length of the hull. That is precisely why assembly in the dock is among the most demanding phases of all. For here, the project, drawn from a digital model, is finally transformed into a real and living vessel. But the hull is only the shell. The true heart of a container ship is its power plant and its engineering systems. These giants are driven by enormous marine diesels that are, in their own right, marvels of heavy machinery. Yet the engine alone is not what matters most. It must be correctly tied to the propeller, the cooling system, the air intake, the exhaust, the fuel system, and the entire operating logic of the vessel. Engineers have long understood that a great many failures arise not from the engine itself, but from the poor integration of its supporting systems. A marine engine is, in essence, a giant air pump, one that demands a colossal volume of air and conditions tuned to perfection. If the ventilation of the engine room is poorly calculated, if the load of the propeller does not match the characteristics of the engine, if the logic of the cooling is broken, the entire system begins to wear itself down. The installation of the engine is therefore not the mere mounting of a heavy unit. It is the delicate engineering union of the ship's entire power network, and on it depends the vessel's survival in the open ocean. When the hull is at last watertight and able to float, one of the most spectacular moments of the whole construction arrives: the launch. For giants of this size, the dry dock method is most often used. The dock is simply allowed to fill with water, and a hull weighing many thousands of tons gradually lifts from its supports and begins to float. From the outside, it appears almost serene, but behind that apparent simplicity lies an enormous body of calculation. There must be precise understanding of how the distribution of loads will change, how the hull will behave at the instant it passes from resting on its blocks to being held by water, how the tugs will work, and how swiftly the vessel will reach a position of safety. After the launch, the container ship is still not ready for service. It is moved to the fitting out quay, where the work continues on the cable runs, the pipelines, the navigation equipment, the radars, the communication systems, the internal compartments, the insulation, the automation, and everything else that turns an empty steel shell into a real and working ship. It is at this stage that the future giant receives its brain. The final stage is the sea trials. This is the moment when the container ship first goes out to sea, not as an unfinished hull, but as a complete vessel, one that must prove that all its systems work together as a single whole. Tested are the maneuverability, the operation of the engine, the stability, the vibrations, the safety, the electronics, the navigation complexes, the communications, the power supply, the emergency modes, and a great many other parameters besides. Only after this can the ship be formally handed over to the customer. And it is here that one sees most clearly why the building of a container ship is reckoned among the most difficult assemblies in the world. This is no mere large ship. It is a floating industrial system, where thousands of tons of steel, miles of pipe and cable, an immense power plant, digital control systems, demands of safety, economy, endurance, and the capacity to withstand ocean storms for decades, all must be brought together as one. A container ship must be more than gigantic. It must be reliable, because all its power is worth nothing without absolute soundness in the open sea. Seen whole, the birth of a container ship makes one thing clear. Here stands one of the summits of modern heavy industry. First, the vessel exists as a digital design. Then sheets of steel become panels. Panels become blocks. Blocks become megasections. And the megasections become a colossal hull that receives its engine, its systems, its electronics, and at last goes out to sea. All of it demands years, thousands of specialists, immense cranes, dry docks, and shipyards the size of separate industrial cities, together with an engineering precision without which such an object simply could not be built. And in this lies the true magic of shipbuilding. The container ship appears to be nothing more than a carrier of boxes. Yet in truth, it is one of the most complex machines ever made by human hands. It is born of metal, of calculation, and of discipline, only to become a part of the global economy. And every time one of these giants leaves port, behind it stand not only the ocean and the trade it serves, but the colossal industrial machine that proved capable of creating it.
Every hour across the globe, dozens of nuclear reactions, but only a handful know that at the heart of every atomic bomb lies a material capable of destroying a city in seconds. This isn't just a weapon, it's a miniature star, crafted by human hands. You'll discover how ordinary uranium births an explosion with the force of 1,000 suns, why sand in New Mexico turned to glass, and what happened to an island that no longer exists. And most importantly, what secret hides inside a nuclear warhead. Watch until the end, because the finale will change how you see the modern world.
Back in the day, when the world was just learning to hear the voice of the atom, a few curious minds peered inside the invisible, into the heart of matter. Those were the years when science was feeling its way forward, but with great determination. German chemist Otto Hahn, along with Fritz Strassmann, like alchemists of a new world, discovered that uranium could split. It was as if ice cracked on a river, behind which a giant lay sleeping. While Europe prepared for war, a group of people secretly gathered across the ocean, later to be called the Masters of Atomic Fire. In the New Mexico desert, the Manhattan Project began. Ordinary physicists, Oppenheimer, Fermi, Teller, became the creators of the greatest force humanity had ever seen. In the summer of 1945, beneath the clouds of dawn, the first nuclear bomb exploded. Sand turned to glass, sky to fire. And in the absolute silence, one scientist whispered, "Now I am become death, the destroyer of worlds."
But the story didn't end there. Days later, Hiroshima and Nagasaki became pages of grief. And just when the world thought it had seen everything, the USSR answered. Under Igor Kurchatov's leadership in 1949, the first Soviet atomic bomb detonated. A decade later, the Tsar Bomba. Its power could level a city the size of Paris. History's irony. Nuclear weapons became not a sword, but a shield. Their existence forced enemies to talk. Ideas of security, control, diplomacy became more important than warfare. For the first time, humanity faced massive questions. Can we negotiate so everyone survives? That's how deterrence doctrine was born. Don't attack, because you know attacking means catastrophe. And while this balance is far from perfect, it's delivered decades without global war between superpowers. An entire era. Cold, anxious, but without mass battlefronts.
Nuclear research sparked whole new industries: nuclear power, reactors on submarines, medical diagnostics. Even space projects got a boost from understanding the atom. To create the most terrifying thing, we learned to grasp the most complex. Yes, nuclear weapons are dangerous, but they're also a mirror of human wisdom. We built something incredibly powerful and chose not to use it on a massive scale. This is a story about power we decided to restrain, about science that taught us not to dominate, but to coexist. Deep in laboratories, where lamplight dimly illuminates blueprints, the path to building a nuclear bomb begins. This isn't just assembling metal, it's modern-day alchemy, where every gram of material holds the power of 1,000 suns. It all starts with uranium or plutonium, isotopes capable of sustaining a chain reaction. But natural uranium is mostly uranium-238, which won't work, so they enrich it, separating out the 235 isotope using centrifuges, where gaseous uranium spins at insane speeds. Plutonium is artificial. It's produced in nuclear reactors, where uranium absorbs neutrons and transforms into plutonium, the stuff you need for a nuclear bomb. The appearance of a nuclear bomb often resembles a classic aircraft bomb, a streamlined metal casing engineered for stable descent from high altitude. In a massive hangar where the walls ring with the echo of metal, the air smells of hot steel and oil. Here begins the birth of the shell that must contain the heart of an atomic explosion. From the glowing throat of an industrial furnace flows a stream of metal, special steel, reinforced with nickel, chromium, and manganese. Its temperature exceeds 1,000 degrees. Summer sunlight looks pale compared to this fire. Masters in protective suits with transparent face shields watch the forming process. Steel sheets bend into streamlined shapes under presses exerting hundreds of tons of force. Before their eyes, an elongated body takes shape, resembling a water droplet frozen under the pressure of the heavens. Next, mechanical arms mill the internal partitions, cut openings for tail stabilizers and locking mechanisms. Every fraction of an inch, the result of meticulous calculation, because balance during descent depends on it. After this, the casing undergoes a strengthening ritual: immersion in an anti-corrosion bath, treatment with polymer coating, application of matte paint. The color? Dark green, like a military shadow in the twilight of pine trees. And finally, testing. They drop it from height, strike it with hammers, spin it in a wind tunnel. Only after passing all trials is the casing ready to receive its lethal payload. A quiet lab, half light, a faint smell of ozone, something heavy hangs in the air. In front of you lies an open nuclear bomb, its metal casing removed, its insides like an organism laid bare. There's nothing extra here. No shine, no decoration, just function, just explosion. At the center, a smooth, perfect sphere. It looks like a dull meteorite. This is the nuclear core. Plutonium-239, cold and deadly, or uranium-235, heavy as a planet in your palm. Its shape, mathematical perfection, polished down to microns. Around this sphere, an entire symphony of pressure. Composite explosives, layer upon layer, like a flower turned inside out. Their job isn't simply to detonate, but to force the explosion inward. Like hands clenching to the limit, these explosive lenses must create implosion, uniform, merciless compression that drives the material supercritical.
If even 1 second lags, the whole contraption becomes a heap of meaningless metal. And at the very heart of this implosion orchestra, the initiator, a tiny device waiting for its moment to release the first neutrons. Polonium and beryllium interact, creating a minuscule storm capable of triggering the irreversible. That's where the chain reaction begins, a match to an atomic forest. Then, the tamper layer. Heavy as a shadow, it wraps the bomb's core not for protection, but for containment. Uranium-238 or tungsten, not active, but absolutely critical. Their job? Delay the neutrons, force them back like an echo in a cave. Everything depends on this. The duration of the blast, its power, its climax. In the tail section, the brain. Automation, electronics, wires and sensors. Barometers waiting for altitude, radars tracking the ground, batteries sleeping, ready to wake.
This is where it's all decided, when everything happens, above the city, in the air, after the drop. Without this nervous system, the blast would be an accident, but here, it's a calculation. If you look at the entire structure in cross-section, it resembles the layers of a planet, like chapters in an encyclopedia of force. The outer shell, smooth and cold. The explosive layer, mathematically arranged. The tamper, an invisible guardian. The core, like a seed of what's to come. And at the very center, a spark, sleeping until awakened. Over 62 years, the world witnessed 2,065 nuclear explosions. 5,224, that's not the number of nuclear explosions, but an approximate estimate of the entire U.S. arsenal, including active, reserve, and decommissioned warheads. Now, the number of nuclear tests that the United States conducted from 1945 to 1992 totals 1,154 detonations.
Each one is a separate page in the history of power, fear, and science. The first blast, Trinity, July 16, 1945, in the New Mexico desert. It was the beginning of an era when atomic energy became a weapon. Then came Hiroshima and Nagasaki, the only instances of nuclear weapons used in combat. In the decades that followed, the U.S. tested bombs at Enuatak and Bikini atolls, in Nevada, underground, in the atmosphere, over water. The blasts had different purposes, testing new designs, demonstrating power, studying effects on equipment and living organisms. Yield varied, from a few kilotons to 15 megatons, like in the Castle Bravo test of 1954. In 1952, the U.S. conducted its first thermonuclear test, Ivy Mike. This wasn't just a bomb anymore, but a miniature star created by humans. The explosion wiped out an entire island.
In the 1960s, testing became routine. The U.S. tested warheads for missiles, aerial bombs, even neutron charges that had minimal blast waves but maximum radiation. The last official detonation happened on September 23, 1992, after which the U.S. declared a moratorium, but the arsenal remained. It gets modernized, adapted, stored. Some warheads are on submarines, some on strategic bombers, some in NATO storage facilities. These explosions aren't just technical events. This is a story about how humanity learned to control the energy of stars and put it in the service of fear. But it's also a reminder that the power capable of destroying civilization sits under the control of those who understand the price of using it. And as long as this balance holds, the world continues to exist on the edge of the abyss, but doesn't fall in.
Every year, millions of tons of steel get recycled worldwide, but only a tiny fraction becomes tools capable of handling hundreds of tons of force. Picture this: a chunk of metal weighing several tons heated to 2200 degrees Fahrenheit, hot enough that steel practically flows, and over the course of a few weeks transformed into a giant wrench longer than 10 feet. But there's one detail almost nobody talks about: the slightest mistake at any stage, and this beast can crack under load. Today, I'm showing you a process hidden from most people's eyes, and if you stick around till the end, you'll find out why these wrenches sometimes fail at the most unexpected moment. I step onto the grounds of the steel mill and immediately realize this is where things happen on a massive scale. All around me, the roar of heavy overhead cranes, the smell of hot steel, and the pounding of hammers you can feel in your chest. The master blacksmith greets me, a tall man, hands scarred from past projects, eyes tracking every movement. He shows me a massive billet, a chunk of chromoly steel over 10 feet long, nearly 2 feet thick, and weighing several tons. Chromoly steel isn't chosen by accident. Chromium gives it corrosion resistance, while molybdenum boosts strength under high heat and stress. This massive piece will become the core of the wrench, and it's already impressive on its own. Even from 3 feet away, you can feel its weight, its scale, its raw potential. The process starts with heat. The billet goes into a furnace, huge, like a small room, and they gradually crank the temperature up to 2200 degrees Fahrenheit. The metal turns red, almost flowing, and when the blacksmith strikes it with a sledgehammer, you hear a deep, resonant boom that vibrates through the floor. Here, timing is everything. Too fast and the metal can crack. Too slow and it cools down, turning hard and unworkable. Precision matters here, and the forge crew knows this by heart. One holds the workpiece in place, another swings the hammer, a third monitors temperature and shape. Every movement is honed by years of practice, and even the smallest mistake can ruin the entire job. When the workpiece becomes pliable, rough shaping begins. They use massive hammers weighing several hundred pounds, controlled by overhead cranes. Strike after strike, the metal gets stretched and expanded, taking the shape of the future wrench. Sparks spray out in fans, and after each blow, a characteristic dent remains on the surface. The next strike integrates it into the overall geometry. You can already make out where the handle will be and where the working jaw for the nut goes. The process takes several days because the metal gradually cools and needs constant reheating to avoid internal stresses and cracks. Each heating and forging cycle brings the workpiece closer to the right shape, but there's no rushing it. Steel doesn't forgive haste. After rough shaping comes precision forging. The blacksmiths work with smaller hammers and specialized dies. The working jaw gets fitted to the exact nut size, the handle stretched to the required length and thickness. Every strike matters. Even a fraction of a millimeter off can ruin the tool. Checking happens constantly. The masters use templates over 6 feet long, gauges for thickness control, straight edges to verify surface flatness. At this stage, the blank gets heated and cooled several more times. Each cycle relieves internal stresses and refines the form. The team works like a single machine. One delivers the blows, another monitors the shape, a third makes sure the metal doesn't overheat and start losing its structure. This isn't just physical labor, it's true craftsmanship. A blacksmith's eye sees what no instrument can: a barely noticeable warp, a slight thickening, microscopic curvature. All of it gets corrected here, on the anvil, while the metal's still hot and cooperative. Next comes heat treatment, one of the most critical stages. The wrench is heated to over 1,800 degrees Fahrenheit, then rapidly cooled in massive oil baths. The moment of immersion is a spectacle in itself. The oil boils, a column of vapor rises, and for a few seconds the shop floor looks like it's shrouded in fog. This makes the metal hard and durable, but also brittle. So immediately after quenching, they perform tempering, reheating to several hundred degrees and slow, gradual cooling. This gives the metal the optimal balance between hardness and flexibility. During this process, the steel literally breathes. You can see it change color from cherry red to deep blue and finally to steel gray. And with each transition, it gets closer to that state where it's ready to handle incredible loads. Manufacturing one of these giant wrenches takes several weeks, sometimes up to 3 or 4, depending on the complexity of the order and the size of the piece. Most of the time is consumed by heating and rough shaping, which are done in stages, with repeated heating and cooling to avoid cracking. After heat treatment comes grinding and polishing. The smiths use large abrasive wheels and cutters to give the wrench a smooth surface and precise dimensions. First, they strip off the rough layer of scale that formed during heating. The metal underneath gleams with fresh steel. Then they polish the handle, fit the working jaw to the nut, check every millimeter against templates. It's striking how much time goes into details that at first glance seem invisible. Rounded edges to prevent burrs, chamfers in the jaw corners, perfect parallelism of the faces. Here, it's not just precision that matters, but the sequence of operations. That's what determines the tool's reliability and the future user's safety. When the wrench is ready, they move it to the test stand. It gets clamped onto giant bolts, and they visibly check how the metal reacts to enormous loads. Engineers monitor deformation, measure deflection, hunt for micro cracks using ultrasonic scanners. They ramp up the load in stages, from minimum to rated and beyond, to confirm the safety margin. You stand nearby, and it's hard to look away as a chunk of metal transforms into a powerful, precision instrument. Here you feel the full scale of industrial work, from furnace temperature to hammer blows to grinding accuracy. At the final stage, craftsmen move on to what seems simple from the outside, but is actually a critically important part of the job: protecting the metal and preparing the tool for use. After weeks of forging, heating, grinding, and polishing, the steel is still vulnerable to external factors. Air, moisture, even oil residue from hands can trigger corrosion. And for a tool of this scale, that means the risk of cracks, deformation, and loss of precision. The craftsmen start by applying a special protective coating to the entire metal body of the wrench. This isn't ordinary paint. They use anti-corrosive compounds and lacquers that penetrate the steel's micropores and form a tough protective film. The coating has to withstand impacts and contact with aggressive fluids the tool will encounter in production. They work with brushes and sprayers, making sure the layer goes on evenly across the entire surface, including the interior parts of the jaw opening and hard-to-reach areas of the handle. If the coating goes on uneven or leaves gaps, that's exactly where corrosion can start down the road, and all this massive work gets put at risk. After applying the protective layer, they paint the tool's handle with special paint. It's not just about making the wrench look good, the paint's designed to improve grip, prevent hands from slipping, and shield the surface from scratches and grime during use. For wrenches this size, they use paint that can handle serious mechanical stress, sudden temperature swings, and contact with oils and lubricants used in factories. Usually they apply 2 or 3 coats, letting each one dry. That's how you get a dense, wear-resistant finish. After painting, they let the coating air dry naturally, takes up to 24 hours, then check it's even by running a special probe across the surface. This step might seem cosmetic, but it's actually critical. Its quality determines how long the wrench lasts, how safe it is to work with, and how precisely it turns those giant nuts. Only after every protection step is complete can the tool be considered fully ready. It's packed into special wooden crates with soft padding to prevent the coating from getting damaged during shipping, then sent off to the customer. Throughout the tour, I kept marveling at how metal transforms in people's hands into an object capable of turning nuts weighing hundreds of pounds while staying precise and controllable. From red-hot blank to lacquered finished product, every step is filled with craftsmanship, physical labor, and engineering ingenuity. These wrenches work for decades, and every time a technician grabs the handle, they're trusting this tool with their safety. This is a place where scale is measured in yards and tons, but precision in thousandths of an inch. And here, one cannot exist without the other. Picture a warship that served for decades, armed, deployed on long voyages, drills, maybe even wars. And then one day, it's no longer needed. What happens to a giant like that after its service ends? At first glance, you might think an old naval vessel just gets cut up for scrap, and that's it. But in reality, its disposal is one of the most complex and dangerous industrial operations out there, where military secrecy, environmental concerns, heavy metallurgy, toxic materials, logistics, and massive costs all collide. Because a warship isn't just tons of steel. Inside, you'll find fuel, oils, cables, electronics, hazardous materials, weapon components, specialized equipment, and in some cases, even a nuclear reactor. So decommissioning a ship after service isn't like tearing down a shed or scrapping a regular hull. It's a tightly planned industrial process where every step follows strict safety, control, and accountability protocols. Today, we're breaking down how military ships go from fleet retirement to recycled metal, and why this undertaking is so complicated and expensive. It all starts not with the cutter or shipyard, but with official fleet decommissioning. The vessel stops being an active combat unit and enters an entirely different status. But scrapping hasn't begun yet. First, the ship is prepped for transport and dismantling. Hull inspections, stability checks, towing plans, and assessments of internal compartments and external structures are completed. A key task? Preventing flooding, listing, or accidents before breakdown starts. The ship may be technically dead as a combat unit, but it's still a massive, complex structure that must reach a specialized facility safely. Only then does the transition begin from military asset to industrial recycling object. Right here, it becomes clear. Ship scrapping isn't a one-time event, but a lengthy project involving military personnel, engineers, contractors, environmental agencies, and metal recycling plants. Before they start cutting into the hull, the ship is stripped bare from the inside out. Equipment gets pulled, anything reusable is removed, and anything sensitive gets destroyed. Weapons, classified electronics, special communication systems, combat control elements all go through mandatory demilitarization. That doesn't just mean removal, they're deliberately deformed or destroyed according to strict protocols to prevent future use. Meanwhile, some equipment might get sent to warehouses and reused on other active ships if it still holds value for the fleet. This selective dismantling saves money, but it massively complicates the whole process, because the ship can't just be sent straight to the scrapyard. It has to be carefully inventoried and taken apart like one enormous collection of systems. Basically, before you can recycle the metal, you first have to separate it from an entire world of military technology that's been accumulating inside that ship for decades. Once the equipment's stripped out, one of the most critical phases begins: removing hazardous materials. Warships are packed with substances that would be serious environmental and safety threats in civilian life. We're talking residual fuel, oils, hydraulic fluids, bilge water, asbestos insulation, heavy metals, old paint, cable materials, and, on older vessels, compounds like PCBs. You can't just leave that inside and start cutting the hull with torches. First, all fluids get pumped out, because cutting could trigger fires, explosions, or contaminate surrounding water. Then, specialists in protective gear remove toxic materials while constantly monitoring air quality. On large vessels, these operations are done zone by zone, section by section, keeping the process under control. In other words, the ship first gets cleaned like a hazardous industrial site, and only then becomes a candidate for mechanical dismantling. At this stage, mistakes cost dearly. Now we're talking not just about metal, but about people's health and environmental risks. Once a ship's been stripped of its dangerous guts, the actual dismantling of the hull begins. But it's not just chaotic cutting. The hull gets carved up in stages to keep the structure stable and prevent multi-ton sections from collapsing uncontrollably. The process breaks down into tiers. First come the primary cuts. The hull and superstructure get divided into large blocks, sized based on crane capacity and yard layout. Then those blocks move to protected zones and get cut further into panels, beams, and smaller pieces. After that comes tertiary processing, sorting and prepping the steel for sale, melting down, or direct reuse. All of this demands precise sequencing because a ship is a massive hollow structure where shifting loads can trigger collapse. So scrapping is essentially controlled demolition, governed by engineering math. What matters isn't just the force of the cut, but understanding how a multi-thousand-ton hull will behave as the structure weakens. The whole economic point of this operation is recovering materials, steel above all. A warship is basically a giant stockpile of metal, and most of its mass can be recycled. The bulk is steel, hull plating, bulkheads, structural members, superstructure. Beyond that, there's non-ferrous metal, copper wiring, brass and bronze fittings, aluminum parts, cable runs, and other valuable components. Non-ferrous metals are pulled out with extra care because they fetch way more than ordinary scrap steel. Some plate and sections go straight back into manufacturing or get reworked at rolling mills. The rest goes to the smelter. From an industrial standpoint, it's a major source of secondary raw material, since recycling shipboard steel takes far less energy than making fresh steel from ore. So scrapping ships isn't just about retiring the old fleet. It's a huge channel for putting metal back into the economy, even though the process itself stays extremely expensive and labor-intensive. Nuclear-powered vessels, mainly nuclear submarines and certain large warships, occupy a category entirely their own and can't be scrapped like conventional ships. First, spent nuclear fuel is removed from the reactor and placed in specially shielded containers and storage facilities. Then, the reactor compartment itself isn't cut open like ordinary scrap metal. It's cut out in one piece, sealed, and transported to long-term storage or controlled burial sites. This isn't just heavy industry anymore. It's where nuclear safety, government oversight, and extremely expensive specialized infrastructure all intersect. If the sub had missile compartments, their disposal may also fall under separate international restrictions tied to arms control treaties. In the end, a nuclear vessel after service becomes not just a disposal job, but a highly complex government project where metallurgy is only a small piece. Everything else is nuclear safety, transportation, storage, and oversight, stretching decades into the future. So why is this industry considered one of the toughest and most dangerous? Because it combines nearly every industrial hazard at once. There's fire and explosion risk from cutting into old fuel systems, collapse risk from multi-ton sections shifting unexpectedly, toxic exposure from asbestos, heavy metals, and decades-old chemicals, environmental contamination of soil, groundwater, and air without proper controls, plus serious legal complexity, international hazardous waste regulations, documentation requirements, site certification, material tracking, and safe transport logistics. That's why modern disposal programs need far more than just cutters with torches. They need full infrastructure. Detailed hazardous substance inventories, sealed containment pads, drainage and filtration systems, continuous reporting, and strict government oversight. Even then, scrapping military ships often loses money or barely breaks even on scrap metal sales alone. Too much investment goes into prep work, safety protocols, careful dismantling, and regulatory compliance. When you look at the whole process from start to finish, one thing becomes clear. Scrapping warships after their service isn't the end. It's the ship's final industrial transformation. First, it's decommissioned from the fleet, then stripped of weapons and classified equipment, cleared of fuel, oils, and toxic materials. Then the hull is cut down piece by piece, metal sorted and returned to industrial circulation. And if we're talking about nuclear vessels, you add decades of monitoring reactor compartments and radioactive materials. Essentially, scrapping a ship is civilization in reverse. Everything built as a symbol of strength and military power now safely broken down into raw materials, waste, hazardous fractions, and reusable components. And that's where the real weight of this industry lies. It doesn't deal with new products. It deals with massive machines from the past, turning them into resources for the future. That's why scrapping warships isn't just cutting steel. It's a complex industrial finale to an entire era of service for each combat vessel.
What if a grass could be stronger than steel, yet softer than silk? How can a single plant be transformed into a floor that withstands a hammer blow and at the same time into a fabric that breathes better than cotton? Bamboo grows so fast it can shoot up by a meter in a single day, and a single plantation can be harvested for decades without ever being replanted. Every year, over 30 million tons of products are made from it, from bridges and houses to toothbrushes and cars. But there is one thing that even the largest producers don't talk about. Watch until the end, and you will learn a secret that will change your perception of this incredible plant forever.
It all begins on vast bamboo plantations that cover millions of hectares across the globe. These are not wild, chaotic jungles, but meticulously managed farms. Unlike a forest, a bamboo grove never needs replanting. When a single stalk or culm is cut, its sprawling underground root system, known as a rhizome, immediately sends up new shoots. This makes it one of the most sustainable resources on the planet. Furthermore, a bamboo forest absorbs 35% more carbon dioxide and produces 35% more oxygen than an equivalent area of trees. Harvesters, armed with simple machetes or handsaws, selectively cut only the mature culms.
A single mature culm can reach 18 meters in height and weigh over 45 kilograms, making its transportation a complex logistical challenge. When these green towers arrive at the processing plant, the radical transformation begins. First, the long culms are cut into manageable sections. They are then fed into a special machine that, with a deafening crack, splits the round sections into long strips. The next step is to strip away the outer green skin and the inner nodes, leaving clean, pale bamboo planks. But hidden within these planks is an enemy of durability: the starches and sugars that are a favorite food for insects and mold.
After this, the planks are sent for drying. Some producers air dry them, but for industrial scale, they are loaded into giant kilns where they spend several days until their moisture content drops from 50% down to an ideal 8 to 10%. This stage is critical. Any residual moisture can lead to warping and cracking in the final product. But the journey from an 18-meter culm to a smooth floorboard requires even more impressive engineering. The dried planks are passed through milling machines that give them a perfect rectangular shape. Then, a process begins that looks like the preparation of an industrial lasagna.
Here, the bamboo planks aren't just glued together. They're completely shredded into long fibers, mixed with an eco-friendly resin, and loaded into enormous steel presses. Under a hellish pressure, reaching over 200 kilograms per square centimeter and high temperature, this mass is forged into an extremely dense, monolithic block. The hardness of this strand-woven flooring can exceed 5,000 on the Jonca scale, making it more than 3 times harder than oak and more scratch-resistant than most traditional hardwoods. However, hardness is just one of bamboo's identities. Its other superpower is the ability to become something incredibly soft and silky. This, known as the viscose process, begins by grinding raw bamboo into a cellulose pulp. This pulp is then steeped in a solution of sodium hydroxide and then carbon disulfide, which transforms it into a thick, viscous liquid. This honey-like liquid is forced under pressure through the tiny holes of a metal plate called a spinneret. Imagine a microscopic shower head. As the thin jets emerge, they enter a bath of sulfuric acid, where they instantly solidify into endlessly long filaments. These filaments are then washed, bleached, dried, and spun into a yarn, from which the final fabric is woven.
Over 30 million tons of bamboo are harvested globally each year, and this figure is only growing. From kitchen cutting boards and toothbrushes to scaffolding that can bear the weight of concrete and trim elements in premium cars, this giant grass proves its versatility. It is a testament to how nature, multiplied by human ingenuity, can offer sustainable, strong, and beautiful solutions to countless challenges, transforming a fast-growing comb into the gold of the modern world. Bamboo grows both in the wild and on specially cultivated plantations.
It is cultivated for the production of building materials, textiles, paper, interior design products, and as a source of biomass. In the wild, there are over 1,000 different species of bamboo. It is a perennial, evergreen plant belonging to the grass family.
Bamboo is known for its extraordinarily rapid growth. Some species can grow several dozen centimeters in a single day. Bamboo flowers very rarely, and after flowering and producing seed, the plant usually dies. Cultivating bamboo requires specific knowledge and care, including correct planting, regular watering, and choosing the right variety for a specific climate.
Picture this. Glass that once shattered into deadly shards now saves lives. How did humanity transform a fragile substance into armor for your car? Every year, the world produces over 100 million square meters of automotive glass, enough to cover an entire country. But the real magic happens where molten rock becomes a perfectly smooth surface, in furnaces reaching temperatures over 2,700 degrees Fahrenheit. That's hotter than the surface of molten lava. How did ordinary quartz sand become the foundation of a safety technology we can't imagine modern transportation without? What accidental experiment changed the history of automobiles forever? You'll discover how the first safety glass was created, what secrets hide within its layers, and why modern windshields can withstand the impact of a rock at 60 miles per hour. Watch until the end. The finale reveals how many stages glass goes through to protect your life. The history of automotive glass production is closely tied to the development of the automobile industry, which emerged in the late 19th century. When the first cars began appearing on roads, they weren't equipped with glass at all. The open body design only partially protected passengers, while dust, wind, insects, and other hazards made trips extremely uncomfortable. Later, as cars got faster, the need arose to install protection for drivers and passengers. Windshields started being made from ordinary window glass, which, while providing some protection, had a serious flaw. During accidents, it shattered into large, sharp shards, leading to numerous injuries and deaths. Glass sliced faces, necks, arms of drivers and passengers. This was a real problem demanding an urgent solution. The first revolutionary breakthrough in automotive glass came with the creation of laminated glass, and it happened by accident. In 1903, French chemist Edouard Benedictus accidentally knocked over a flask coated with nitrocellulose. The glass cracked, but stayed intact thanks to a thin plastic layer. This accident inspired the scientists to create multi-layer glass, which later became the foundation for laminated safety glass. By the 1910s, laminated glass started appearing in premium automobiles. Its construction consisted of two glass layers with a thin, transparent film sandwiched between them. On impact, the glass wouldn't shatter. Cracks would stay trapped in the film. In the 1920s, laminated glass became widely used in windshield production. Its main advantage? Enhanced safety. Even in serious crashes, fragments wouldn't fly everywhere. They'd stay locked in the polymer layer. The next stage in automotive glass development came in the 30s, when tempered glass manufacturing technology was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it shattered, it broke into small pieces with blunt edges, minimizing injuries. In the mid-20th century, tempered glass began to be used for side and rear car windows. It was cheaper to produce compared to laminated glass and provided a sufficient level of safety for these parts of the vehicle. In the 50s and 60s, automotive glass became even more advanced thanks to technological developments. Important changes occurred. Improvements to laminated glass and the development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production and automation of manufacturing processes allowed for a reduction in the cost of automotive glass. One of the biggest technological breakthroughs in glassmaking came in 1959 with the invention of the float process. This technology, developed by British company Pilkington, made it possible to manufacture perfectly smooth glass by spreading molten glass across a surface of molten tin. Picture this. Red-hot liquid glass pours onto a mirror-like surface of molten metal and spreads itself out, forming a perfectly flat sheet. Thanks to this method, glass became more uniform, stronger, and accessible for mass production. The float process is still the foundation of automotive glass manufacturing today, ensuring precise dimensions, smooth surfaces, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 60s, heating wires started being installed in rear windows to prevent fogging and freezing. In the 80s, glass with special metallic coatings appeared that reflected sunlight and reduced cabin heating. UV protective glass, thanks to new technologies, began providing nearly complete protection from harmful radiation. Modern automotive glass is divided into several types depending on its purpose and manufacturing technology. The windshield is typically laminated glass consisting of 2 layers of glass with a polymer film sandwiched between them. This design ensures that when damaged, the glass doesn't shatter into sharp fragments. Side and rear glass are most often tempered glass, which breaks into small blunt pieces upon impact, reducing injury risk. Panoramic roofs or other specialty glass types often use laminated or tempered glass with special coatings for ultraviolet radiation protection. The main components of glass are natural materials mixed in specific proportions to achieve the desired properties. Quartz sand is the primary ingredient of glass, providing its transparency. It must be extremely pure with minimal impurities. Soda is added to lower the melting point of glass. Lime improves the mechanical strength and chemical properties of glass. Additional additives are used to adjust color, transparency, resistance to ultraviolet light, and other characteristics. The raw materials are purified, dried, and ground to a uniform consistency. It's critical that impurities that could affect glass quality are eliminated as much as possible. After the raw materials are prepared, they're loaded into specialized furnaces for melting. The melting temperature to form glass reaches around 5,000 degrees Fahrenheit. This is the temperature at which stone transforms into liquid. During the melting process, the raw materials become a uniform, viscous fluid. The glass mixture gets stirred to distribute components evenly. This matters. You want to avoid air bubbles or inconsistencies in the finished product. Glass melting furnaces come equipped with modern temperature control systems and process automation, ensuring top quality end results. After melting, the glass mass undergoes forming, which in modern production is most often done using the float process. Liquid glass flows out of the furnace and enters a bath of molten tin. Thanks to tin's high density, the glass mass spreads evenly across its surface. Under its own weight, the glass forms a perfectly flat and smooth surface. Gradually lowering the temperature, the glass hardens. By the time it exits the bath, it's ready for processing. The float method allows manufacturers to produce glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions needed for automotive production. Automated cutting machines ensure precision in the process. To prevent cracks and chips, the glass edges are ground down. Each sheet undergoes inspection for defects like microcracks, bubbles, or other damage. To guarantee the strength and safety of automotive glass, it goes through a tempering process. The glass is heated to around 1,112 degrees Fahrenheit. Then the glass surface is rapidly cooled by air jets, while the inner layers cool more slowly. This creates tension that increases impact resistance. When tempered glass breaks, it shatters into small, safe fragments, minimizing the risk of injury. Windshields use laminated glass, a construction of glass and polymer film. Its manufacturing involves several steps. A polymer film is placed between 2 glass sheets. The construction is put into a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to 284 degrees Fahrenheit under high pressure. This creates a rock-solid bond between the layers. Laminated glass has exceptional impact resistance, and when damaged, it stays held together by the polymer film, keeping drivers and passengers safe. To enhance automotive glass properties, various coatings are applied. Anti-glare coatings reduce reflections from the sun or headlights of other cars. UV protection, special layers block harmful ultraviolet radiation. Hydrophobic coatings make water sheet right off the glass surface. Heating elements, thin heating wires can be embedded in the windshield, making it easier to clear ice or fog. To achieve the exact shape needed, special thermoforming equipment is used. The glass is heated to a temperature where it becomes pliable and is formed according to the specified parameters. In the final stage, every piece undergoes rigorous inspection. They check for clarity and defects. The glass is tested for impact resistance and load endurance. Standards compliance, dimensional accuracy, shape, and other parameters are verified. The finished automotive glass is packaged to prevent damage during transport. It's shipped to auto plants or service centers where it's installed in vehicles. And that's how, journeying from quartz sand through the hellish flames of furnaces at 5,000 degrees Fahrenheit, through a bath of molten tin, through tempering and lamination, glass is born, capable of protecting life at 75 miles per hour. This is the story of how an accidentally shattered flask changed the automotive world forever. Automotive glass production is a high-tech process combining physics, chemistry, and engineering. Thanks to modern technology and strict quality control standards, automotive glass delivers safety, comfort, and durability. Every time you get in a car, remember, between you and danger, a thin layer of glass that's passed through dozens of production stages to save your life in that critical moment. Today we're going on an incredible journey. From massive crankshafts that power ocean vessels to precision railroad components that keep millions of passengers safe. Settle in and let's dive into the mesmerizing world of industrial manufacturing. Here we're witnessing something truly impressive, the machining of a massive marine crankshaft weighing over 15 tons. This isn't your typical workshop project. These crankshafts are the beating heart of container ships and cruise liners, converting the explosive power of diesel engines into rotational motion that propels these ocean giants across our seas. The star of the show, a revolutionary vertical boring mill. Rising nearly 3 stories tall, this engineering marvel features a 20-foot diameter faceplate capable of machining parts up to 65 feet long. The machine's spindle delivers an impressive 1,600 horsepower while maintaining accuracy tolerances of just 4/10,000ths of an inch. That's thinner than a human hair. An advanced computer numerical control system coordinates up to 12 simultaneous axes, ensuring every cut is executed with mathematical precision. Watch as the massive crankshaft rotates at a carefully controlled speed of 15 revolutions per minute. Carbide cutting tools, each costing more than a luxury car, slice through hardened steel like butter. The cooling system pumps 500 gallons per minute of specialized cutting fluid, preventing thermal distortion while washing away chips that look more like metal ribbons. Notice how the operator monitors vibration sensors and thermal cameras. At this scale, even tiny deviations can spell disaster. The real magic happens during the finishing passes. Using diamond-tipped tools, surface finish reaches an incredible 0.4 microns, smoother than a mirror. Laser measurement systems continuously verify dimensions, while ultrasonic testing ensures the internal structure remains intact. This single crankshaft will operate for decades, generating millions of horsepower cycles. It's a testament to German engineering precision that transforms raw steel into a mechanical masterpiece worth over $500,000. Welcome to where they've redefined what heavy-duty really means. This isn't just another CNC lathe. This is a mechanical monster engineered to tackle the roughest, toughest machining jobs in heavy industry. When aerospace manufacturers need to machine titanium landing gear components, or when power plants require custom turbine shafts, this is where they turn. This beast can handle parts up to 5 feet in diameter and 40 feet long, weighing up to 25 tons. The main spindle generates 400 horsepower through a precision planetary gearbox, delivering massive torque at low speeds. Watch the machine attack this massive steel workpiece with aggressive roughing cuts. The cutting parameters are mind-blowing. Depth of cut just over half an inch, feed rate around a 32nd of an inch per revolution, removing over 200 cubic inches of material per minute. High-pressure coolant jets at 1,000 pounds per square inch blast away continuous ribbons of steel chips that could fill a pickup bed in just minutes. Advanced vibration damping and thermal compensation systems maintain dimensional accuracy within 0.02 of an inch across the entire part length. The CNC system with adaptive control technology automatically adjusts cutting parameters based on real-time force and temperature feedback. It's like having a master machinist intuition built right into the machine's brain. Step into the world of railroad wheel manufacturing, where safety and precision aren't just priorities, they're matters of life and death. Every single day, millions of passengers trust their lives to these wheels, which must withstand enormous forces, extreme temperatures, and millions of rotation cycles. From high-speed trains racing across the European countryside to heavy freight locomotives hauling cargo across the American plains, the wheels we're about to see represent the culmination of over 150 years of railroad engineering evolution. Our journey begins with carefully selected steel billets, heated to a blazing 2,190 degrees Fahrenheit in massive induction furnaces. Watch as the glowing steel is shaped by 8,000-ton forging presses that deliver forces equivalent to the weight of 800 elephants. This forging process aligns the steel's grain structure, creating the incredible strength needed to support railcars weighing 25 tons. The wheels are then normalized in computer-controlled furnaces, cooling slowly over 48 hours to achieve the perfect balance of hardness and toughness. Quality control begins immediately. Ultrasonic testing reveals any internal defects that could prove catastrophic in service. Now the precision work begins. Each wheel blank is mounted on state-of-the-art CNC wheel lathes, masterpieces of German engineering capable of maintaining tolerances tighter than the thickness of paper. These machines feature massive chucks 10 feet in diameter that grip the wheel with hydraulic pressure equivalent to 50 car jacks. The cutting tools are specially designed carbide inserts, each costing $200 and engineered to maintain sharp edges through thousands of cuts. Computer vision systems scan each wheel, creating a three-dimensional map that guides the machining process. This is where artistry meets engineering. The wheel profile isn't just a simple curve, it's a complex mathematical shape that determines how the train will ride, steer, and brake. Watch as the lathe creates the tread surface with its precise 1-in-20 taper, the flange that keeps the train on the rails, and the intricate root radius that prevents stress concentrations. Each cut is monitored by laser sensors measuring to within 0.01 millimeters. Surface finish must be perfect. Any imperfections will create wear that could lead to derailment at 200 miles per hour. Here we're looking at one of the most demanding machining operations out there, boring and facing an 8-inch diameter hole through massive steel components. This isn't your typical drilling operation. We're talking about creating precision holes through materials that could stop a tank round. These operations are common in heavy industrial applications like hydraulic cylinders for mining equipment, deep hole drilling for oil drilling, and cylinder blocks for massive diesel engines. The horizontal boring mill dominates this operation with its massive spindle assembly, capable of reaching several feet into the workpiece. The boring bar itself, a precision tool weighing hundreds of pounds, must remain absolutely rigid while cutting forces try to deflect it. Advanced vibration damping systems and precision spindle bearings ensure cutting tool stability. The cutting insert, $300 of carbide engineering, must maintain a sharp edge while removing cubic inches of steel per minute. Watch as a massive cutting tool begins its journey through steel, creating this perfect 8-inch hole. The cutting parameters are carefully calculated. Too aggressive, and the boring bar will deflect. Too conservative, and productivity suffers. High-pressure coolant floods the cutting zone, not just for cooling, but to flush away the continuous stream of steel chips that could jam the operation. The machine's computer numerical control system automatically compensates for boring bar deflection, ensuring the final hole diameter stays within a tolerance of 0.01 inches across its entire length. Now comes facing, creating a perfectly flat surface perpendicular to the hole. The facing head, equipped with multiple cutting inserts, machines the surface at feed rates measured in thousandths of an inch. Once complete, this component could become part of a mining excavator's hydraulic cylinder, where it'll control movements of machinery weighing hundreds of tons. The precision we just witnessed ensures these systems run reliably for decades, moving mountains one bucket at a time. Our final segment showcases the artistry of complex turning operations, creating intricate threaded components that combine multiple diameters, sophisticated geometries, and precision threads in a single setup. These parts might look simple, but they represent the pinnacle of machining mastery, demanding perfect coordination of cutting tools, spindle speeds, and feed rates to achieve dimensional perfection across every feature. This component features multiple turned diameters, each with different tolerances and surface finish requirements. Notice the stepped geometry requiring different cutting tools for each operation, the internal threading that must align perfectly with external features, and the complex radii that seamlessly blend surfaces. The threading operation demands specialized thread cutting tools and precise spindle synchronization. The computer numerical control system coordinates spindle speed with carriage speed to create perfect thread pitch. Tool changes happen automatically, each cutting insert optimized for its specific operation. Single-point threading tools carve helical grooves with mathematical precision, creating threads that will mate perfectly with corresponding components. Thread pitch accuracy within 0.0001 inches, correct thread form angles, and perfect surface finish all combine to create threads exceeding commercial standards. The completed part undergoes comprehensive quality inspection using specialized thread gauges, optical comparators, and coordinate measuring machines. Every dimension, thread specification, and surface finish gets verified against engineering drawings. These complex turned parts often become critical components in aerospace applications, medical devices, or precision instruments, where failure isn't an option.
Today we're at a facility they don't exactly advertise, but one the modern world can't live without. I'm standing in front of a massive complex where they produce TNT, that explosive material that blasts through rocks and quarries, sends rockets into the sky, and, when necessary, strikes back at the enemy. Everything here smells like chemicals, metal, and that industrial power that sends shivers down your spine. The territory stretches hundreds of yards in every direction. Concrete walls, pipes, tanks, and above it all, a low but constant hum of reactors. Let's walk through together. I just got my access pass, and we're heading into the production floor. Hold on tight, it's gonna get intense. TNT, or trinitrotoluene, showed up back in the 19th century when chemists started experimenting with toluene, a colorless liquid you get from coal or petroleum. 166 years ago, a German chemist named Julius Wilbrand heated toluene with a mix of acids and got a yellow crystal that detonates with monstrous force. Since then, TNT became the king of explosives, stable, powerful, won't blow up from impact or fire, only from a detonator. You can drop it, heat it, shoot it with a rifle, and nothing happens until a blasting cap goes off. That predictability is what made it indispensable. 1 gram of TNT, that's the benchmark unit for measuring explosive force, the standard all other substances get compared to. Here at the plant, everything starts with massive tanks of toluene. This liquid flows into reactors, giant vessels made of stainless chromium molybdenum steel, because regular steel gets eaten away by acids in a matter of weeks. They pump in a mixture of nitric and sulfuric acids, concentrates that'll melt right through gloves. The reactor temperature is kept around 195 to 212 degrees Fahrenheit. Hot enough to keep the reaction going, but not so hot that it spins out of control. The nitration process happens in stages, taking anywhere from several hours to several days. First, you get mononitrotoluene, then dinitrotoluene, and finally trinitrotoluene, TNT itself. At each stage, another nitro group latches onto the toluene molecule, and with every step, the stuff gets more and more explosive. The acids circulate in a closed loop because they're regenerated and reused, not just dumped into the ground. Operators in protective gear monitor the gauges, pressure, temperature, concentration. Everything stays locked down because the slightest slip and the reaction could go sideways. From the reactor, the mixture flows into coolers, long coiled tubes where the hot TNT crystallizes. Then it's into settling tanks. The heavy TNT sinks to the bottom while the lighter acids get skimmed off. What you're left with is a jelly-like mass, crude TNT, still damp with acid. It gets washed with hot water at around 160 to 175 degrees Fahrenheit to neutralize what's left. The water changes 3 times. The first run comes out yellow with acid, the second is cloudy, and the third is clean as a tear. The spent water doesn't just get dumped. It's neutralized with lime and holding pools, filtered through a sand layer about 10 feet thick, and only then sent to treatment facilities. Ecology stays under control because acid is poison to anything living. Meanwhile, the crystals get unloaded. The mass is already solid, but still 6 to 10% damp. Now comes drying, one of the most fascinating stages. The vacuum drying chamber, a room where rotor drums hum, each about 6.5 feet in diameter. TNT gets loaded in batches of 200 pounds. They seal the drum, pump the air down to a pressure around 4 inches of mercury, and fire up the heat to 130 to 140 Fahrenheit. Fans push warm air around inside. The drum rotates, crystals tumble, dry evenly, no sticking to the walls. 2 hours, and out comes pure yellow powder at 0.5% moisture. Skip this step, and TNT would clump together or go unstable from the dampness. The powder color ranges from light yellow to deep orange, depending on purity. Here, they're producing top-grade stuff, 98% pure. Next up, granulation. They moisten the powder, press it into matchbox-sized bricks under about 3,000 pounds per square inch. These bricks come out hard as rock. Then they crush them in hammer mills, where shafts spin at 6,000 revolutions per minute, turning the bricks into granules between 1 and 3 millimeters in diameter. Why granules? Because they're easier to pack, don't create dust, and detonate uniformly. The dust gets sucked out by ventilation because breathing in TNT is bad news. The granules get poured into sealed crates holding 100 pounds each. That's the standard for quarries and the military. Every crate gets checked for moisture, no more than 0.7%. Otherwise, the TNT starts to sweat and becomes sensitive. There are special molds for underwater charges too. The pellets get mixed with paraffin so they don't get wet. The crates are sealed, labeled by batch, and sent to storage. From here, the TNT heads out to quarries, mines, military bases. One crate is enough to blast through 200 tons of rock. Now, about safety, because without it, they wouldn't last a day here. The plant is divided into zones. Reactors sit inside concrete shelters at safe distances from each other, with anti-detonation barriers between them, about 50 feet high, made of reinforced concrete. The logic is simple. If one reactor blows, the barrier absorbs the shock wave and keeps the detonation from jumping to the next one. No open flames, no sparks. They even hand over their cell phones at the entrance. All electrical equipment is explosion-proof, lights sealed in airtight housings. Personnel wear anti-static clothing, shoes with conductive soles so static doesn't throw a spark. Every 5 minutes, sensor checks for gas leaks. Emergency showers and CO2 fire extinguishers everywhere. Were there incidents? In the 19th century, explosions wiped out entire factories, but now, 0 accidents in the last 10 years. Why? Because of automation. Computers shut down the reactor in seconds at the slightest anomaly. One operator at a console monitors 10 processes simultaneously. Compare that to the old factories. Back then, everything was done by hand. TNT was packed with bare hands. Explosions happened regularly. Now, robotic manipulators, sensors, cameras. Evolution. Let's look inside the lab. This is where they test every batch. A sample gets placed in a bomb chamber, a thick-walled steel cylinder. They detonate a milligram and measure the detonation velocity, around 22,600 feet per second. If the velocity is below spec, that means there are impurities in the batch, or the crystal structure is compromised. Then they check stability. Heat it to 200 degrees Fahrenheit, drop it from 10 feet, it shouldn't crack or detonate. Then there's friction sensitivity. The cylinder spins for 6 hours, and if it doesn't blow, you're good. Lab techs check purity with a chromatograph. Toluene or acid traces, not allowed. Production here is massive, 1,000 tons per month. Power comes from their own gas turbines and steam boilers. Waste? They regenerate the acids, redistill the toluene, send it back into the cycle. Filters on smokestacks 200 feet tall. Wastewater cleaned until it's crystal clear. Nearest town is 10 miles out, so no complaints from the neighbors. Interesting fact, TNT isn't just for blowing things up. Melt it at 180 degrees Fahrenheit, it turns liquid like hot wax, and pour it into shell casings. Or mix it with other compounds for plastic charges. In quarries, 1 ton shatters a boulder the size of a 3-story house. In mining, you can't drill a mile-long tunnel without it. In the military, it's the backbone of torpedoes, mines, and aerial bombs. I'm standing in the granulation shop right now. Hearing the press rumbling, watching granules pour into bins like golden sand. The air's clean, but there's that distinct chemical smell, a familiar scent to anyone who's been inside plants like this. Discipline here is ironclad. 8-hour shifts, every action by the book, every step under camera. The people here are like jewelers, except they're not working with gold. They're working with explosives. The factory's like a living organism, roaring, spinning, producing power. TNT isn't evil, it's a tool, It builds roads, digs mines, defends the nation. Without it, there'd be no 1,000-foot bridges, no tunnels carved through mountain ranges. From the yellow crystal discovered a century and a half ago to today's high-precision production with robots and computers, it's been a massive journey. But the essence remains the same, turning chemistry into controlled force.
Imagine if construction could be not just strong, but ultra-lightweight, durable, and environmentally friendly all at once. That's exactly the revolution fiberglass rebar brought to the table. A modern material that's gradually replacing classic steel rebar in countries around the world. China produces it especially aggressively, a giant controlling a massive share of the global market. But what is this secret material that's changing the game? Fiberglass rebar is 4 to 5 times lighter than steel, never rusts, withstands harsh environments, and lasts over 50 years. China produces more than 500 million pounds of this stuff annually and controls 60% of global exports. But why are Western countries afraid of this dependency? What role does fiberglass rebar play in Beijing's geopolitical strategy? And how do they make this material that starts as molten glass at 2,700 degrees? Stick around till the end. You'll learn about projects where this material has already changed the future of construction. Fiberglass rebar. These are reinforcing rods made from a composite material based on fiberglass, impregnated with specialized resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and withstands harsh conditions, like acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs nearly half a kilogram per meter of length, while fiberglass rebar weighs around 120 grams for the same size. This means it's easier to work with, requires lower transportation and installation costs, and as a result, construction becomes faster and cheaper. China holds the leading role in global fiberglass rebar production. Factories located primarily in the eastern and central regions of the country are equipped with modern pultrusion, molding, and fiberglass polymerization lines. Chinese manufacturers produce over 500 million pounds of these materials every year, with exports making up about 60% of total global volume. China's huge advantage isn't just scale, it's price. Thanks to low-cost electricity and resources, Chinese products often undercut competitors from the US and Europe. But this triggers intense geopolitical debates. Zoom out, and fiberglass rebar has become a real hot card in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. Here's the secret angle. China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in Asia, Africa, and Latin America, Beijing is aggressively pushing this material via its global construction corporations operating under the Belt and Road Initiative. This allows China to not only expand its presence in the global construction market, but also strengthen economic influence in these regions through control over building resources. The trend toward fiberglass rebar isn't just about cost savings or new materials, it's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the US, where more and more bridges, roads, and homes are being built using lightweight composites. Unlike metal, this material doesn't corrode, making infrastructure more reliable and longer lasting. According to reports from the American Association of Construction Materials, average construction costs using fiberglass rebar drop by 20%, while structural lifespan doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, less environmental impact, and industry growth. Picture this: you're building a bridge or a high-rise. Instead of heavy steel rebar, you're using thin fiberglass rods. They can be longer, lighter, and easier to install. Plus, you don't have to worry about them rusting years later and causing the concrete to deteriorate. China's already deploying its fiberglass rebar on massive construction projects. In major districts of Beijing, Shanghai, and Guangzhou, new highways and bridge spans are going up with these materials. Around the world, Chinese companies are supplying this rebar to projects in the US, Europe, and the Middle East, strengthening their technological and economic footprint. It all starts with glass, the raw material for making glass fibers. Glass is produced from a mixture of sand, limestone, and soda. These ingredients head into massive industrial furnaces, cranking up the heat to 2,700 degrees Fahrenheit. Here, the mixture melts down into liquid glass. Then, molten glass flows through specialized openings, spinnerets, forming thousands of thin filaments. These fibers get cooled and gathered into bundles. This creates primary fiberglass, thin, flexible, and incredibly strong strands. To give the fibers their necessary properties, they're treated with a special chemical solution, an organic binder, or silane. This coating ensures a rock-solid bond between the fiberglass and the polymer matrix that comes next. The treated filaments get collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main event, forming the composite matrix. The raw material? Polymer resins, typically epoxy, polyester, or vinyl ester. They deliver high-strength performance and provide resistance to moisture and chemical exposure. Bundles of fiberglass are dipped or soaked in a polymer resin solution. The fibers get evenly coated with polymer, and excess resin is removed to prevent clumps and irregularities. The prepared wet bundles feed into a specialized forming line, an extruder. Here, the molten composite is pushed through forming dies, shaping it into rods or bars of the required diameter. Then comes a critical step, pulling and polymerization. The finished reinforcing rods immediately move to cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a unified structure. Dimensional and shape control is crucial, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard diameter for fiberglass rebar ranges from 1/4 inch to about 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During manufacturing, it passes through forming rollers that create ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It grips firmly in the concrete mass and won't slip under load. At the end of the production line, workers or automated systems cut the reinforcing bars to standard lengths, typically 20 feet or 40 feet. The bars are bundled into packages that are easy to transport and store. Each batch goes through testing for strength, flexibility, and corrosion resistance. Manufacturers often guarantee the rebar will last over 50 years, several times longer than traditional steel reinforcement. Fiberglass rebar is gaining more and more importance in modern construction thanks to its lightweight, strength, and corrosion resistance. You're about to see some of the most interesting projects actively using this innovative material. Delhi Metro, Phase 4 in India. A massive metro project where this rebar is being used extensively to reinforce tunnels and structures. This helps extend the lifespan of the infrastructure and reduce the weight of construction materials. Jizan Flood Mitigation Channel in Saudi Arabia, the world's largest project using fiberglass rebar, designed to reinforce long channels for flood control. We're talking 240 tons of fiberglass rebar that need to provide high resistance to aggressive environments. Muskrat Falls Hydroelectric Project in Canada. Rebar manufacturers are supplying material for reinforcement that guarantees the hydroelectric plant's long service life, especially under conditions of water contact and high humidity. The Sunshine Skyway Rest Area Seawall in Florida, USA. A marine structure where fiberglass rebar is the ideal material due to its corrosion resistance in saltwater. Here it reduces the need for repairs and extends the service life of the walls. The Alligator River Bridge in North Carolina, USA. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Toronto's TTC North Subway Extension Tunnels in Canada, a project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic events. And just like that, traveling from molten glass at 2,700 degrees through the formation of ultrafine fibers, polymer resin impregnation, and ribbed surface creation, a material is born that serves for over 50 years without a single trace of corrosion. This is a story about how humanity learned to create rebar lighter than air and stronger than steel, a material that's changing the geopolitics of construction and making bridges eternal.
300 tons of steel, 1 locomotive, 3 days, nothing. A machine that hauled 10,000 tons becomes scrap in 72 hours. Wheels that rolled 2 million miles sheared off in one motion. A 20-ton engine ripped from the frame by crane. The diesel tank holding over 1,300 gallons sliced in half in 10 seconds. This isn't an accident. This is scheduled decommissioning. The most precise, cold-blooded, calculated process in global industry. Today we're showing you how locomotives die. Why behind every death lies exact mathematical calculation. And where the metal goes when a train reaches the end of the line. On the edge of an industrial city sits a massive concrete lot the size of an airport. Rows of dead machines stretch beyond the horizon. Diesel locomotives, electric engines, freight cars, tankers, refrigerated units, several hundred strong. Each one's a former workhorse, run into the ground. A TE-10 series locomotive weighs 276 tons. Over 40 years, it traveled more than 4 million kilometers, 100 laps around Earth. A hopper car, 78 tons empty plus 100 tons of cargo every trip. Now they're tapped out. Metals fatigued from constant vibration and temperature swings. Corrosion ate through load-bearing beams. Wheel set bearings hit their limit. Repair cost more than replacement. Economics beat engineering. So the machine gets put in line for total disassembly, down to the last bolt, the last rivet, the last square inch of steel. Stage 1 of recycling is prep, the most dangerous part. A single locomotive's fuel tank holds up to 7 tons of diesel. The lubrication system, half a ton of industrial oil. The cooling circuit, thousands of gallons of antifreeze. Electric locomotives transformers, special dielectric oil that releases toxic fumes when burned. All fluids get pumped out with industrial equipment. Work runs 8 hours straight. Fluids go into separate tanker cars for processing. Diesel gets filtered and sold as industrial fuel. Used oil regenerated to commercial grade. Antifreeze cleaned and back into service. Not a drop wasted. One stray spark, the entire yard goes sky high. Open flames banned, spark-producing tools banned, even regular cell phones banned. Only when the locomotive is bone dry does real teardown begin. First, they strip out whatever can be sold whole. No cutting, no torches, no press. Battery packs, tons of pure lead. Traction motors, pounds of pure copper in the windings, sold as complete units. Power transformers from electric locomotives, copper coils weighing up to 2 tons apiece. Cable harnesses, miles of copper wire, spooled into coils. Instruments, sensors, control computers, all sold as parts to keep working locomotives running. Next, the wheel sets. Alloy steel, hardened to near diamond toughness. One set weighs 2 tons and sells as premium scrap for casting new wheels. Then they pull the cooling radiators, aluminum blocks the size of a small truck, each weighing about a ton. They remove the air compressors and unbolt the high-pressure fuel pumps. Incredibly precise devices machined to within 1/100th of a millimeter. After that, they yank the engine from the frame. The D49 diesel, 20 tons of metal, 4,000 horsepower. An overhead crane lifts it through a roof opening. It's headed either for full overhaul or straight under the press. Now the locomotive's down to a bare steel skeleton. That's when the real monsters come in. Hydraulic shears, the scrapper's main tool. Crushing force up to 1,500 tons. They cut through an 8-inch steel beam like paper. One movement, no sparks, no flame, almost no noise. Where shears won't fit, tight spots, complex welds, they bring in the torch. The oxyacetylene flame heats metal to 3,000 degrees. Steel melts instantly. The cutter, in fireproof suit and dark mask, guides the jet along the seam with surgical precision. Sparks fly 30 feet in every direction. A 100-ton body breaks down in 2 working days. Cab, separate. Frame, separate. Shell, separate. Fuel tank, separate. Engine covers, separate. Every piece gets its own number and goes to its own pile. Metal gets sorted by type, the most critical step. Sorting accuracy directly determines the final price. Ferrous scrap, standard carbon steel. Non-ferrous, copper, aluminum, brass, bronze. Stainless steel, separate pile. Engine block cast iron, separate pile. Alloyed steel from wheel sets, separate pile, worth almost 10 times more than regular steel scrap. Sorted metal gets pressed. A 2,000-ton hydraulic press crushes bent steel sheets into a dense cube about the size of a household fridge. One bale weighs up to 5 tons. Density nearly matches solid steel. Bales get loaded into rail cars, the very same freight cars that will one day end up here themselves, then shipped to the steel mill. There, at 1,600 degrees, steel melts in an electric arc furnace and gets cast into fresh billets. One retired diesel locomotive yields roughly 200 tons of pure metal, enough to build the shell of a brand new locomotive. The circle closes. A machine that hauled freight for half a century becomes the rail another machine will roll on. A wheel that traveled 1,000,000 kilometers becomes the wheel for the next 1,000,000. A beam that bore thousands of tons becomes the beam of a new bridge. That's the secret of industrial recycling. Nothing vanishes. Steel outlives any locomotive, any factory, any engineer who forged it. It simply changes shape and starts a new life. Every year, tens of thousands of rail cars and thousands of locomotives reach the scrapyard. Each transforms into new rails, new bridges, new trains, carrying the next generation of cargo across continents. The endless cycle of steel in industrial civilization. Subscribe. We show you how real industrial scale actually works. Picture this, a sheet of aluminum, 4 millimeters thick. You can bend it with your bare hands, scratch it with a key, punch through it with a hammer. Now imagine that exact same material is what makes up the wing you're sitting on at 36,000 feet. That wing's carrying 300 tons at 550 miles per hour, and it doesn't break, doesn't bend, doesn't crack for decades. How does a 4mm sheet transform into a structure you trust with your life? Today we're going behind the scenes at an aircraft manufacturing plant where they press wings and fuselages for passenger jets, and I'm going to show you every single step of that journey. If you're into deep dives like this, hit subscribe and ring that bell so you don't miss new episodes.
It all starts in the raw materials warehouse, and the first thing that hits you is the scale. Aluminum sheets and plates are stacked several meters high, each sheet marked with its alloy designation. Aviation doesn't use regular aluminum. They use 2000 and 7000 series alloys, enhanced with copper, zinc, and magnesium. These additions make the metal several times stronger than pure aluminum, while keeping its light weight. Every batch arrives with a passport: chemical composition, mechanical properties, ultrasonic inspection results. If even one parameter falls outside tolerance, the entire roll goes back to the supplier. There's no such thing as good enough here. The cost of a mistake is measured in human lives. From the warehouse, sheets travel to the cutting shop on special carts, with soft padding to prevent surface scratches. Laser and water jet cutters slice blanks from digital templates, each part cut to within tenths of a millimeter. A single wing skin set comprises hundreds of parts in different shapes and thicknesses, and each one has its own unique number in the engineering documentation. Now for the most spectacular part: forming. That flat sheet needs to become a panel with precise curvature, matching the aerodynamic profile of a wing or the roundness of a fuselage. For this, they've got presses that'll take your breath away. The hydraulic stretch press for skin forming. This machine stands as tall as a 3-story building, with force measuring tens of thousands of tons. The aluminum sheet gets clamped along the edges by special grips. A massive steel die, the punch, rises from below with the exact shape of the future panel, and the press slowly, inch by inch, stretches the sheet around this form. The metal stretches, takes on the curvature, and stays that way forever. The sound, a deep, heavy groan of metal that makes the floor vibrate under your feet. The entire pressing cycle takes several minutes, but prepping for one cycle? Hours. Setting up the die, calibrating the force, checking the sheet temperature, because cold aluminum behaves completely differently than warm. For fuselage panels, they use a different method: shot peen forming. It looks almost absurd. They lay a flat sheet on a table and blast it with steel balls about a millimeter in diameter from special nozzles under pressure. The balls hammer the surface at enormous speed, creating thousands of microscopic dents. The top layer of metal stretches while the bottom stays the same, and the sheet starts to curve on its own, like running scissors along a ribbon and watching it curl into a spiral. By controlling the intensity of the bombardment and the impact zone, you can achieve precisely the curvature you need, that signature fuselage roundness. The method seems crude, but the precision is stunning, within tenths of a millimeter on panels several meters long. After forming, each panel gets checked with a laser scanner. The beam sweeps across the entire surface, building a 3-dimensional model of the part that's overlaid on the digital reference. The computer highlights deviation zones, and if even a single point falls outside tolerance, the panel goes to scrap or rework. The formed panels aren't wings or fuselage yet. They're just skin, a thin shell that can't handle anything serious on its own. To make it withstand flight loads, internal structural elements are attached from the inside: stringers and frames. Stringers are long profiles running along the structure. They handle tension and compression. Frames are cross-sectional rings that maintain the shape. Together, they form a skeleton to which the skin gets riveted. And this sandwich of shell and framework can now bear enormous loads. And here begins the most painstaking work: riveting. A single wing on a passenger jet has several 100,000 rivets. Each one is made from a special aviation alloy. Each one goes into a drilled hole with precision down to a few thousandths of an inch. Automated riveting machines place up to several thousand rivets an hour. The robot drills the hole, inserts the rivet, bucks it, and immediately checks the force.
But there are places the robot can't reach. That's where people work. A riveter with a pneumatic hammer and bucking bar is one of the most respected workers on the aircraft factory floor. While the skin is being made, they fabricate the spars, the main load-bearing beams of the wing. These are the most heavily stressed parts in the entire aircraft. The whole fuselage hangs from them, along with passengers, fuel, and cargo. A spar for a large airliner is a single piece up to 115 feet long, milled from a solid aluminum plate several inches thick. A 5-axis machine removes up to 90% of the original metal, leaving behind a complex landscape of ribs, webs, and flanges. Milling a single spar takes up to 24 hours of continuous operation. The cutting tool follows its programmed path inch by inch, and you can't stop the process because any pause will leave a mark on the surface. From a plate weighing several tons, you get a part that weighs 10 times less but can carry loads of hundreds of tons. The chips don't go to waste. They're collected, pressed into briquettes, and sent back for remelting. When all the parts are ready, assembly begins. The wing is assembled in a special jig, a massive steel frame as long as the wing itself, holding every component in its exact position. First, they install the spars, then the ribs, transverse frames that define the aerodynamic profile, followed by the stringers, and finally, the skin. Panels are fitted and riveted one after another. At every stage, inspectors check gaps, alignment, and rivet tension. The tolerance for panel fit-up is 0.3 of a millimeter. If the gap is larger, the panel comes off and gets refitted. Assembling one wing takes about 2 weeks. The fuselage is built in sections: nose, center, tail, and each is finished completely on its own. Then they're joined into a single tube. The moment of joining is an incredible sight. 2 enormous cylinders, several meters in diameter, slowly approach each other on rails, slide together with a gap measured in fractions of a millimeter, and lock in place with thousands of bolts and rivets. After assembly comes sealing. Every seam, every rivet hole in the fuselage gets coated with a special sealant that turns flexible and waterproof when it cures. Without it, at 36,000 feet, where pressure is 4 times lower than at sea level, air would leak through microscopic gaps, making it impossible to keep the cabin pressurized. After sealing, they close up the fuselage and pump in pressure, simulating flight conditions. Sensors all over the body track leaks. If air's seeping out somewhere, they hunt it down, find it, fix it. Only after passing that test does the section get cleared. The wing goes through its own trials. They mount it in a test rig and bend it upward with hydraulic cylinders, slowly, carefully, measuring deflection at hundreds of points simultaneously. The wing has to withstand bending several feet upward without breaking. It flexes like a bow, but doesn't snap. During certification tests, they bend the wings until they actually break to know the exact failure limit and confirm it exceeds the design spec with margin to spare. Once the wing and fuselage pass every inspection, they're hauled to final assembly.
That massive hangar the size of several football fields, where ceilings soar 10 stories high. Here, wings mate with the fuselage through the central keel beam. Landing gear gets installed, engines hang beneath, cockpit and systems go in. From separate sections, an airplane is born. The entire journey from flat sheet aluminum to finished wing, that's months of work, hundreds of operations, millions of control points. Every rivet recorded in a passport, every seam documented, every panel with its own story, from metal smelting to the machine number that formed it. Next time you sit by the window and look at that wing, remember, this structure started as a flat sheet barely 1/6 of an inch thick. And every fraction of that journey, someone's work, someone's inspection, someone's craft. Hey everyone, on this channel we go behind the scenes where cameras don't usually get access. If you're into these deep dives, hit subscribe and ring that bell so you don't miss new episodes. Today we're at a factory where strike drones are built from sheet metal. You know, standing in the middle of humming machinery, watching an ordinary piece of aluminum transform into a machine that can fly thousands of miles, you realize this isn't just manufacturing. This is an entire world where every single part has its own story. Just one look at the assembly line gives you goosebumps. Dozens of airframes at different stages, the smell of red-hot metal, the roar of presses and the crackle of welding. We're going to walk through every step, from cutting sheets to the finished drone, and I'll show you exactly how it all works. Buckle up, there's going to be lots of steel, bolts, and maybe a little adrenaline, because the scale here is seriously impressive. It all starts in the cutting shop, where stacks of aluminum and duralumin sheets sit waiting, roughly 1/10 of an inch thick. They arrive in massive bundles, wrapped in protective film to prevent scratches during transport, and are immediately laid out on the cutting equipment tables. Before cutting, every sheet goes through incoming inspection, checking thickness, surface flatness, absence of micro cracks. The laser cutter traces the contours of wings, fuselage, and tail with surgical precision. No crooked lines or jagged edges, because in flight, an error of a millimeter can cost you dearly. The drone needs perfect aerodynamics to fly stable and efficient. The laser melts the metal's edge, leaving a smooth cut, while the plasma cutter handles thicker material. Sparks flying, but both technologies deliver clean geometry without extra finishing. Then the blanks head to pressing. Massive hydraulic presses, thousands of tons of force, stamp out bends, stiffening ribs, and longerons. The sound is like thunder when the die drops and the metal beneath it crunches, taking its commanded shape. The output? Finished panels with precision geometry that'll later be joined into the fuselage. The aluminum here isn't your regular stuff. It's a special alloy with magnesium and copper that handles temperature swings from -58 to +194 degrees Fahrenheit without cracking from vibrations or friction. This material's lighter than steel, but strong enough for a structure that needs to endure hours of continuous flight. Next up, fuselage assembly. Different vibe here. Workers in protective suits, tables covered with blueprints, and a whole arsenal of tools. Every panel gets ultrasonic testing for hidden defects. Then they bend it, drill holes, and bolt it together. I watched them assemble the tail section, like a construction set, only full scale, a couple yards long. The bolts aren't ordinary either, titanium or high alloy steel, with threads that hold for years. There are automated lines too, where robots install rivets themselves, thousands per hour. No fatigue, no mistakes. While the fuselage takes shape, engines are already roaring on the next stand over. Here's everything about simplicity and reliability. A 2-stroke gasoline engine, similar to those powering old mopeds or lawnmowers, but tailored for the sky. No complex turbines or compressors, just cylinders, a carburetor, spark plugs, and a pusher propeller in the back. About 15 horsepower, but for a drone weighing around 450 pounds, that's more than enough to cover thousands of miles at a cruising speed of 110 miles per hour. The simplicity of design is a deliberate choice. Fewer parts mean fewer points of failure during long autonomous flights. The engine arrives semi-assembled,
already a complete unit with crankshaft, pistons, and exhaust system. First thing, it's mounted onto an aluminum frame, which then attaches to the tail section of the fuselage. A worker in gloves slides the engine into the groove, lines it up with the holes, and torques down the bolts with a calibrated wrench, each to a specific torque value spelled out in the documentation. Every bolt gets anti-vibration washers because in flight, vibration can loosen any connection in a matter of hours. Then they hook up the fuel line. Thin rubber hoses run from the tank in the wing to the carburetor through filters, keeping dirt from clogging the jets. The fuel, regular aviation gasoline, a mixture with additives for stability on long-distance flights. The tank sits inside the wing, and its capacity is calculated so the drone can complete the entire route without refueling. As fuel burns off, the center of gravity shifts, and the autopilot accounts for this during flight control. Next up, the engine control electronics. The throttle valve connects to a servo that takes orders from the autopilot. It automatically adjusts RPM based on altitude, speed, and remaining fuel. The servo is small, like one from an RC model, but with metal gears for reliability. Plastic wouldn't survive here. The propeller goes on last, two-bladed, with a pitch that's dialed in on a special test stand. It's laser balanced to eliminate vibrations that could damage the shaft or wing structure. At idle, it sounds like a moped a half-mile away, but at full throttle, it roars like a miniature airplane.
Next up, engine testing. They lock it onto a vibration stand, hook it up to a computer, and fire it up. First few seconds, light smoke from the oil, then steady RPM. The technician listens. Any metallic knocking? Exhaust running smooth? Cylinder staying below 203 degrees Fahrenheit? Sensors pull real-time data, temperature, oil pressure, rotation speed. They tune the propeller, adjusting blade angles to max out thrust while keeping fuel burn lean. Every engine runs on the stand for at least several hours straight, simulating actual flight loads. If everything checks out, they preserve the engine, wrap it in plastic, and set it next to the fuselage. Mounting it on the drone takes a few minutes. Slide it into the tail section, tighten the bolts, check the fuel line and wiring. Done. Ready to roll out to the flight range. Now the wings, that's a whole different story. Ribs and spars are stamped out of duralumin sheets, bonded with foam core to form the aerodynamic profile, then covered with fabric or plastic. Wingspan runs about 8 feet, and each one feels light as a feather to the touch, yet strong as a wooden plank. Hidden inside is a lot. Fuel tanks, wiring, some of the electronics. The wings attach to the fuselage with quick-release fittings, so the drone can be disassembled for transport and put back together right in the field in a matter of minutes. The electronic guts deserve their own mention too. Surprisingly simple. Navigation module, chip-based autopilot, altitude and heading sensors, barometer and accelerometer. Nothing extra, because the drone has to fly itself, along a preset path, thousands of miles over the ground without operator input. Programmers test the software on separate benches, punch in coordinates, and the virtual model on screen flies exactly along the planned route, hugging terrain and holding altitude. After final assembly comes painting and camouflage. The body gets coated with anti-corrosion primer, then covered with special radar-absorbing paint, gray-green matte finish so it doesn't glint in the sun. This isn't just cosmetic. That coating genuinely reduces radar signature. Then comes test stand evaluation. They check balance, vibration, fuel tank sealing. Interesting fact, drones aren't just tested under normal conditions, but also in vacuum chambers to see how joints and connections behave at high altitude, where pressure and temperature drop sharply. If everything checks out, the drone moves to flight trials. It launches from a catapult, climbs, gains altitude, runs its program, and returns. Quiet, almost smokeless, just dissolves into the sky like a ghost.
The production scale is impressive. Dozens of machines being assembled simultaneously on the line, work running around the clock in 3 shifts. Metallurgists melting alloys, machinists turning shafts, electronics techs soldering boards, all in one complex where every stage syncs with the others. Quality control at every step, because one defective part can destroy the entire aircraft.
Without this metal, there'd be no electronics, no smartphone in your pocket, no computer on your desk, no satellite in orbit. Every second, millions of microchips are being soldered worldwide, and they all depend on tin. The metal that 5,000 years ago launched humanity into the Bronze Age today connects transistors and processors. The oldest metal of civilization became the foundation of the digital revolution. How do gray rocks from the jungles of Malaysia become the silvery metal that flows from your soldering iron? You'll learn why tin doesn't rust, how it changed the course of human history, and why modern industry would collapse without it. Watch until the end. The finale reveals what's behind every microchip in your phone. This is the story of a metal that survived millennia and remained irreplaceable. Tin's story predates writing itself. Around 5,000 years ago, in the 3rd millennium BC, someone accidentally mixed copper with tin. The result? An alloy harder and stronger than both metals, bronze. It changed everything. The Bronze Age began, an entire civilizational era named after a tin alloy. Bronze swords, axes, armor were sharper and lasted longer than stone and copper. Armies with bronze weapons conquered continents. There was one problem. Tin was rare. Copper could be mined everywhere, but tin only in a few places on Earth. Cornwall in Britain, Bohemia in Central Europe, the mountains of Afghanistan. Expeditions traveled thousands of miles for tin. Phoenician traders sailed to Britain's foggy shores across the entire Mediterranean just for tin. The metal was valued more than gold. Whoever controlled tin deposits controlled military power. Civilizations rose and fell depending on access to this silvery metal. In the Middle Ages, tin was used to make tableware, tin cups, plates, mugs. Tin doesn't rust and doesn't give food a metallic taste. Rich people ate from tin, poor people from wood or clay. Tin soldiers became a favorite toy for children in the 19th century. They were cast by the millions. But a strange danger lurked. At temperatures below -13 degrees Celsius, with tin, something miraculous happens. The silvery metal starts turning into gray powder. This is called tin pest. The crystalline structure reorganizes, the metal crumbles. During cold winters, tin buttons on soldiers' uniforms turn to dust. Tin pipes and church organs inside unheated cathedrals disintegrated. Napoleon lost his army in Russia, not just from the cold. Tin buttons on soldiers' uniforms crumbled, clothing fell apart. Tin past played its role in history. Modern tin is treated with additives that prevent this transformation, but pure tin in freezing temperatures still turns to powder. Where does tin come from today? Tin is a rare element. It makes up just 0.02% of Earth's crust. The primary tin mineral is cassiterite, tin oxide, dark brown or black crystals, incredibly heavy, density almost 7 grams per cubic centimeter, heavier than iron. The largest deposits are in Southeast Asia, Indonesia, Myanmar, Thailand, Malaysia. They account for about 70% of global production. There are deposits in China, Peru, Bolivia, Australia. Tin is extracted 2 ways: open pit mining in quarries or washing from placer deposits. Placers form when cassiterite gets weathered out of rock by rivers over centuries and accumulates in valleys. Heavy crystals settle to the bottom. Lighter rock gets carried away by the current. In Malaysia and Indonesia, entire islands are made of tin-bearing sands. That's where most of the world's tin comes from. Then begins the dramatic process of transforming dark stone into silvery metal. Tin mining from placer deposits uses giant dredges. Picture a floating factory, a steel ship with a massive pipe that descends to the bottom. At the end of the pipe, a cutter head with teeth rotates. It tears into the bottom sand, grinds it up. Powerful pumps suck up the mixture of sand and water, slurry, and lift it to the surface. The ship has washing equipment installed, a system of flumes, screens, and centrifuges. The slurry flows down inclined flumes lined with special mats. Light sand washes away with water, while heavy caoutchouc crystals get trapped in the mat fibers. It's like gold mining, except instead of gold, it's tin. Periodically, the mats are removed and shaken out. You get a concentrate, dark sand containing up to 70% caoutchouc. The rest is impurities from other minerals. This concentrate is re-washed on special tables, blown with air to separate light particles. The final concentrate contains about 75% tin oxide. It's dried and shipped to the smelting plant. At the plant, cassiterite is reduced to metallic tin. The concentrate is mixed with coke, carbon, and loaded into a reverberatory furnace. It's a massive furnace, the length of a bus, lined with refractory brick. Inside, temperatures reach 2,400 degrees Fahrenheit. Natural gas or fuel oil burns, flames reflect off the furnace roof and heat the mixture from below. At this temperature, carbon strips oxygen from the tin oxide. Cassiterite is reduced to metal. Molten tin collects at the bottom of the furnace, a silvery pool glowing orange from the heat. Tin's melting point is just 450 degrees, one of the most easily melted metals. The molten metal is periodically tapped through a tap hole, an opening in the furnace's sidewall. Silvery metal flows into ladles, but this isn't pure tin yet. It contains impurities: iron, copper, lead, arsenic. Refining is needed, purification. The molten tin is heated to 750 degrees and blown with compressed air. Impurities oxidize and float to the surface, a slag. The slag is skimmed off, the blowing repeated, several times over. Pure tin gets poured into molds, creating ingots weighing about 66 pounds each. Silvery white, shiny. Tin is incredibly soft. You can scratch it with your fingernail. But it has this amazing property. It doesn't oxidize in air. More precisely, it forms this ultra-thin oxide film that protects the metal from further corrosion. That's why tin cookware lasted for centuries. Today, most tin doesn't go into cookware, it goes into electronics. 70% of global tin production is used for soldering. Solder is an alloy of tin with lead or silver. The melting point of solder is around 400 degrees Fahrenheit, low enough that it won't damage electronic components. When you're soldering a microchip to a circuit board, the solder melts, flows into the gaps, cools down, and forms a solid electrically conductive connection. Without tin, assembling electronics would be impossible. Every smartphone contains thousands of soldered connections. Every computer motherboard, tens of thousands, all held together by tin. Tin is also used for tinning, coating other metals with a thin layer of tin. Tin cans, they're actually steel, just coated with tin inside and out. A layer of tin just a few microns thick protects the steel from rust and prevents food from contacting iron. Making tin plate, that's the second largest use of tin. Tin alloys are used in bearings, Babbitt metals, alloys of tin with copper and antimony. They're soft, lubricate well, handle heavy loads. Organotin compounds serve as stabilizers in PVC plastic production. Global tin production runs around 350,000 tons per year. That's tiny compared to steel or aluminum. But tin, it's a strategic metal. Without it, the electronics industry grinds to a halt. Tin prices hover around $25,000 per ton, 10 times more expensive than aluminum. Tin reserves are limited. Accessible deposits will last maybe 30 years at current extraction rates. That's why tin gets actively recycled, recovered from electronic scrap during disposal. Here's something interesting. Tin is one of the few metals we actively recycle. Electronic waste recycling has become an entire industry. Old circuit boards from computers, smartphones, and TVs get collected and shipped to specialized facilities. There, the boards are shredded, treated with chemicals, or heated. The tin dissolves or melts out, then gets extracted and purified. From 1 ton of electronic waste, you can recover up to 22 pounds of tin. This is economically and environmentally profitable. First, it reduces the strain on natural deposits, which aren't that abundant anymore. Second, you don't need to spend energy on mining and processing ore. Tin recycling requires 10 times less energy than primary production. In developed countries, up to 30% of tin comes from recycled materials. Japan, which has no deposits of its own, recycles up to 50%. And just like that, traveling from dark cassiterite crystals in tropical placer deposits, through the hellish heat of furnaces at 1300 degrees and countless purification stages, tin emerges into the world, civilization's most ancient metal, now the backbone of modern electronics. A metal that 5,000 years ago gave humanity bronze and empires, and today connects billions of transistors and processors. This is the story of how a rare element survived millennia without losing its value. What's more, it became even more critical. Every time you power up your smartphone, computer, or any electronic device, remember, inside, thousands of tiny droplets of tin hold microchips together. Without this soft silvery metal, there'd be no internet, no satellites in space, no artificial intelligence. Tin, the silent hero of the technological revolution, the metal that bridges past and future. From bronze swords of antiquity to microprocessors of today. 5,000 years of service to humanity. And this isn't the end. It's the continuation of a metal story that never goes out of style. Picture this. 8% of all CO2 on the planet comes from one industry, steel. Every single second, the world produces 60 tons of steel, and every ton leaves behind nearly 2 tons of carbon dioxide. But in Sweden, something seemingly impossible happened. They made steel without coal, 0 coal. Instead, hydrogen and electricity. Sounds like science fiction? In 2021, a Volvo truck built from this steel hit the roads, the first vehicle in history made from steel with a 0 carbon footprint. How is humanity walking away from a technology that's 3,000 years old? You'll learn why traditional steelmaking is killing the planet, how hydrogen is replacing coal and blast furnaces, and why this revolution will change everything, from skyscrapers to cars. Watch to the end. The finale will show you that the future of steel isn't black anymore. It's green. The history of steel production began 3,000 years ago when humanity learned to smelt iron. The principle remained unchanged for millennia. Iron ore is heated with coal. Carbon strips oxygen from iron oxide, and you get pure iron. This is called reduction. And the byproduct? Carbon dioxide, which escapes into the atmosphere. For centuries, nobody cared. In the 19th century, blast furnaces appeared, steel giants as tall as a 20-story building. Inside, temperatures hit 3,600 degrees Fahrenheit. Superheated air blasts in from below, while iron ore and coke, specially fired coal, get loaded from above. The ore descends, meets the carbon, and out comes molten pig iron, glowing orange like lava. Pig iron then becomes steel by blowing oxygen through it to remove excess carbon. This technology fueled the Industrial Revolution, built skyscrapers, bridges, ships, automobiles, but it comes with a monstrous cost. Every ton of steel requires about 1,300 pounds of coke. When burned and used to reduce the ore, it produces nearly 4,000 pounds of carbon dioxide for every ton of steel. Global steel production, almost 2 billion tons per year. Do the math. Around 7.5 billion tons of CO2 annually. That's 8% of all global greenhouse gas emissions, more than all aviation worldwide. If the steel industry were a country, it would rank third in emissions after China and the US. And the problem's getting worse. Demand for steel is rising, especially in developing countries. By 2050, emissions from steelmaking could double if nothing changes. Humanity's caught in a trap. Modern civilization is impossible without steel, but steel is killing the climate. Aluminum or plastic can't replace steel in most applications. The properties are just too different. We needed a revolution, and it started in cold Sweden, in the city of Luleå, above the Arctic Circle. In 2016, 3 Swedish companies, SSAB, Vattenfall, and LKAB, announced the launch of the Hybrid Project, Hydrogen Breakthrough Iron-Making Technology, a breakthrough technology for producing iron with hydrogen. The idea seemed insane. Replace carbon with hydrogen in the ore reduction process. Instead of the iron plus carbon reaction that produces CO2, use iron plus hydrogen, which gives you H2O, water, just water, no carbon dioxide. But the challenge was titanic. They needed to build a hydrogen production plant using electrolysis, powered by renewable energy. They needed to design direct reduction reactors that use hydrogen to process iron. They needed to prove this iron could be transformed into quality steel and make all of it economically viable. 5 years of work, hundreds of millions of euros in investment. In June 2021, they fired up the world's first hydrogen-based steel plant in Luleå, a pilot facility, but fully operational. The revolution had begun. Now let's break down how this actually works. The process starts with hydrogen production. Typically, hydrogen comes from natural gas, but that creates CO2 emissions. Hybrid uses water electrolysis. They run electric current from wind and hydroelectric plants through water. The water splits into hydrogen and oxygen, pure green hydrogen, zero emissions. This hydrogen feeds into a shaft furnace, a direct reduction reactor. Iron ore pellets get loaded from the top. These are walnut-sized granules made of iron oxide. Superheated hydrogen enters from below at around 1500 degrees Fahrenheit. The hydrogen rises up through the pellet bed. A chemical reaction occurs. Hydrogen strips the oxygen from the iron oxide. What forms is metallic iron and water vapor. Yep, just steam. The pellets sink downward, gradually losing oxygen and transforming into porous iron, called sponge iron or direct reduced iron, DRI. What comes out are gray, porous granules of pure iron. But this isn't steel yet. The sponge iron gets loaded into an electric arc furnace, a massive steel vessel with graphite electrodes as thick as telephone poles. They run monstrous electrical current through these electrodes, tens of thousands of amps. Between the electrodes and the metal, an electric arc forms with temperatures reaching 6,300 degrees Fahrenheit. That's hotter than the surface of the sun. The iron melts in minutes. They add alloying elements, chromium, nickel, molybdenum, to get the exact grade of steel they need. The electricity for the furnace also comes from renewables, hydroelectric plants, and wind turbines. The molten steel glows blindingly white. They pour it into molds, let it cool. What you get are steel ingots or billets, indistinguishable in properties from conventional steel, but their carbon footprint, practically zero. The entire process uses not a single ounce of coal, not a single ounce of coke, not a cubic foot of natural gas, just iron ore, hydrogen, electricity, and water. This is fossil zero metallurgy. In August 2021, a historic event occurred. The company SSAB shipped its first batch of green steel to a customer. The buyer was Volvo. This steel was used to manufacture body parts for trucks, the first vehicles in human history made from carbon-free steel. Volvo ran tests: strength, fatigue resistance, weldability, corrosion resistance, all parameters identical to regular steel, or even better. Because the process is more controlled, fewer impurities. In 2022, other companies also received batches of green steel, manufacturers of excavators, construction equipment, household appliances. Mercedes-Benz ordered a batch for use in passenger cars. SSAB announced that by 2026, it will launch the first full-scale hydrogen-based plant. Capacity, 1,300,000 tons of steel per year. By 2035, all SSAB products will be carbon-free. The company promises to cut Sweden's emissions by 7% just by switching to hydrogen. But hybrid isn't the only project out there. Right there in Sweden, they're building the H2 green steel plant, 5 million tons per year. Launch is set for 2025. In Germany, ThyssenKrupp is converting its blast furnaces to hydrogen. Austria's voestalpine fired up a pilot hydrogen plant. South Korea's POSCO is pouring billions into the technology. Even China, the world's biggest steel producer, announced it's building hydrogen plants. Governments are backing the tech with subsidies and tax breaks. The European Union rolled out a carbon tax on steel imports. More emissions, higher tariff. That makes green steel competitive. The big problem right now? The cost of green hydrogen. Hydrogen from electrolysis is still pricier than hydrogen from natural gas, but prices are dropping. Over the last 10 years, the cost of electrolysis fell by 2/3. As renewable energy capacity grows, hydrogen will get cheaper still. Another advantage of hydrogen metallurgy? It's way more compact. A traditional steel plant is an absolute monster of a complex. Coking plants, sintering factories, blast furnaces, converters, rolling mills. All of that eats up miles of land. A hydrogen facility is much tighter. An electrolyzer to produce hydrogen, a shaft furnace to reduce the ore, an electric arc furnace for melting. You can build a plant right next to your iron ore source and renewable energy, instead of hauling raw materials halfway across the globe. Swedish projects use ore from local Kiruna deposits, one of the largest in the world, and electricity from hydroelectric plants and wind farms in northern Sweden. Logistics get simpler, costs drop. Steel quality can be higher too. Direct reduction with hydrogen gives you purer iron with less sulfur, phosphorus, and other nasty impurities. That steel's better suited for high-strength applications: aviation, cars, bridges, wind turbines. Ironically, the green technology turns out to be technically superior as well. Sure, there are challenges. Hydrogen metallurgy demands massive amounts of electricity. Producing 1 ton of steel requires about 3.5 megawatt hours of power. That's a small city's daily energy consumption. That's why projects are being built where cheap renewable energy is abundant. Scandinavia with its hydroelectric plants, Germany and Denmark with wind, Australia with sun. You also need infrastructure for storing and transporting hydrogen. It's an explosive gas. They're building special pipelines, storage tanks, safety systems. But all of this is solvable. The technology exists, the economics are starting to add up, and so is the political will. Analysts predict that by 2030, 10% of the world's steel will be produced with hydrogen. By 2050, a third or even half. That'll cut CO2 emissions by 1 billion tons annually, like removing 200 million cars from the roads. The metallurgy revolution, quiet but powerful.
And just like that, journeying from ancient blast furnaces where iron was smelted with coal 3,000 years ago, through recognizing an environmental catastrophe and searching for solutions, humanity arrived at hydrogen, the most abundant element in the universe. The very same gas that stars are made of now melts steel on Earth. Instead of black smoke from blast furnace stocks, water vapor. Instead of billions of tons of carbon dioxide, water. This is a story about how a technology that seemed unshakable was rewritten in a decade. Every time you see a new skyscraper, bridge, or car 10 years from now, know this: inside, possibly, green steel. Metal produced without harming the climate. The metal of the future, made from ore, water, wind, and sun. Black metallurgy is turning green. And this isn't just a color change, it's a paradigm shift. Humanity has proven you can build civilization without destroying the planet, even in an industry as dirty as steel. The hydrogen revolution has begun, and it will change everything.
Every day, 120,000 commercial flights take off worldwide. A Boeing 777 weighs 280 tons at landing, an Airbus A380, 575 tons. The moment those wheels hit the runway, all that metal, fuel, and passengers slam into the tires at 185 miles per hour. In a fraction of a second, the tire heats up to nearly 400 degrees Fahrenheit. The load on each one is like stacking dozens of cars on a single piece of rubber. And it doesn't burst. Every flight, every day, 120,000 times. But here's the crazy part. An aircraft tire isn't built to survive just one landing. It has to last at least 200 full cycles before replacement. 200 times at 185 miles per hour. 200 times, hundreds of tons pressing down. And it can't fail. Not once.
That's not a suggestion. It's an international standard. And without meeting it, a tire doesn't get certified. How is that even possible? What's inside this black shell passengers never see, always tucked behind metal doors? Today, we're going inside an aircraft tire factory. What's in there will completely change how you see landing.
Let's start with this. An aircraft tire isn't just a bigger car tire. It's fundamentally different. Take the main landing gear tire on a Boeing 737, the world's most common airliner. Diameter, roughly 50 inches. Weight, anywhere from 220 to 265 pounds. Internal pressure, 200 pounds per square inch. Your car runs at 36 pounds per square inch. An aircraft tire inflates almost 6 times harder. That's why when one fails, rare but real, the explosion is violent enough to damage the airframe. In 2000, exploded tire debris punctured Concorde's wing and triggered the catastrophic Paris disaster. That's the cost of failure. The smoke on landing, that white puff you see in videos, isn't burning rubber. It's a tire accelerating from 0 to 185 miles per hour instantly. Before touchdown, it's stationary. At contact, instant violent spin-up. Friction, heat, smoke. The tire survives. Now, here's where it gets interesting. The tire must be both super strong and super light. Every extra pound means extra fuel every single flight, multiplied by thousands of flights yearly over the aircraft's lifetime. This balance, strength versus weight, defines absolutely everything in manufacturing. Engineers obsess over grams. Weight is money. Weight is physics. Get it wrong and airlines lose millions. The raw materials for aircraft tires aren't the same as truck tires. The main ingredient is natural rubber, not synthetic, natural. That's because it has a unique molecular structure that lets the material deform and bounce back thousands of times without fatigue failure. Synthetics can't handle that stress. Here's the thing. All natural rubber for aviation tires comes from plantations in Malaysia, Indonesia, and Thailand, from rubber trees. A farmer makes an incision in the bark. White sap flows out. Latex. After coagulation, pressing, and drying, you get dense blocks of raw rubber. Those blocks get shipped to Michelin, Goodyear, and Bridgestone factories, the trio making nearly every aircraft tire worldwide. But rubber is just the start. The second key component is nylon cord, special threads thinner than human hair that create the reinforcing skeleton inside the tire. A regular car tire has 4 cord layers. An aircraft tire, 30 to 40. And this is where something transforms plain rubber into an aviation tire. But before we get to manufacturing, here's something most people don't know. Aircraft tires aren't filled with air. They're filled with pure nitrogen. At 40,000 feet, the temperature outside hits minus 76 degrees Fahrenheit. Regular air contains moisture. At that temperature, moisture freezes, pressure jumps unpredictably, and the tire can behave on landing in ways engineers never intended. Nitrogen is dry and thermally stable. That's why it's in every aircraft tire in the world, from a small regional ATR to the massive C5 Galaxy. But nitrogen is the final step. First, you have to build what holds it.
Aircraft tire production starts with cord. Nylon threads are woven into fabric, then impregnated with rubber compound. The result is a sheet material, strong, flexible, capable of holding enormous pressure. From these sheets, layer by layer, the tire carcass is assembled by hand, not by robots, because every layer has to be stretched with precise tension, aligned, pressed down, every air bubble removed. One bubble, the size of a coin, and the tire is scrap. The operator works on a spinning drum, like a potter with clay. Only instead of clay, he's handling sheets of rubber cord, layer by layer, 30, 40 layers, each one at a precise angle to the last. This crosshatch pattern creates the strength to hold 280 tons. Building a single tire carcass takes several hours. It's handwork demanding experience. No automated line replicates this precision yet. A skilled builder spends years learning to feel the material. Next, mounting the bead ring. This rigid steel ring locks the tire onto the wheel rim, keeping it from blowing off under 200 pounds per square inch of pressure. It gets wrapped in rubber and fused into the carcass on both sides. Then the blank goes into the press mold. Vulcanization begins. Under pressure and 340 degrees Fahrenheit, rubber's molecular chains cross-link, forming a three-dimensional lattice structure. That gives the rubber its elasticity and shape memory. The tire stays 10 to 20 hours under these conditions. That's not a typo, up to 20 hours per unit. While it's in the oven, nothing can be undone. If there's a mistake, they'll only find out at inspection. Every aviation tire goes through multiple inspection levels before shipping. First, visual. A specialist with a magnifying glass examines every inch of the surface, looking for cracks, bumps, foreign contaminants. But the real inspection is invisible. X-ray imaging. Every tire gets scanned, like airport luggage, only far more powerful. The image reveals everything: how cord layers sit, where steel rings are positioned, and whether there are any air pockets inside. Even one bubble larger than allowable size, the tire gets scrapped. No exceptions. Next, ultrasonic scanning. Sensors sweep the entire surface, detecting material delamination the X-ray might miss. Every millimeter, automatically. Results get recorded in that tire's passport. Finally, dynamic testing. The tire gets inflated to working pressure and spun on a test rig, simulating landing loads. Only after passing all three levels does a tire receive its certificate and serial number. Every tire is fully traceable: manufacturer, date, raw material batch, assembler's name. If something goes wrong, they'll find the source within hours. Ever wonder why tire-related aviation incidents are single-digit cases per billion landings? That's why. Because the cost of failure isn't a warranty claim or lawsuit. It's catastrophe. Every year, the world produces about 1.5 million aircraft tires. Michelin controls roughly 60% of that market. A single tire costs $1,500 to $5,000, depending on aircraft type. Airlines replace tires every 200 landings, or sooner if wear becomes critical. But they don't throw them away. They retread them, cut new grooves, re-vulcanize the rubber, run full quality control again. One tire can go through 3 or 4 retreading cycles before it's finally recycled. That tire under your plane may have already survived several hundred landings and still passed every inspection. Next time your plane touches down and you feel that thump and rubber squeal, you'll know exactly what just happened. Hundreds of tons of metal and people entrusted to 4 pieces of rubber. Rubber that dozens of engineers designed, operators assembled by hand, X-rayed, tested with ultrasound, and ran on test rigs. Rubber that in decades has almost never failed. 120,000 times a day. Every day. Subscribe to the channel. This is where we go behind doors that are usually closed.
Each year, the world burns energy equivalent to the power of thousands of volcanoes. And all of this is contained thanks to a material almost no one thinks about: refractory brick. Its market exceeds 30 billion euros, and more than 70% of this mass is consumed by a single industry: metallurgy. Just to line one blast furnace requires up to 4,000 tons of such brick. How does ordinary clay transform into stone capable of withstanding over 1,600 degrees? And why, without this material, would factories, plants, and even our fireplaces grind to a halt? Watch carefully. Everything will become clear. At the heart of it all lies not ordinary red clay, but a particular variety, refractory clay, or kaolin. Its uniqueness derives from its chemical composition, dominated by two oxides, aluminum oxide and silicon dioxide. It is precisely their elevated content that endows the raw material with its principal characteristic, an extraordinarily high melting point. To impart stability to the finished product, manufacturers employ a rather cunning technical stratagem. A portion of the extracted clay is not sent directly into production, but is first fired in kilns at temperatures reaching up to 1,500 degrees. Through this process, the clay loses its plasticity and transforms into an exceedingly hard, stone-like material known as chamotte.
This prepared chamotte is then crushed and used as the principal component, with a specified quantity of fresh, plastic clay added to it, which acts as a binder. This approach solves a key problem. It significantly reduces shrinkage of the products during final drying and firing, preventing warping and cracking. So, the process begins with the preparation of components. Extracted clay and pre-prepared chamotte are fed to the grinding line. Giant crusher jaws split the large pieces, and then roller mills and ball mills relentlessly grind them down to a fine powder with a precisely defined grain size.
Following crushing, automated dosing systems weigh each component: grog powder, clay powder, water, with computerized precision according to the formula. This entire mixture is sent to powerful mixers, where it's intensively blended until an absolutely homogeneous mass, known as the batch, forms. Next, the shapeless mass must acquire its contours. The most common method is semi-dry pressing. The batch, containing minimal moisture, is loaded into high-strength metal molds. Then, a press bears down upon it with tremendous force, measured in hundreds of tons. Thanks to this colossal pressure, what emerges is a dense, smooth block with perfect geometry, a green brick. The next stage requires not strength, but patience and precision. The raw brick is carefully arranged on trolleys and dispatched to long tunnel dryers. This is a slow and delicate phase, which can last from 1 to several days. Inside the dryer, a meticulously controlled microclimate is maintained. Temperature gradually rises whilst humidity decreases. It is essential that moisture escapes from the brick as uniformly as possible. Any haste will result in the outer layers drying faster than the inner ones, which creates critical stresses and simply tears the brick apart with cracks from within. When all the water has been removed, the culmination arrives: firing. The brick enters the fiery tunnel of the kiln, where it awaits a true transformation. Moving slowly through different zones, it gradually heats to peak temperatures, which for fireclay brick reach 1,400 degrees, whilst for high alumina varieties may exceed 1,750 degrees. This is not merely drying, but a profound metamorphosis. At such temperatures, mineral particles soften and sinter together, forming a robust ceramic structure. Within the system of aluminum oxide and silicon dioxide, new crystalline compounds form, particularly needle-like mullite crystals, which, rather like reinforcement bars, permeate the entire structure of the brick, imparting exceptional strength to it.
Having passed the peak heating stage, the brick moves just as slowly through the cooling zone. This phase is no less crucial, since rapid cooling would cause thermal shock and destroy the product. What emerges from the kiln is an entirely new entity, a hard, resonant, slightly rough-textured block that fears no fire. What follows is purely quality control. Each piece undergoes rigorous inspection for dimensional accuracy and absence of defects, after which it is marked, packaged, and dispatched to fulfill its principal purpose, to contain flame. To grasp the true significance of refractory brick, one need only consider the numbers. The global refractory materials market represents an industry valued at more than 30 billion euros annually, and over 70% of this colossal volume of product is consumed by a single sector, ferrous metallurgy. The internal protective lining of one large blast furnace alone may require between 2,000 and 4,000 tons of refractories. And a single steel pouring ladle, which transports hundreds of tons of molten metal, gets through several complete sets of lining per year. The standard fire clay brick, grade Sha A, which is the most common type, weighs approximately 3.5 kilograms and is capable of withstanding temperatures up to 1,690 degrees Celsius. Refractory brick lines the interiors of blast furnaces, where pig iron is born from ore. It provides refractory lining for oxygen converters and electric arc furnaces, in which pig iron is transformed into steel. Enormous steel pouring ladles transporting molten metal are likewise protected internally by armor of refractories. Moreover, for each zone of the unit, a particular, specific type of brick is selected. The second most significant consumer is the cement industry. Long rotating kilns, several hundred meters in length, in which cement clinker is fired at temperatures of 1,450 degrees, are entirely lined internally with specialized varieties of refractory brick. The glass industry also cannot exist without refractories. Enormous tank furnaces, where glass mass is melted at temperatures of approximately 1,600 degrees, are lined with special, highly resistant types of brick, which are capable of withstanding for years not only the heat, but also the aggressive chemical action of molten glass. Besides these giants, refractory brick is used in thermal power engineering for lining boilers, in the chemical industry for lining reactors, and also in waste incineration furnaces. And, of course, on a far smaller scale, we encounter it in everyday life. It is precisely from Chamotte brick that fireplaces, stoves, and chimneys are built, because it guarantees safety and longevity.
Every rock you hold in your hands could be hiding miles of wire. Sounds insane, but it's true. Copper ore, this gray-green boulder, holds millions of tons of metal that powers every city on the planet. Every wire in your home, every cable underground, every power line stretching across continents. It all started with a chunk of dull rock that got blasted, crushed, and melted at 2,200 degrees. Humanity extracts 25 million tons of copper every year. That's the weight of 4,000 Eiffel Towers. Each ton requires blasting 100 tons of rock, drilling hundreds of feet deep into the earth, processing mountains of stone, and all for a metal that makes up less than 1% of the ore's mass. How do you extract red metal from gray rock? Metal that conducts electricity better than anything else on Earth. How do pits nearly a mile deep give birth to wires that light up megacities? Stick around till the end. You'll see how rock becomes the energy of civilization. Chuquicamata, northern Chile. The Atacama Desert, the driest place on Earth. Home to the planet's largest open-pit copper mine. Depth, 3,300 feet. Width, 2.5 miles. Length, 3 miles. A wound in the Earth's crust, visible from space. Excavators the size of a 3-story building gnaw at rock around the clock. Each bucket, 700 cubic feet. In 1 hour, a single excavator tears out 1,000 tons of ore. Bel AZ dump trucks with wheels 13 feet high haul 300 tons per trip. The road out of the pit, a serpentine stretch 12 miles long. Trucks spiral upward for an hour just to reach the surface. Chile produces 6 million tons of copper a year. That's 28% of the global market. Peru delivers 2.5 million tons. China mines 1.5 million but consumes 14 million. The rest it buys. The US produces 1,200,000 tons. Russia, 700,000. Copper is a strategic resource. Without it, no power grids, no communications, no electronics. Countries fight over deposits more quietly than they do over oil, but no less fiercely. Mining starts with explosions. 100-foot-tall drill rigs bore 12-inch diameter holes 65 feet deep. The well pattern is calculated to the inch. Distance between holes, 16 feet. Each one gets packed with ammonium nitrate mixed with diesel fuel. ANFO, the cheapest explosive there is. One charge, 650 pounds. A single bench takes 400 tons of explosives. Detonation controlled by electronic timers. Each hole blows with a 10-millisecond delay. That creates a destruction wave that fractures the rock without throwing it far. The blast lasts 3 seconds. Sound like an earthquake carries 20 miles. The ground heaves. A 1,000-foot column of dust rises from the pit. When the dust settles, you're looking at 2 million tons of fractured rock. Excavators move in. 24 hours to haul it all out before the next blast. The conveyor never stops. Blast, haul, drill new holes. Blast again. The pit grows 65 feet deeper every year. "6,000 years ago, on the island of Cyprus, people found a strange stone. Green, heavy, with a metallic sheen on the break. When they threw it into the fire, the stone melted and a red liquid flowed out. As it cooled, it turned into metal, soft, flexible, shiny. The ancients called it cuprum, after the island of Cyprus. They made knives, axes, jewelry from copper. But the major discovery happened in 1831. Michael Faraday created the first electric generator. Turns out copper conducts electricity better than any affordable metal. 6 times better than iron. 1.5 times better than aluminum. Only silver beats it, but that's way too expensive. Copper became the perfect conductor. In 1879, Thomas Edison built the first power station on Pearl Street in New York. Copper wires stretched through the streets. Cities began to glow at night. The era of electrification had begun. Demand for copper exploded. What was once used for coins and statues became the backbone of energy. Quarries expanded. Mines went miles deep. Humanity started devouring copper by the ton. The 20th century transformed copper into civilization's circulatory system. Every house requires 440 pounds of copper. Wiring, pipes, radiators. One car, 50 pounds of copper in the alternator, starter, wiring. One wind turbine, 9,000 pounds of copper in the generator windings. A Tesla factory for battery production, 22 million pounds of copper annually. A power transmission line across Siberia, 660 million pounds of copper and thousands of miles of wire. By the start of the 21st century, humanity was mining 33 billion pounds a year. By 2020, 55 billion, a 60% increase in 20 years. The reason, electrification of developing countries. India's building new cities. China's laying high-speed rail. Africa's installing solar panels. Copper's needed everywhere. The problem is rich ores are running out. Ore used to contain 5% copper. Now, 0.5%. To extract 1 ton of metal, you need to process 200 tons of rock. Pits are getting deeper, processes more complex, cost higher, but demand's growing faster. Ore from the pit heads to the processing plant. This is where chemistry and physics kick in. First step, crushing. Jaw crushers grind refrigerator-sized rocks down to 4-inch chunks. Cone crushers pulverize them to gravel. Ball mills turn gravel into sand. The mill's diameter, 26 feet, length, 40. Inside, steel balls weighing 110 pounds each spin around. They pound the ore, grinding it to powder. After 8 hours of rotation, the ore becomes dust. This dust gets mixed with water, creating slurry. It flows through flotation machines. These are giant tanks with air pumped in from below. Air bubbles get coated with flotation reagents, chemicals that stick to copper particles. Copper floats to the surface in foam. Waste rock settles to the bottom. The process runs through 10 stages. Each stage increases copper concentration. At the input, 0.5%. At the output, 25%. That's concentrate. From 100 tons of ore, you get 2 tons of concentrate. The remaining 98 tons? Waste that gets stored in tailings ponds the size of a lake. The concentrate heads to a copper smelter. Here it's turned into pure metal. First stage, roasting. The concentrate is heated to 1300 degrees Fahrenheit in the presence of oxygen. Sulfur burns off as sulfur dioxide gas. What's left is sinter, a mix of copper and iron oxides. The sinter gets loaded into a reverberatory furnace. Temperature 2200 degrees. Silica flux is added. Iron bonds with the silica and floats up as slag. Copper settles at the bottom as matte, an alloy that's 50% copper. The matte is poured into a converter. Pure oxygen is blasted in under pressure. Remaining iron and sulfur burn away. Temperature climbs to 2370 from the exothermic reaction. After 6 hours of blowing, what's left in the converter is blister copper, 98% pure. But that's not enough for wires, you need electrolysis. Blister copper is cast into anodes 2 inches thick. They're submerged in tanks filled with copper sulfate solution. A current of 2 volts runs through. Copper dissolves off the anodes and deposits onto cathodes. After 3 weeks, the cathodes are coated with a layer of pure copper 4 inches thick. Purity, 99.99%. This is market-grade copper, ready to become wire. And just like that, after a journey from an explosion in a half-mile deep quarry through crushing, flotation, smelting at temperatures above 1800 degrees Fahrenheit, and electrolysis, gray rock transforms into red metal that carries electricity to every home on the planet. Without copper, there'd be no light in cities. No internet. Every data center runs on copper busbars. No electric cars. A single Tesla contains 175 pounds of copper. No renewable energy. Solar and wind farms need 3 times more copper than coal plants. Every year, humanity lays down 6 million miles of copper wire. That's the distance from Earth to the Sun and back 7 times. 25 million tons of metal connecting continents into a single electrical grid. Copper is civilization's nervous system. Electrical impulses race through copper veins like thoughts through neurons. Factories operate, hospitals save lives, homes glow in the night. All thanks to metal that was once just green rock in the ground. Every time you flip a light switch, remember, between your finger and that bulb, miles of copper wire born from an explosion in a desert quarry on the other side of the world. It's the magic of turning stone into energy. And this magic won't stop as long as cities shine. Every year, over 1,000 giant ships are sent for scrapping, each weighing up to 50,000 tons, nearly the length of 3 football fields. It's like dismantling an entire floating city with hundreds of miles of cables, tons of toxic substances, and metal worth millions of dollars. One mistake, and an environmental disaster becomes inevitable. But here's the thing, that's not even the most surprising part. Inside each of these massive vessels lies something that turns scrapping into a genuine treasure hunt. Workers risk their lives amid plasma cutters and toxic fumes to extract these valuables. What exactly are they after, and why have some countries turned ship graveyards into a multi-billion-dollar business whose dark side everyone stays silent about? Stick around till the end. What you're about to discover will make you look at every ship in port with completely different eyes. This is the story of how steel giants die and new metal is born. Why is ship recycling important? The vessels we typically picture as massive floating megastructures can stretch nearly 1,000 feet long. Their weight sometimes reaches tens of thousands of tons, making them among the largest man-made objects created for ocean travel and cargo transport. But beyond their massive scale, these ships have an incredibly complex internal structure. Hundreds of miles of cables, pipelines, shafts, and various safety and comfort systems, plus countless different components and mechanisms serving different functions. This entire architecture isn't just metal, it's a complex organism that needs to be very carefully and properly dismantled when a ship reaches the end of its service life. It's absolutely critical to properly remove all hazardous substances accumulated during its operation.